falsification of a theory may be described in a similar way. We need not say that the theory is false, but we may say instead that it is contradicted by a certain set of accepted basic statements. Nor need we say of basic statements that they are true or false, for we may interpret their acceptance as the result of a conventional decision, and the accepted statements as results of this decision. This certainly does not mean that we are forbidden to use the concepts true and false, or that their use creates any particular difficulty. The very fact that we can avoid them shows that they cannot give rise to any new fundamental problem. The use of the concepts true and false is quite analogous to the use of such concepts as tautology, contradiction, conjunction, implication, and others of the kind. These are non-empirical concepts, logical concepts. They describe or appraise a statement irrespective of any changes in the empirical world. Whilst we assume that the properties of physical objects, of genidentical objects in Lewin's sense, change with the passage of time, we decide to use these logical predicates in such a way that the logical properties of statements become timeless. If a statement is a tautology, then it is a tautology once and for all. This same timelessness we also attach to the concepts true and false, in agreement with common usage. It is not common usage to say of a statement that it was perfectly true yesterday but has become false today. If yesterday we appraised a statement as true which today we appraise as false, then we implicitly assert today that we were mistaken yesterday, that the statement was false even yesterday, timelessly false, but that we erroneously took it for true. Here one can see very clearly the difference between truth and corroboration. The appraisal of a statement as corroborated or as not corroborated is also a logical appraisal and therefore also timeless, for it asserts that a certain logical relation holds between a theoretical system and some system of accepted basic statements. But we can never simply say of a statement that it is as such, or in itself, corroborated, in the way in which we may say that it is true. We can only say that it is corroborated with respect to some system of basic statements, a system accepted up to a particular point in time. The corroboration which a theory has received up to yesterday is logically not identical with the corroboration which a theory has received up to today. Thus we must attach a subscript, as it were, to every appraisal of corroboration, a subscript characterizing the system of basic statements to which the corroboration relates, for example, by the date of its acceptance. Corroboration is therefore not a truth value, that is, it cannot be placed on a par with the concepts true and false, which are free from temporal subscripts, for to one and the same statement there may be any number of different corroboration values, of which indeed all can be correct or true at the same time. For they are values which are logically derivable from the theory and the various sets of basic statements accepted at various times. The above remarks may also help to elucidate the contrast between my views and those of the pragmatists who propose to deem truth in terms of the success of a theory and thus of its usefulness, or of its confirmation or of its corroboration. If their intention is merely to assert that a logical appraisal of the success of a theory can be no more than an appraisal of its corroboration, I can agree. But I think that it would be far from useful to identify the concept of corroboration with that of truth. This is also avoided in ordinary usage. For one might well say of a theory that it has hardly been corroborated at all so far, or that it is still uncorroborated. But we should not normally say of a theory that it is hardly true at all so far, or that it is still false. 85. The path of science. One may discern something like a general direction in the evolution of physics, a direction from theories of a lower level of universality to theories of a higher level. This is usually called the inductive direction, and it might be thought that the fact that physics advances in this inductive direction could be used as an argument in favor of the inductive method. Yet an advance in the inductive direction does not necessarily consist of a sequence of inductive inferences. Indeed, we have shown that it may be explained in quite different terms in terms of degree of testability and corroborability. For a theory which has been well corroborated can only be superseded by one of a higher level of universality, that is, by a theory which is better testable and which, in addition, contains the old, well corroborated theory or at least a good approximation to it. It may be better, therefore, To describe that trend, the advance towards theories of an ever higher level of universality as quasi-inductive. The quasi-inductive process should be envisaged as follows. The IES of some level of universality are proposed, and deductively tested. After that, theories of a higher level of universality are proposed, and in their turn tested with the help of those of the previous levels of universality, and so on. The methods of testing are invariably based on deductive inferences from the higher to the lower level. On the other hand, the levels of universality are reached, in the order of time, by proceeding from lower to higher levels. The question may be raised, why not invent theories of the highest level of universality straight away? Why wait for this quasi-inductive evolution? Is it not perhaps because there is after all an inductive element contained in it? I do not think so. Again and again suggestions are put forward, conjectures, or theories of all possible levels of universality. Those theories which are on too high a level of universality, as it were, that is, too far removed from the level reached by the testable science of the day, give rise, perhaps, to a metaphysical system. In this case, even if from this system statements should be deducible, or only semi-deducible, as for example in the case of Spinoza's system, which belong to the prevailing scientific system, there will be no new testable statement among them, which means that no crucial experiment can be designed to test the system in question. If, on the other hand, a crucial experiment can be designed for it, then the system will contain, as ARST approximation, some well-corroborated theory, and at the same time also something new and something that can be tested. Thus the system will not, of course, be metaphysical. In this case, the system in question may be looked upon as a new advance in the quasi-inductive evolution of science. This explains why a link with the science of the day is as a rule established only by those theories which are proposed in an attempt to meet the current problem situation, that is, the current difficulties, contradictions, and falsifications. In proposing a solution to these difficulties, these theories may point the way to a crucial experiment. To obtain a picture or model of this quasi-inductive evolution of science, the various ideas and hypotheses might be visualized as particles suspended in a fluid. Testable science is the precipitation of these particles at the bottom of the vessel. They settle down in layers, of universality. The thickness of the deposit grows with the number of these layers, every new layer corresponding to a theory more universal than those beneath it. As the result of this process, ideas previously floating in higher metaphysical regions may sometimes be reached by the growth of science, and thus make contact with it, and settle. Examples of such ideas are atomism, the idea of a single physical principle or ultimate element, from which the others derive, the theory of terrestrial motion, opposed by Bacon as Titius, the age-old corpuscular theory of light, the fluid theory of electricity, revived as the electron gas hypothesis of metallic conduction. All these metaphysical concepts and ideas may have helped, even in their early forms, to bring order into man's picture of the world, and in some cases they may even have led to successful predictions. Yet an idea of this kind acquires scientific status only when it is presented in falsifiable form, that is to say, only when it has become possible to decide empirically between it and some rival theory. My investigation has traced the various consequences of the decisions and conventions, in particular of the criterion of demarcation adopted at the beginning of this book. Looking back, we may now try to get a last comprehensive glimpse of the picture of science and of scientific discovery which has emerged. What I have here in mind is not a picture of science as a biological phenomenon, as an instrument of adaptation, or as a roundabout method of production. I have in mind its epistemological aspects. Science is not a system of certain, or well-established, statements, nor is it a system which steadily advances towards a state of nullity. Our science is not knowledge, episteme. It can never claim to have attained truth, or even a substitute for it, such as probability. Yet science has more than mere biological survival value. It is not only a useful instrument. Although it can attain neither truth nor probability, the striving for knowledge and the search for truth are still the strongest motives of scientific discovery. We do not know, we can only guess. And our guesses are guided by the unscientific, the metaphysical, though biologically explicable, faith in laws, in regularities which we can discover. Like Bacon, we might describe our own contemporary science, the method of reasoning which men now ordinarily apply to nature, as consisting of anticipations, rash and premature, and of prejudices. But these marvelously imaginative and bold conjectures or anticipations of ours are carefully and soberly controlled by systematic tests. Once put forward, none of our anticipations are dogmatically upheld. Our method of research is not to defend them, in order to prove how right we were. On the contrary, we try to overthrow them. Using all the weapons of our logical, mathematical, and technical armory, we try to prove that our anticipations were false in order to put forward, in their stead, new unjustified and unjustifiable anticipations, new rash and premature prejudices, as Bacon derisively called them. It is possible to interpret the ways of science more prosaically. One might say that progress can come about only in two ways, by gathering new perceptual experiences, and by better organizing those which are available already. But this description of scientific progress, although not actually wrong, seems to miss the point. It is too reminiscent of Bacon's induction, too suggestive of his industrious gathering of the countless grapes, ripe and in season, from which he expected the wine of science to of his myth of a scientific method that starts from observation and experiment and then proceeds to theories. This legendary method, by the way, still inspires some of the newer sciences which try to practice it because of the prevalent belief that it is the method of experimental physics. The advance of science is not due to the fact that more and more perceptual experiences accumulate in the course of time. Nor is it due to the fact that we are making ever better use of our senses. Out of uninterpreted sense experiences science cannot be distilled, no matter how industriously we gather and sort them. Bold ideas, unjustified anticipations, and speculative thought, are our only means for interpreting nature, our only organon, our only instrument, for grasping her. And we must hazard them to win our prize. Those among us who are unwilling to expose their ideas to the hazard of refutation do not take part in the scientific game. Even the careful and sober testing of our ideas by experience is in its turn inspired by ideas. Experiment is planned action in which every step is guided by theory. We do not stumble upon our experiences, nor do we let them over us like a stream. Rather, we have to be active, we have to make our experiences. It is we who always formulate the questions to be put to nature, it is we who try again and again to put these questions so as to elicit a clear-cut yes or no, for nature does not give an answer unless pressed for it. And in the end, it is again we who give the answer, it is we ourselves who, after severe scrutiny, decide upon the answer to the question which we put to nature after protracted and earnest attempts to elicit from her an unequivocal no. Once and for all, says Whale, with whom I fully agree, I wish to record my unbounded admiration for the work of the experimenter in his struggle to wrest interpretable facts from an unyielding nature who knows so well how to meet our theories with a decisive no or with an inaudible yes. The old scientific ideal of episteme of absolutely certain, demonstrable knowledge has proved to be an idol. The demand for scientific objectivity makes it inevitable that every scientific statement must remain tentative forever. It may indeed be corroborated, but every corroboration is relative to other statements which, again, are tentative. Only in our subjective experiences of conviction, in our subjective faith, can we be absolutely certain. With the idol of certainty, including that of degrees of imperfect certainty or probability, there falls one of the defenses of obscurantism which bar the way of scientific advance. For the worship of this idol hampers not only the boldness of our questions, but also the rigor and the integrity of our tests. The wrong view of science betrays itself in the craving to be right, for it is not his possession of knowledge, of irrefutable truth, that makes the man of science, but his persistent and recklessly critical quest for truth. Has our attitude, then, to be one of resignation? Have we to say that science can fool only its biological task, that it can, at best, merely prove its mettle in practical applications which may corroborate it? Are its intellectual problems insoluble? I do not think so. Science never pursues the illusory aim of making its answers null, or even probable. It advances, rather, towards an innate yet attainable aim, that of ever discovering new, deeper, and more general problems, and of subjecting our ever tentative answers to ever renewed and ever more rigorous tests. This is the end of the text of the original book. The appendices I-7 which are here printed on pages 0 were also part of that original edition. Addendum. In the preceding chapter of my book, which was the null chapter, I tried to make clear that by the degree of corroboration of a theory I mean a brief report that summarizes the way in which the theory has stood up to tests, and how severe these tests were. I have never deviated from this view. See for example the beginnings of the new appendices 7, p. 9, p0, and especially the last section, of 9, pp. F. Here I wish to add the following points. 1. The logical and methodological problem of induction is not insoluble, but my book aired a negative solution. A. We can never rationally justify a theory, that is to say, our belief in the truth of a theory, or in its being probably true. This negative solution is compatible with the following positive solution, contained in the rule of preferring theories which are better corroborated than others. B. We can sometimes rationally justify the preference for a theory in the light of its corroboration, that is, of the present state of the critical discussion of the competing theories, which are critically discussed and compared from the point of view of assessing their nearness to the truth, verisimilitude. The current state of this discussion may, in principle, be reported in the form of their degrees of corroboration. The degree of corroboration is not, however, a measure of verisimilitude. Such a measure would have to be timeless, but only a report of what we have been able to ascertain up to a certain moment of time, about the comparative claims of the competing theories by judging the available reasons which have been proposed for and against their verisimilitude. 2. A metaphysical problem raised by the idea of verisimilitude is, are there genuine regularities in nature? My reply is yes. One of the arguments, non-scientific but perhaps transcendental, see pages, in favor of this reply is, if no regularities were apparent in nature then neither observations nor language could exist, neither a descriptive nor an argumentative language. 3. The force of this reply depends on some kind of common-sense realism. 4. The pragmatic problem of induction solves itself. The practical preference for the theory which in the light of the rational discussion appears to be nearer to the truth is risky but rational. 5. The psychological problem, why do we believe that the theory so chosen will continue to be worthy of our trust, is, I suggest, trivial. A belief or trust is always irrational, but it may be important for action. 6. Not all possible problems of induction are solved in this way. See also my forthcoming book, Objective Knowledge, An Evolutionary Approach. Appendix I. Definition of the dimension of a theory, cf. sections and. The definition which follows here should be regarded as only provisional. It is an attempt to define the dimension of a theory so as to make it agree with the dimension of the set of curves which results if the field of application of the theory is represented by a graph paper. A difficulty arises from the fact that we should not assume that either a metric or even a topology is defined for the field. To begin with, in particular, we should not assume that any neighborhood relations are defined. And I admit that this difficulty is circumvented rather than overcome by the definition proposed. The possibility of circumventing. Appendices. It is connected with the fact that a theory always prohibits some homotypic events, as we have called them, i.e. a class of occurrences which differ only in their spatio-temporal coordinates, cf. sections and. For this reason, spatio-temporal coordinates will, in general, appear in the schema which generates the field of application, and consequently the field of the relatively atomic statements will, in general, show a topological and even a metrical order. The proposed definition says, A theory T is called D-dimensional with respect to the ELD of application F if and only if the following relation holds between T and F. There is a number D such that, A, the theory does not clash with any D-tuple of the ELD and, B, any given D-tuple in conjunction with the theory divides all the remaining relatively atomic statements uniquely into two inite subclasses A and B, such that the following conditions are satisfied: alpha, every statement of the class A forms, when conjoined with the given D-tuple, A falsifying D plus tuple, i.e. a potential falsier of the theory. Beta, the class B on the other hand is the sum of one or more, but always a inite number, of inite subclasses by such that the conjunction of any number of statements belonging to any one of these subclasses by is compatible with the conjunction of the given D-tuple and the theory. This definition is intended to exclude the possibility of a theories having two ELDs of application such that the relatively atomic statements of one ELD result from the conjunction of the relatively atomic statements of the other. This must be prevented if the ELD of application is to be identical with that of its graphic representation, cf section. I may add that by means of this definition the problem of atomic statements, cf note to section, is solved in a manner which might be described as deductivist, since the theory itself determines which singular statements are relatively atomic, with respect to the theory. For it is the theory itself through which the ELD of application is deemed, and with it the statements which because of their logical form have equal status with respect to the theory. Thus the problem of the atomic statements is not solved by the discovery of statements of some elementary form out of which the other, more composite, statements are built up inductively, or composed by the method of truth functions. On the contrary, the relatively atomic statements and along with them the singular statements appear as a sort of precipitation, as it were, or as a, relatively, solid deposit, laid down by the universal statements of the theory. Appendix 2. The general calculus of frequency in finite classes, cf sections. And the general multiplication theorem, we denote the inite reference class by alpha, and the two property classes by beta and gamma. Our RST problem is to determine the frequency of those elements which belong both to beta and to gamma. The solution is given by the formula alpha f superscript 2, beta dot gamma, equals alpha f superscript 2, beta, dot alpha dot beta f superscript 2, gamma. Or, since beta and gamma may be commuted, cent, alpha f superscript 2, beta dot gamma, equals alpha dot gamma f superscript 2, beta, dot alpha f superscript 2, gamma. The proof results immediately from the definition given in section. From, we obtain, by substitution in accordance with this definition, comma, n, alpha dot beta dot gamma, n, alpha, equals n, alpha dot beta, n, alpha, n, alpha dot beta dot gamma, n, alpha dot beta, which proves to be an identity after cancellation of n, alpha dot beta. Contrast with this proof, and with the proof of S, by Reichenbach in Mathematische p. If we assume independence, cf section, i.e. S. Alpha dot beta f superscript 2, gamma, equals alpha f superscript 2, gamma. We obtain from, the special multiplication theorem, S. Alpha f superscript 2, beta dot gamma, equals alpha f superscript 2, beta, dot alpha f superscript 2, gamma. With the help of the equivalence of, and, cent, the symmetry of the relation of independence can be proved, cf note to section. The addition theorems deal with the frequency of those elements which belong either to beta or to gamma. If we denote the disjunctive combination bination of these classes by the symbol beta plus gamma, where the sign plus, if placed between class designations, sign is not arithmetical addition but the non-exclusive or, then the general addition theorem is alpha f superscript 2, beta plus gamma, equals alpha f superscript 2, beta, plus alpha f superscript 2, gamma, alpha f superscript 2, beta dot gamma. This statement follows from the definition in section if we use the universally valid formula of the calculus of classes. Comma. alpha dot beta plus gamma equals alpha dot beta plus alpha dot gamma. And the formula, which is also universally valid, comma, n beta plus gamma equals n beta plus n gamma n beta dot gamma. Under the assumption that, within alpha, beta and gamma have no member in common, a condition which can be symbolized by the formula S n alpha dot beta dot gamma equals 0. Appendices. We obtain from the special addition theorem S alpha f superscript 2 beta plus gamma equals alpha f superscript 2 beta plus alpha f superscript 2 gamma. The special addition theorem holds for all properties which are primary properties within a class alpha, since primary properties are mutually exclusive. The sum of the relative frequencies of these primary properties is of course always equal to. The division theorems state the frequency of a property gamma within a class selected from alpha with respect to the property beta. The general formula is obtained immediately by inversion of alpha dot beta f superscript 2 gamma equals alpha f superscript 2 beta dot gamma slash alpha f superscript 2 beta. If we transform the general division theorem, with the help of the special multiplication theorem, we obtain S alpha dot beta f superscript 2 gamma equals alpha f superscript 2 gamma. In this formula we recognize again the condition S, thus we see that independence may be described as a special case of selection. The various theorems which may be connected with the name of Bayes are all special cases of the division theorem. Under the assumption that alpha dot gamma is a subclass of beta, or in symbols Bs alpha dot gamma I beta, we obtain from the RST special form of Bayes' rule Bs alpha dot beta f superscript 2 gamma equals alpha f superscript 2 gamma slash alpha f superscript 2 beta I. We can avoid the assumption Bs by introducing, in place of beta, the sum of the classes beta, beta, beta n. We shall, in analogy to our use of the sign plus between class designations, use the sign backslash in front of class designations. We can then write a second, universally valid, form of Bayes' theorem as follows. B alpha dot backslash beta f superscript 2 beta I equals alpha f superscript 2 beta I slash alpha f superscript 2 backslash beta I. To the numerator of this formula we can apply the special addition theorem S, if we assume that the beta I have no members in common in alpha. This assumption can be written slash S n alpha dot beta j equals 0 I superscript 1j. Under this assumption we obtain the third, special, form of Bayes' theorem, which is always applicable to primary properties beta I slash S alpha dot backslash beta f superscript 2 beta I equals alpha f superscript 2 beta I slash backslash alpha f superscript 2 beta I. The fourth and most important special form of Bayes' theorem may be obtained from the last two formulae together with its constituent assumptions, slash S, and Bs. Bs. Alpha dot gamma I backslash beta I. Which is always satisfied if gamma I backslash beta I is satisfied. Substituting in, slash S, beta I gamma for beta I, we apply to the left side of the result the formula. Bs. Alpha dot backslash beta I dot gamma equals alpha dot gamma. Bs. To the right side of the result we apply, cent, both to the denominator and denominator. Thus we obtain S. Alpha comma gamma f superscript 2, beta I, equals alpha dot if superscript 2, gamma, dot alpha f superscript 2, beta I, slash backslash, alpha dot beta f superscript 2, gamma, dot alpha f superscript 2, beta I. Thus if beta I is an exclusive system of property classes, and any property class which is, within alpha, part of beta I, then, S, gives the frequency of every one of the properties beta I within a selection with respect to gamma. Appendix 3. Derivation of the first form of the binomial formula, for finite sequences of overlapping segments. Cf section. The RST binomial formula. N. 1, alpha F superscript 2, M, equals NCMPMQN, M. Where P equals alpha F superscript 2, Q equals alpha F superscript 2, 0, Mn, may be said to be proved under the assumption that alpha is, at least, n, I free, neglecting errors arising at the last term, cf section, if we can show that n. 2, alpha F superscript 2, sigma m, equals PMQN, m. Where sigma m denotes one particular n-tuple, although an arbitrarily chosen one, which contains m1s. The symbol is intended to indicate that what is given is the complete arrangement of this n-tuple, i.e. not only the number of ones but also their positions in the n-tuple. 4. Note that, n, is an alternative way of writing the binomial coefficient nc, i.e. the number of ways in which m things may be arranged in n places, provided mn. Assume that, holds for all n, m, and sigma, i.e. the various arrangements of the ones. Then there will be, according to a well-known combinatorial theorem, NCM distinct ways of distributing m1s in n places, and in view of the special addition theorem, we could then assert. Now suppose, to be proved for any one n, i.e. for one particular n and for every m and every sigma which are compatible with this n. We now show that given this assumption it must also hold for n plus, i.e. we shall prove 0 and, comma, alpha f superscript 2, sigma m plus 0, equals pmqn plus, m, n plus, alpha f superscript 2, sigma m plus, equals pm plus q, n plus, m plus. Where sigma m plus 0 or sigma m plus respectively signify those sequences of the n plus length which result from sigma m by adding to its end a 0 or a 1. Let it be assumed, for every length n of the n tuples, or segments, considered, that alpha is, at least, n, free, from after ect, thus for a segment of the length n plus, alpha has to be regarded as being at least n free. Let sigma m denote the property of being a successor of an n-tuple sigma m. Then we can assert 0, comma, alpha f superscript 2, sigma m point 0, equals alpha f superscript 2, sigma m, dot alpha f superscript 2, 0, equals alpha f superscript 2, sigma m, q alpha f superscript 2, sigma m, equals alpha f superscript 2, sigma m, dot alpha f superscript 2, equals alpha f superscript 2, sigma m, p. We now consider that there must obviously be just as many sigma m, i.e. successors of the sequence sigma m in alpha, as there are sequences sigma m in alpha, n, and hence that n alpha f superscript 2, sigma m, equals alpha f superscript 2, sigma m, n plus. With this we can transform the right-hand side of. For the same reason we have 0. Alpha f superscript 2, sigma m point 0, equals alpha f superscript 2, sigma m plus 0, comma, alpha f superscript 2, sigma m, equals alpha f superscript 2, sigma m plus, n plus. With these we can transform the left-hand side of. That is to say, we obtain by substituting, and, in 0, comma, alpha f superscript 2, sigma m plus 0, equals alpha f superscript 2, sigma m, q, n plus, n plus, n. Alpha f superscript 2, sigma m plus, equals alpha f superscript 2, sigma m, p. Thus we see that, assuming that, holds for some one n, and all the arrangements sigma m belonging to it, we can derive, by mathematical induction. That is in fact valid for n equals n for all sigma m, where m is seen by assuming rstm equals and then m equals 0. Thus we can assert 3, and consequently, and Appendix 4. A method of constructing models of random sequences, cf sections. And we assume, as in section, that for every given night number n a generating period can be constructed which is n-free, from after ect, and which shows equal distribution. In every such period, every combinatorially possible x tuple, for xn plus, of ones and zeros will appear at least once. A. We construct a model sequence which is absolutely free, from after ect, in the following way. We write down an n-free period for an arbitrarily chosen n. This period will have a night number of terms, say n. We now write down a new period which is at least n, free. Let the new period have the length n. In this new period, at least one sequence must occur which is identical with the previously given period of length n, and we rearrange the new period in such a way that it begins with the sequence. This is always possible, in accordance with the analysis of section. This we call the second period. We now write down another new period which is at least n, free, and seek in this third period that sequence which is identical with the second period, after rearrangement, and then so rearrange the third period that it begins with the second, and so on. In this way we obtain a sequence whose length increases very quickly and whose commencing period is the period which was written down rst. This period, in turn, becomes the commencing sequence of the second period, and so on. By prescribing a particular commencing sequence together with some further conditions, e.g. that the periods to be written down must never be longer than necessary, so that they must be exactly ni, free, and not merely at least ni, free, this method of construction may be so improved as to become unambiguous and to denote a d-night sequence, so that we can calculate for every term of the sequence whether it is a 1 or a 0. We thus have a d-night sequence, constructed according to a mathematical rule, with frequencies whose limits are f cent equals f cent, 0, equals alpha alpha. By using the procedure employed in the proof of the third form of the binomial formula, section 0, or of the theorem of Bernoulli, section, it can be shown, with any degree of approximation, for whatever frequency value we may choose, that there exist sequences which are absolutely free, provided only that we make the assumption, which we have just proved, that at least one sequence exists which is absolutely free. B. An analogous method of construction can now be used to show that sequences exist which possess an absolutely free middle frequency, cf section, even though they have no frequency limit. We need only change procedure, a, in such a way that after some given number of increases in length, we always add to the sequence a night block, or iteration, of ones, for example. This block is made so long that some given frequency p which is different from is reached. After attaining this frequency, the whole sequence now written down, it may now have the length m, is regarded as the commencing sequence of a period which is m, free, with equal distribution, and so on. C. Finally, it is possible to construct in an analogous way a model of a sequence which has more than one absolutely free middle frequency. According to A, there are sequences which do not have equal distribution and are absolutely free. Thus all we have to do is to combine two such sequences, A and B, with the frequencies P and Q, in the following way. We write down some commencing sequence of A, then search B, until we end in it the sequence, and rearrange the period of B, preceding this point in such a way that it begins with the sequence written down. We then use this whole rearranged period of B, as commencing sequence. Next we search A, until we end this new written down sequence, rearrange A, and so on. In this way we obtain a sequence in which again and again terms occur up to which it is ni free for the relative frequency p of the sequence, A, but in which also again and again terms occur up to which the sequence is ni free for the frequency q of b. Since in this case the numbers ni increase without limit, we obtain a mode of construction for a sequence which has two distinct middle frequencies, both of which are absolutely free. For we did determine a and b in such a way that their frequency limits are distinct. Note: the applicability of the special multiplication theorem to the classical problem of throwing two dice x and y at a time, and related problems, is assured if, for example, we make the hypothetical estimate that the combination sequence, as we may call it, i.e. the sequence alpha that has the throws with x as its odd terms and the throws with y as its even terms, is random. Appendix V. Examination of an objection. The two-slit experiment, cf. Section. The imaginary experiment described below under A is intended to refute my assertion that arbitrarily exact simultaneous, non-predictive, measurements of the position and momentum of a particle are compatible with the quantum theory. A. Let A be a radiating atom, and let light from it fall on a screen S after passing through two slits, SL and SL. According to Heisenberg, we can in this case measure exactly either the position of A or the momentum of the radiation, but not both. If we measure the position exactly, an operation that blurs or smears the momentum, then we can assume that light is emitted from A in spherical waves. But if we measure the momentum exactly, for example by measuring the recoils due to the emission of photons, thereby blurring or smearing the position, then we are able to calculate the exact direction and the momentum of the emitted photons. In this case we shall have to regard the radiation as corpuscular, needle radiation. Thus to the two measuring operations there correspond two different kinds of radiation, so that we obtain two different experimental results. For if we measure the position exactly we obtain an interference pattern on the screen, a point-like source of light, and one whose position can be exactly measured is point-like emits coherent light. If on the other hand we measure the momentum exactly, we get no interference pattern. Flashes of light, or scintillations, without interference pattern, appear on the screen after the photons have passed through the slits, consonantly with the fact that the position is blurred or smeared and that a non-point-like source of light does not emit coherent light. If we were to suppose that we could measure both the position and the momentum exactly, then the atom would have to emit, on the one hand, according to the wave theory, continuous spherical waves that would produce interference patterns, and it would have to emit, on the other hand, an incoherent corpuscular beam of photons. If we were able to calculate the path of each photon we should never get anything like interference, in view of the fact that photons neither destroy one another nor otherwise interact. The assumption of exact measurements of position and momentum taken simultaneously leads thus to two mutually contradictory predictions. For on the one hand it leads to the prediction that interference patterns will appear, and on the other hand to the prediction that no interference patterns will appear. B. I shall now reinterpret this imaginary experiment statistically. I shall deal RST with the attempt to measure position exactly. I replace the single radiating atom by a cluster of atoms in such a way that coherent light is emitted by them, and propagated in the form of spherical waves. This result is obtained by the use of a second screen pierced by a very small aperture A so placed between the atom cluster and the RST screen that the aperture A is in exactly the place previously occupied by the single radiating atom A. The atom cluster emits light which, after undergoing selection according to a given position by passing through the aperture A, spreads in the form of continuous spherical waves. Thus we replace the single atom, whose position is exactly determined, by a statistical case of pure positional selection. C. In a similar way, the atom with exactly measured momentum but blurred or smeared position will be replaced by a pure selection according to a given momentum, or, in other words, by a monochromatic beam of photons traveling along parallel lines from some, non-point-like, source of light. In each of the two cases we obtain the correct experimental result, interference patterns in case B, and no interference patterns in case C. D. How are we to interpret the third case, which is supposed to lead to two mutually contradictory predictions. To discover this, we imagine that we have exactly observed the path of the atom A, which means both its position and its momentum. We should then nd that the atom emits single photons, and recoils with each emission. Each recoil shifts it to another position, and each time the shift is in a new direction. Assuming that the atom radiates in this way for a period of time, we do not raise the question whether it also absorbs energy during this period. It will take up a number of dierent positions during this period, ranging over a considerable volume of space. For this reason, we are not allowed to replace the atom by a point-like cluster of atoms. We can only replace it by a cluster of atoms distributed over a considerable volume of space. Furthermore, since the atom radiates in all directions, we have to replace it by a cluster of atoms radiating in all directions. Thus we do not obtain a pure case, nor do we get coherent radiation. And we do not get interference patterns. Objections similar to the one here examined may be reinterpreted statistically along the lines of this example. In connection with our analysis of this imaginary experiment, I should like to say that argument A, contrary to what might be supposed at RST, would be in any case quite insufficient to elucidate the so-called problem of complementarity, or the dualism of wave and particle. It tries to do so by showing that the atom is able to emit only either coherent waves or incoherent photons, and that therefore no contradiction arises, because the two experiments are mutually exclusive. But it is simply not true that the two experiments are mutually exclusive, for we can of course combine a not too exact measurement of position with a not too exact measurement of momentum, and in this case the atom neither emits completely coherent waves nor completely incoherent photons. My own statistical interpretation has, clearly, no difficulty whatever in treating such intermediate cases, even though it was never intended to solve the problem of the dualism of waves and particles. I suppose that a really satisfactory solution of this problem will hardly be possible within the framework of statistical quantum physics, Heisenberg's and Schrödinger's particle theory as interpreted by Born, but I think it might perhaps be solved within the framework of the quantum physics of wave-elds or the second quantization, Dirac's emission and absorption theory and the wave-eld theory of matter by Dirac, Jordan, Pauli, Klein, Me, Wigner. Cf. Note to my introduction to section. Appendix 6. Concerning a non-predictive procedure of measuring, cf. Section. We suppose that a non-monochromatic beam of particles, for instance a beam of light moving along parallel paths in the x direction, is subjected to selection of their momenta by the interposition of Alter. If the beam consists of electrons, we shall have to use instead of Alter an electric eld perpendicular to the direction of the beam in order to analyze its spectrum. We assume with Heisenberg that this procedure leaves unaltered the momenta, or, more precisely, their components in the x direction, and consequently also the velocities, or their x components, of the selected particles. Behind Alter we put a Geiger counter, or a moving strip of photographic LM, in order to measure the time of arrival of the particles, and this allows us, since the velocities of the particles are known, to calculate their x-co ordinates for any instant preceding their time of arrival. Now we may consider two possible assumptions. If, on the one hand, it is assumed that the x-co ordinates of the positions of the particles were not interfered with by the measuring of their momenta, then the measurement of position and momentum can be validly extended to the time before the momentum was selected, by the Alter. If, on the other hand, it is assumed that a selection according to the momentum does interfere with the x-co ordinates of the positions of the particles, then we can calculate their paths exactly only for the time interval between the two measurements. Now the assumption that the position of the particles in the direction of their height might be disturbed in some unpredictable way by a selection according to a given momentum means the same as that the position co ordinate of a particle would be altered in some incalculable way by the selection. But since the velocity of the particle has remained unchanged, this assumption must be equivalent to the assumption that, owing to that selection, the particle must have jumped discontinuously, with superluminal velocity, to a dierent point of its path. This assumption, however, is incompatible with the quantum theory as at present accepted. For although the theory permits discontinuous jumps, it permits them only in the case of particles within an atom, within the range of discontinuous eigenvalues, but not in the case of free particles within the range of continuous eigenvalues. It is possible, presumably, to design a theory, in order to escape the conclusions reached above, or to preserve the principle of indeterminacy, which alters the quantum theory in such a way that the assumption of a disturbance of the position by selecting the momentum is compatible with it, but even this theory, which I might call a theory of indeterminacy, could derive only statistical consequences from the principle of indeterminacy, and could therefore be corroborated only statistically. Within this theory, the principle of indeterminacy would only be a formally singular probability statement, although its content would go beyond what I have called the statistical scatter relations. For, as will be shown below with the help of an example, these are compatible with the assumption that selecting the momentum does not disturb the position. Thus this latter assumption does not allow us to infer the existence of a superpure case such as is forbidden by the scatter relations. This statement shows that the method of measuring I have examined does not eke the statistically interpreted formulae of Heisenberg. It may thus be said to occupy, within my statistical interpretation, the same logical place, as it were, as, within his interpretation, Heisenberg's statement denying the physical reality of exact measurements. In fact, one might regard my statement as the translation of Heisenberg's statement into the statistical language. That the statement in question is correct may be seen from the following considerations. We might try to obtain a superpure case by reversing the order of the steps in the experiment, by RST selecting, say, a position in the x direction, the y direction, with the help of a fast shutter, and only afterwards selecting the momentum with the help of a LTR. This might be thought feasible, for as a result of the position measurement, all sorts of momenta would appear, out of which the LTR without disturbing the position will select only those which happen to fall within some small range. But these considerations would be mistaken. For if a group of particles is selected by an instantaneous shutter, in the way indicated, then Schrödinger's wave packets, obtained by superimposition of waves of various frequencies, give us only probabilities, to be interpreted statistically, of the occurrence of particles in this group which have the given momentum. For any given night range of momenta px, this probability tends towards 2 provided we make the length of the wave train infinitely short, i.e. measure the position with arbitrary precision, by opening the instantaneous shutter for an arbitrarily short time. In the same way, the probability tends towards 0 for any night period during which the instantaneous shutter is open, i.e. for any value of the position range x, provided px tends towards 0. The more exactly we select the position and the momentum, the more improbable it will be that we shall nd any particles at all behind the LTR. But this means that only among a very great number of experiments will there be some in which any particles are found behind the LTR, and this without our being able to predict in advance in which of the experiments particles will be found there. Thus we cannot by any means prevent these particles from appearing only at intervals scattered at random, and consequently we shall not be able to produce in this way an aggregate of particles which is more homogeneous than a pure case. There appears to be a comparatively simple crucial experiment for deciding between the theory of indeterminacy, described above, and the quantum theory. According to the former theory, photons would arrive on a screen behind a highly selective LTR, or spectrograph, even after the extinction of the source of light, for a period of time, and further, this afterglow produced by the LTR would last the longer the more highly selective the LTR was. Appendix 7. Remarks concerning an imaginary experiment, cf. section. We may start from the assumption that A and B are measured, or selected, with an arbitrary degree of precision. In view of the result obtained in Appendix 6, we may assume that the absolute momentum A of the particle arriving at x from the direction px can be measured with an arbitrary degree of precision. Accordingly, B may also be determined as precisely as we choose, by using the principle of conservation of energy. Moreover, the position of SL and x, and the instance of the arrival of the A particles at x, can be measured with arbitrary precision. Thus we need only investigate the situation with respect to the indeterminacies A and B, which arise in consequences of indeterminacies of the corresponding directions, and the vector p connected with the indeterminacy of the position of p, which also arises in consequence of the indeterminacy of a direction, viz. the direction px. If the beam px passes through a slit at x, then a directional indeterminacy phi will occur, in consequence of the direction at the. For a criticism of some of the assumptions underlying section and this appendix, see note to Appendix 6. Slit. This angle phi can be made as small as we like by making A sufficiently large, for we have h phi at Ra, where r is the width of the slit. But it is impossible by this method to decrease A, it would decrease only by increasing r, which would lead to an increase of p, for we have A at phi A, which in view of, leads to h A at r, showing that A does not depend upon A. Owing to the fact that for any chosen r we can make phi as small as we like by increasing A, we can also make the component A in the px direction, which we denote by A, x, as small as we like, and we can do this without interfering with the precision of the measurement of the position of p, since this position too becomes more precise with increasing A, and decreasing r. Now we wish to show that a corresponding argument holds for b, y, i.e. for the pi component of b. Since we may put A equals 0, according to our assumption, we obtain from the conservation of momenta b equals b, A. For any given A, b and A, b depends directly upon phi, which means that we can have an arrangement such that h b at A at r holds, and therefore also Appendix 7.0 h b A at r. Moreover, we obtain, in analogy to b at psi dot b, where psi denotes the indeterminacy of the direction of b, accordingly we obtain in view of, and b, ah, psi at b r b. But this means, however small we make r, we always can make psi and with it, b, y as small as we like by using sufficiently high values for the momentum b, and this, again, without interfering with the precision of the measurement of the position p. This shows that it is possible to make each of the two factors of the product, p, y, b, y as small as we like, independently of the other. But for the refutation of Heisenberg's assertion as to the limits of attainable precision, it would have been sufficient to show that one of these two factors can be made as small as we like without making the other grow beyond all bounds. In addition, it may be noted that by an appropriate choice of the px direction it is possible to determine the distance px in such a way that p and b are parallel, and thus, for sufficiently small phi, normal to pi. In consequence, the precision of the momentum in this direction, and moreover the precision of the position, in the same direction, both become independent of the precision of the measurement of the position of p. The latter, if we use high values of A, depends mainly upon the smallness of r. They are both dependent only upon the precision of the measurements of position and momentum of the particle arriving at x from the direction px, and upon the smallness of psi. This corresponds to the fact that the precision, A, x, of the particle arriving at x depends upon the smallness of phi dot. One sees that with respect to the precision of the measurements, the situation of the apparently non-predictive measurement of the A particle arriving at x and of the prediction of the path of the B particle leaving P are completely symmetrical. Note to new appendices, edition. Although I found, to my surprise, that I could still agree with almost all the philosophical views expressed in the book, and even with most of those on probability ALD in which my ideas have changed more than in any other, I felt that I had to append to it some of the new material accumulated through the years. There was a considerable amount of this, for I never stopped working on the problems raised in the book, and it was therefore not possible to include in these new appendices all my relevant results. I must mention especially one result that is missing here. It is the propensity interpretation of probability, as I call it. The exposition and discussion of this interpretation grew, quite against my intentions, until it became the main part of a new book. The title of this new book is Postscript, After 20 Years. It is a sequel to the present book, and it contains much that is closely related to it, quite apart from probability theory. In this connection I may also refer to two papers of mine which I might have included among these appendices had I not been reluctant to add to them any further. They are Three Views Concerning Human Knowledge, and Philosophy of Science, a Personal Report. The RST2 of my new appendices contain 3 short notes, published between and closely connected with the book. They do not read well, I am afraid, they are unduly compressed, and I was unable to make them more readable without changes that would have diminished their value as documents. Appendices 2 to V are somewhat technical, too much so for my taste, at least. But these technicalities are necessary, it seems to me, in order to solve the following philosophical problem. Is the degree of corroboration or acceptability of a theory of probability, as so many philosophers have thought? Or in other words, does it obey the rules of the probability calculus? I had answered this question in my book, and my answer was, no. To this some philosophers replied, but I mean by probability, or by corroboration, or by confirmation, something different from what you mean. To justify my rejection of this evasive reply, which threatens to reduce the theory of knowledge to mere verbalism, it was necessary to go into technicalities. The rules, axioms, of the probability calculus had to be formulated, and the part played by each of them had to be found. For in order not to prejudge the issue whether or not degree of corroboration is one of the possible interpretations of the calculus of probability, this calculus had to be taken in its widest sense, and only such rules admitted as were essential to it. I began these investigations in, and a brief report of some of my earlier investigations is contained in Appendix 2. An outline of my more recent results is given in Appendices 4 and V. In all these appendices it is asserted that, apart from the classical, the logical, and the frequency interpretations of probability, which were all dealt with in the book, there are many different interpretations of the idea of probability, and of the mathematical calculus of probability. They thus prepare the way for what I have later called the propensity interpretation of probability. Yet I had not only to examine the rules of the probability calculus, I had also to formulate rules for the evaluation of tests, that is, for degree of corroboration. This was done in a series of 3 papers, here reprinted in Appendix 9. Appendices 7 and 8 form a kind of link between my treatment of probability and of corroboration. The remaining appendices will be, I hope, of interest to both philosophers and scientists, especially those on objective disorder, and on imaginary experiments. Appendix 12 consists of a letter from Albert Einstein, here published for the RST time, with the kind permission of his literary executors. Appendix I. 2 notes on induction and demarcation. The RST of the 2 notes here republished is a letter to the editor of Erkenntnis. The second is a contribution to a discussion at a philosophical conference in Prague. It was published in Erkenntnis as part of the report on the conference. The letter to the editor was RST published in Erkenntnis, i.e. Annalen der Philosophie, no. pp. F. I have broken up some of the paragraphs, for easier reading. The letter was evoked by the fact that my views, at the time, were being widely discussed by members of the Vienna Circle, even in print, cf. note, although none of my own manuscripts, which had been read by some members of the Circle, had been published, partly because of their length. My book, Logik der Verstehung, had to be cut to a fraction of its original length, to be acceptable for publication. The emphasis, in my letter, upon the difference between the problem of a criterion of demarcation and the pseudo-problem of a criterion of meaning, and upon the contrast between my views and those of Schlick and Wittgenstein, was provoked by the fact that even in those days my views were discussed, by the Circle, under the misapprehension that I was advocating the replacement of the variability criterion of meaning by a falsiability criterion of meaning, whereas in fact I was not concerned with the problem of meaning, but with the problem of demarcation. As my letter shows, I tried to correct this misinterpretation of my views as early as. I have tried to do the same in my Logic der Forschung, and I have been trying ever since. But it appears that my positivist friends still cannot quite see the difference. These misunderstandings led me, in my letter, to point out, and to dwell upon, the contrast between my views and those of the Vienna Circle, and as a consequence, some people were led to assume, wrongly, that I had developed my views originally as a criticism of Wittgenstein. In fact, I had formulated the problem of demarcation and the falsiability or testability criterion in the autumn of, years before Wittgenstein's views became a topic of discussion in Vienna. Cf. my paper Philosophy of Science, a personal report, now in my Conjectures and Refutations. This explains why, as soon as I heard of the Circle's new variability criterion of meaning, I contrasted this with my falsiability criterion, a criterion of demarcation, designed to demarcate systems of scientific statements from perfectly meaningful systems of metaphysical statements. As to meaningless nonsense, I do not pretend that my criterion is applicable to it. Here is the letter of a criterion of the empirical character of theoretical systems. 1. Preliminary question. Hume's problem of induction. The question of the validity of natural laws arises out of an apparent contradiction between the principle of empiricism, the principle that only experience can decide about the truth or falsity of a factual statement, and Hume's realization that inductive, or generalizing, arguments are invalid. Schlick, enunced by Wittgenstein, believes that this contradiction could be resolved by adopting the assumption that natural laws are not genuine statements but, rather, rules for the transformation of statements, that is to say, that they are a particular kind of pseudo-statement. This attempt to solve the problem, the solution seems to me to be verbal anyway, shares with all the older attempts, such as a priorism, conventionalism, etc. a certain unfounded assumption. It is the assumption that all genuine statements must be, in principle, completely decidable, i.e. variable and falsiable, more precisely, that for all genuine statements, an ultimate, empirical verification, and an ultimate, empirical falsification must both be logically possible. If this assumption is dropped, then it becomes possible to resolve in a simple way the contradiction which constitutes the problem of induction. We can, quite consistently, interpret natural laws or theories as genuine statements which are partially decidable, i.e. which are, for logical reasons, not variable but, in an asymmetrical way, falsifiable only. They are statements which are tested by being submitted to systematic attempts to falsify them. The solution suggested here has the advantage of preparing the way also for a solution of the second and more fundamental of two problems of the theory of knowledge, or of the theory of the empirical method. I have in mind the following. 2. Main problem. This, the problem of demarcation, Kant's problem of the limits of scientific knowledge, may be deemed as the problem of NDing, a criterion by which we can distinguish between assertions, statements, systems of statements, which belong to the empirical sciences, and assertions which may be described as metaphysical. According to a solution proposed by Wittgenstein, this demarcation is to be achieved with the help of the idea of meaning or sense. Every meaningful or senseful proposition must be a truth function of atomic propositions, i.e., it must be logically completely reducible to, or deducible from, singular observation statements. If some alleged statement turns out not to be so reducible, then it is meaningless or nonsensical or metaphysical or a pseudo-proposition. Thus metaphysics is meaningless nonsense. It may appear as if the positivists, by drawing this line of demarcation, had succeeded in annihilating metaphysics more completely than the older anti-metaphysicists. However, it is not only metaphysics which is annihilated by these methods, but natural science as well. For the laws of nature are no more reducible to observation statements than metaphysical utterances. Remember the problem of induction. They would seem, if Wittgenstein's criterion of meaning is applied consistently, to be meaningless pseudo-propositions, and consequently to be metaphysical. Thus this attempt to draw a line of demarcation collapses. The dogma of meaning or sense, and the pseudo-problems to which it has given rise, can be eliminated if we adopt, as our criterion of demarcation, the criterion of falsiability, i.e. of an, at least, unilateral or asymmetrical or one-sided decidability. According to this criterion, statements, or systems of statements, convey information about the empirical world only if they are capable of clashing with experience, or more precisely, only if they can be systematically tested, that is to say, if they can be subjected, in accordance with a methodological decision, to tests which might result in their refutation. In this way, the recognition of unilaterally decidable statements allows us to solve not only the problem of induction. Note that there is only one type of argument which proceeds in an inductive direction, the deductive modus tollens, but also the more fundamental problem of demarcation, a problem which has given rise to almost all the other problems of epistemology. For our criterion of falsiability distinguishes with succinct precision the theoretical systems of the empirical sciences from those of metaphysics, and from conventionalist and tautological systems, without asserting the meaninglessness of metaphysics, which from a historical point of view can be seen to be the source from which the theories of the empirical sciences spring. Varying and generalizing a well-known remark of Einstein's, one might therefore characterize the empirical sciences as follows: insofar as a scientific statement speaks about reality, it must be falsiable, and insofar as it is not falsiable, it does not speak about reality. A logical analysis would show that the role of one-sided falsiability as a criterion for empirical science is formally analogous to that of non-contradictoriness for science in general. A contradictory system fails to single out, from the set of all possible statements, a proper subset. Similarly, a non-falsiable system fails to single out, from the set of all possible empirical statements, of all singular synthetic statements, a proper subset. The second note consists of some remarks which I made in a discussion of a paper read by Reichenbach at a philosophical conference in Prague, in the summer of, when my book was in Page Proofs. A report on the conference was later published in Erkenntnis, and my contribution, here published in translation, was printed in Erkenntnis, p. 0. On the so-called logic of induction and the probability of hypotheses. I do not think that it is possible to produce a satisfactory theory of what is traditionally and also by Reichenbach, for example, called induction. On the contrary, I believe that any such theory, whether it uses classical logic or a probability logic, must, for purely logical reasons, either lead to an innate regress, or operate with an a prioristic principle of induction, a synthetic principle which cannot be empirically tested. If we distinguish, with Reichenbach, between a procedure of NDing and a procedure of justifying a hypothesis, then we have to say that the former, the procedure of ending a hypothesis, cannot be rationally reconstructed. Yet the analysis of the procedure of justifying hypotheses does not, in my opinion, lead us to anything which may be said to belong to an inductive logic. For a theory of induction is superfluous. It has no function in a logic of science. Scientific theories can never be justed, or varied. But in spite of this, a hypothesis A can under certain circumstances achieve more than a hypothesis B, perhaps because B is contradicted by certain results of observations, and therefore falsified by them, whereas A is not falsified, or perhaps because a greater number of predictions can be derived with the help of A than with the help of B. The best we can say of a hypothesis is that up to now it has been able to show its worth, and that it has been more successful than other hypotheses, although, in principle, it can never be justed, varied, or even shown to be probable. This appraisal of the hypothesis relies solely upon deductive consequences, predictions, which may be drawn from the hypothesis. There is no need even to mention induction. The mistake usually made in this field can be explained historically. Science was considered to be a system of knowledge as certain as it could be made. Induction was supposed to guarantee the truth of this knowledge. Later it became clear that absolutely certain truth was not attainable. Thus one tried to get in its stead at least some kind of watered-down certainty or truth, that is to say, probability. But speaking of probability instead of truth does not help us to escape either from the innate regress or from a priorism. From this point of view, one sees that it is useless and misleading to employ the concept of probability in connection with scientific hypotheses. The concept of probability is used in physics and in the theory of games of chance in a finite way which may be satisfactorily deemed. With the help of the concept of relative frequency, following von Mises. Reichenbach's attempts to extend this concept so as to include the so-called inductive probability or the probability of hypotheses are doomed to failure, in my opinion, although I have no objection whatever against the idea of a truth frequency within a sequence of statements which he tries to invoke. For hypotheses cannot be satisfactorily interpreted as sequences of statements, and even if one accepts this interpretation, nothing is gained, one is only led to various utterly unsatisfactory definitions of the probability of a hypothesis. For example, one is led to a definition which attributes the probability instead of 0 to a hypothesis which has been falsified 1,000 times, for this attribution would have to be made if the hypothesis is falsified by every second result of its tests. One might perhaps consider the possibility of interpreting the hypothesis not as a sequence of statements but rather as an element of a sequence of hypotheses, and of attributing to it a certain probability value qua element of such a sequence, though not on the basis of a truth frequency, but rather on the basis of a falsity frequency within that sequence. But this attempt is also quite unsatisfactory. Simple considerations lead to the result that it is impossible in this way to arrive at a probability concept which would satisfy even the very modest demand that a falsifying observation should produce a marked decrease in the probability of the hypothesis. I think that we shall have to get accustomed to the idea that we must not look upon science as a body of knowledge, but rather as a system of hypotheses, that is to say, as a system of guesses or anticipations which in principle cannot be justified, but with which we work as long as they stand up to tests, and of which we are never justified in saying that we know that they are true or more or less certain or even probable. Appendix 2. A note on probability. The following note, a set of independent axioms for probability, was RST published in Mind, NS, p. It is brief, but, unfortunately, it is badly written. It was my RST publication in the English language, moreover, the proofs never reached me. I was then in New Zealand. The introductory text of the note, which alone is here reprinted, clearly states, and I believe for the RST time, that the mathematical theory of probability should be constructed as a formal system, that is to say, a system which should be susceptible of many different interpretations, among them, for example, the classical interpretation, the frequency interpretation, and the logical interpretation, now sometimes called the semantic interpretation. One of the reasons why I wanted to develop a formal theory which would not depend upon any particular choice of an interpretation was that I hoped later to show that what I had called in my book degree of corroboration, or of confirmation or of acceptability, was not a probability, that its properties were incompatible with the formal calculus of probability. Cf. Appendix 9, and my postscript, Sections 2. Another of my motives for writing this note was that I wanted to show that what I had called in my book logical probability was the logical interpretation of an absolute probability, that is to say, of a probability p, x, y, with tautological y. Since a tautology may be written not x and not x, or xx, in the symbols used in my note, we contain the absolute probability of x, for which we may write p, x, or pa, x, in terms of relative probability as follows. P, x, equals p, x, xx, or pa, x, equals p, x, xx, equals p, x, yy. A similar definition is given in my note. When I wrote this note I did not know Kolmogorov's book Foundations of Probability, although it had been RST published in German in Kolmogorov had very similar aims, but his system is less formal than mine, and therefore susceptible to fewer interpretations. The main point of Dierens is this. He interprets the arguments of the probability functor as sets. Accordingly, he assumes that they have members, or elements. No corresponding assumption was made in my system. In my theory, nothing whatever is assumed concerning these arguments, which I call elements, except that their probabilities behave in the manner required by the axioms. Kolmogorov's system can be taken, however, as one of the interpretations of mine. See also my remarks on this topic in Appendix 4. The actual axiom system at the end of my note is somewhat clumsy, and very shortly after its publication I replaced it by a simpler and more elegant one. Both systems, the old and the new, were formulated in terms of product, or conjunction, and complement, negation, as were also my later systems. At that time, I had not succeeded in deriving the distributive law from simpler ones, such as A to A and B below, and I therefore stated it as an axiom. But, written in terms of product and complement, the distributive law is very clumsy. I have therefore here omitted the end of the note, with the old axiom system. Instead I will restate here my simpler system, cf. British Journal Philosophy SC, LOCCIT, based, like the old system, on absolute probability. It is, of course, derivable from the system based on relative probability given in Appendix 4. I am stating the system here in an order corresponding to that of my old note. AP, XY, P, X, commutation. AP, XY, Z, P, XYZ, association. AP, XX, P, X. Tautology. A. There are at least one X and one Y such that P, X, superscript 1 P, Y. Existence. BP, X, P, XY, monotony. BP, X, equals P, XY, plus P, XY. Complement, B. For every X there is a Y such that P, Y, P, X, and P, XY, equals P, X, P, Y. Independence. Here follows my old note of, with a few slight stylistic corrections. A set of independent axioms for probability. From the formal point of view of axiomatics, probability can be described as a two-termed functor, i.e., a numerical function of two arguments which themselves need not have numerical values, whose arguments are variable or constant names, which can be interpreted, e.g., as names of predicates or as names of statements according to the interpretation chosen. If we desire to accept for both of the arguments the same rules of substitution and the same interpretation, then this functor can be denoted by P, X, X, which can be read as the probability of X with regard to X. It is desirable to construct a system of axioms, S, in which P, X, X, appears as undefined, primitive functors and which is constructed in such a way that it can be equally well interpreted by any of the proposed interpretations. The three interpretations which have been most widely discussed are, the classical definition of probability as the ratio of the favorable to the equally possible cases, the frequency theory which defines probability as the relative frequency of a certain class of occurrences within a certain other class, and the logical theory which defines probability as the degree of a logical relation between statements, which equals if X is a logical consequence of X, and which equals 0 if the negation of X is a logical consequence of X. In constructing such a system S, capable of being interpreted by any of the interpretations mentioned, and by some others too, it is advisable to introduce, with the help of a special group of axioms, see below, Group A, certain undefined functions of the arguments, e.g., the conjunction, X and X, symbolized here by XX, and the negation, non-X, symbolized by X. Thus we can express symbolically an idea like X and not X with the help of XX, and its negation by XX. If, i.e., the logical interpretation, is adopted, XX is to be interpreted as the name of the statement, which is the conjunction of the statement named X and its negation. Supposing the rules of substitution are suitably formulated, it can be proved for any X, X, and X. P, X, XX, equals P, X, XX. Thus the value of P, X, XX, depends on the one real variable X only. This justifies the following explicit definition of a new one-termed functor pa, X, which I may call absolute probability. df pa, X, equals P, X, XX. An example of an interpretation of pa, X, in the sense of, i.e. of the logical interpretation, is the concept logical probability as used by me in a previous publication. Now it is possible to proceed with the whole construction from the other end, instead of introducing P, X, X, as primitive concept, primitive functor, of an axiom system S and dening pa, X, explicitly, we can construct another axiom system S in which pa, X, appears as, undefined, primitive variable, and we can then proceed to define pa, XX, explicitly, with the help of pa, X, as follows. dfp, X, X, equals pa, XX. Pa, X. The formulae adopted in S as axioms, and df, now become theorems within S, i.e. they can be deduced with the help of the new system of axioms S. It can be shown that the two methods described, the choice of S and df, or S and df respectively, are not equally convenient from the viewpoint of formal axiomatics. The second method is superior to the RST in certain respects, the most important of which is that it is possible to formulate in S an axiom of uniqueness which is much stronger than the corresponding axiom of S, if the generality of S is not restricted. This is due to the fact that if pa, X, equals 0, the value of P, X, X, becomes indeterminate. A system of independent axioms, S, as described above, is here subjoined. It is easy to construct a system S with the help of it. Combined with definition df, it is sufficient for the deduction of the mathematical theory of probability. The axioms can be divided into two groups. Group A is formed by the axioms for the junctional operations, conjunction and negation of the argument, and is practically an adaptation of the system of postulates for the so-called algebra of logic. Group B gives the axioms peculiar to the measurement of probability. The axioms are here followed with several misprints the complicated axiom system, which I have since replaced by the simpler one given above. Christchurch, NZ, November 0th. Appendix 3. On the heuristic use of the classical definition of probability, especially for deriving the general multiplication theorem. The classical definition of probability as the number of favorable cases divided by the number of equally possible cases has considerable heuristic value. Its main drawback is that it is applicable to homogeneous or symmetrical dice, say, but not to biased dice, or in other words, that it does not make room for unequal weights of the possible cases. But in some special cases there are ways and means of getting over this difficulty, and it is in these cases that the old definition has its heuristic value. Every satisfactory definition will have to agree with the old definition where the difficulty of assigning weights can be overcome, and therefore, a fortiori, in those cases in which the old definition turns out to be applicable. 1. The classical definition will be applicable in all cases in which we conjecture that we are faced with equal weights, or equal possibilities, and therefore with equal probabilities. 2. It will be applicable in all cases in which we can transform our problem so as to obtain equal weights or possibilities or probabilities. 3. It will be applicable, with slight modifications, whenever we can assign a weight function to the various possibilities. 4. It will be applicable, or it will be of heuristic value, in most cases where an oversimplified estimate that works with equal possibilities leads to a solution approaching to the probabilities 0 or 1. 5. It will be of great heuristic value in cases in which weights can be introduced in the form of probabilities. Take, for example, The following simple problem, we are to calculate the probability of throwing with a die an even number when the throws of the number 6 are not counted, but considered as no throw. The classical definition leads, of course, to slash. We may now assume that the die is biased, and that the unequal probabilities p of its sides are given. We can then still calculate the required probability as equal to p plus p equals p plus p plus p plus p plus p plus p p. That is to say, we can modify the classical definition so as to yield the following simple rule. Given the probabilities of all the mutually exclusive possible cases, the required probability is the sum of the probabilities of all the mutually exclusive favorable cases, divided by the sum of the probabilities of all the mutually exclusive possible cases. It is clear that we can also express this rule, for exclusive or non-exclusive cases, as follows. The required probability is always equal to the probability of the disjunction of all the exclusive or non-exclusive favorable cases, divided by the probability of the disjunction of all the exclusive or non-exclusive possible cases. 6. These rules can be used for a heuristic derivation of the definition of relative probability, and of the general multiplication theorem. For let us symbolize, in the last example, even by A and other than a 6 by B. Then our problem of determining the probability of an even throw if we disregard throws of a 6 is clearly the same as the problem of determining P, A, B, that is to say, the probability of A, given B, or the probability of ending in A among the B's. The calculation can then proceed as follows. Instead of writing P plus P, we can write, more generally, P, ab, that is to say, the probability of an even throw other than a 6. And instead of writing P plus P, plus P, or, what amounts to the same, P, we can write P, B, that is to say, the probability of throwing a number other than 6. It is clear that these calculations are quite general, and assuming P, B, superscript 10, we are led to the formula. Or to the formula, more general because it remains meaningful even if P, B, equals 0. P, ab, equals P, A, B, P, B. This is the general multiplication theorem for the absolute probability of a product of. By substituting BC for B, we obtain from P, ABC, equals P, A, BC, P, BC, and therefore, by applying, to P, BC, P, ABC, equals P, A, BC, P, B, C, P, C. Or, assuming P, C, superscript 10, P, ABC, slash P, C, equals P, A, BC, P, B, C. This, in view of, is the same as P, ab, C, equals P, A, BC, P, B, C. This is the general multiplication theorem for the relative probability of a product of. The derivation here sketched can be easily formalized. The formalized proof will have to proceed from an axiom system rather than from a definition. This is a consequence of the fact that our heuristic use of the classical definition consisted in introducing weighted possibilities, which is practically the same as probabilities, into what was the classical definitions. The result of this modification cannot any longer be regarded as a proper definition, rather it must establish relations between various probabilities, and it therefore amounts to the construction of an axiom system. If we wish to formalize our derivation, which makes implicit use of the laws of association and of the addition of probabilities, then we must introduce rules for these operations into our axiom system. An example is our axiom system for absolute probabilities, as described in Appendix 2. If we thus formalize our derivation of, we can get, at best only with the condition provided P, C, superscript 10, as will be clear from our heuristic derivation. But, may be meaningful even without this proviso, if we can construct an axiom system in which P, A, B, is generally meaningful, even if P, B, equals 0. It is clear that we cannot, in a theory of this kind, derive, in the way here sketched, but we may instead adopt, itself as an axiom, and take the present derivation, see also formula, of my old Appendix 2, as a heuristic justification for introducing this axiom. This has been done in the system described in the next appendix, Appendix 4. Appendix 4. The formal theory of probability. In view of the fact that a probability statement such as P, A, B, equals R can be interpreted in many ways, it appeared to me desirable to construct a purely formal or abstract or autonomous system, in the sense that its elements, represented by A, B, can be interpreted in many ways, so that we are not bound to any particular one of these interpretations. I proposed RST a formal axiom system of this kind in a note in mind here reprinted in Appendix 2. Since then, I have constructed many simplified systems. There are three main characteristics which distinguish a theory of this kind from others. It is formal, that is to say, it does not assume any particular interpretation, although allowing for at least all known interpretations. 2. It is autonomous, that is to say, it adheres to the principle that probability conclusions can be derived only from probability premises, in other words, to the principle that the calculus of probabilities is a method of transforming probabilities into other probabilities. 3. It is symmetrical, that is to say, it is so constructed that whenever there is a probability P, B, A, i.e. a probability of B given A, then there is always a probability P, A, B, also even when the absolute probability of B, P, B, equals 0, that is, even when P, B, equals P, B, A, equals 0. Apart from my own attempts in this ELD, a theory of this kind, strange to say, does not seem to have existed hitherto. Some other authors have intended to construct an abstract or formal theory, for example Kolmogorov, but in their constructions they have always assumed a more or less specific interpretation. For example, they assumed that in an equation like P, A, B, equals R, the elements A and B are statements, or systems of statements, or they assumed that A and B are sets, or systems of sets, or perhaps properties, or perhaps night classes, ensembles, of things. Kolmogorov writes, the theory of probability, as a mathematical discipline, can and should be developed from axioms in exactly the same way as geometry and algebra, and he refers to the introduction of basic geometric concepts in the Foundations of Geometry by Hilbert, and to similar abstract systems. And yet, he assumes that, in P, A, B, I am using my own symbols, not his A and B are sets, thereby excluding, among others, the logical interpretation according to which A and B are statements, or propositions, if you like. He says, rightly, what the members of the set represent is of no importance, but this remark is not sufficient to establish the formal character of the theory at which he aims, for in some interpretations, A and B have no members, nor anything that might correspond to members. All this has grave consequences in connection with the actual construction of the axiom system itself. Those who interpret the elements A and B as statements or propositions very naturally assume that the calculus of statement composition, the propositional calculus, holds for these elements. Similarly, Kolmogorov assumes that the operations of addition, multiplication, and complementation of sets hold for his elements, since they are interpreted as sets. More concretely, it is always presupposed, often only tacitly, that such algebraic laws as the law of association, A, or the law of commutation, B, or the law of idempotence, C, AB, C equals A, BC, AB equals BA, A equals AA, hold for the elements of the system, that is to say, for the arguments of the function P. Having made this assumption either tacitly or explicitly, a number of axioms or postulates are laid down for relative probability. P, A, B. That is to say, for the probability of A, given the information B, or else for absolute probability P, A. That is to say, for the probability of A, given no information, or only tautological information. But this procedure is apt to veil the surprising and highly important fact that some of the adopted axioms or postulates for relative probability, P, A, B, alone guarantee that all the laws of Boolean algebra hold for the elements. For example, a form of the law of association is entailed by the following two formulae, cf. the preceding Appendix 3. D, P, AB, equals P, A, B, P, B. E, P, AB, C, equals P, A, B, C, P, B, C. Of which the RST, D, also gives rise to a kind of definition of relative probability in terms of absolute probability. Descent, if P, B, superscript 10 then P, A, B, equals P, AB, slash P, B. While the second, the corresponding formula for relative probabilities, is well known as the general law of multiplication. These two formulae, D, and E, entail, without any further assumption, except substitutivity of equal probabilities, the following form of the law of association. F, P, AB, C, equals P, A, B, C. But this interesting fact remains unnoticed if, F, is introduced by way of assuming the algebraic identity, A, the law of association before even starting to develop the calculus of probability, for from A, AB, C equals A, B, C. We may obtain, F, merely by substitution into the identity. P, X, equals P, X. Thus the derivability of, F, from, D, and, E, remains unnoticed. Or in other words, it is not seen that the assumption, A, is completely redundant if we operate with an axiom system which contains, or implies, D, and, E, and that by assuming, A, in addition to, D, and, E, we prevent ourselves from ending out what kind of relations are implied by our axioms or postulates. But to end this out is one of the main points of the axiomatic method. In consequence, it has also not been noticed that, D, and, E, although implying, F, i.e. an equation in terms of absolute probability, do not alone imply, G, and, H, which are the corresponding formulae in terms of relative probability. G, P, AB, C, D, equals P, A, B, C, D. H, P, A, B, C, D, equals P, A, B, C, D. In order to derive these formulae, see Appendix V, 2, much more is needed than, D, and, E, a fact which is of considerable interest from an axiomatic point of view. I have given this example in order to show that Kolmogorov fails to carry out his program. The same holds for all other systems known to me. In my own systems of postulates for probability, all theorems of Boolean algebra can be deduced, and Boolean algebra, in its turn, can of course be interpreted in many ways, as an algebra of sets, or of predicates, or of statements, or propositions, etc. Another point of considerable importance is the problem of a symmetrical system. As mentioned above, it is possible to define relative probability in terms of absolute probability by descent, as follows. Descent, if P, B, superscript 10 then P, A, B, equals P, AB, slash P, B. Now the antecedent if P, B, superscript 10 is unavoidable here since division by 0 is not a defined operation. As a consequence, most formulae of relative probability can be asserted, in the customary systems, only in conditional form, analogous to descent. For example, in most systems, G is invalid, and should be replaced by the much weaker conditional formula, G. G if P, D, superscript 10 then P, AB, C, D, equals P, A, B, C, D. And an analogous condition should be prex to H. This point has been overlooked by some authors, for example, Juries and von Wright. The latter uses conditions amounting to B superscript 10, but this does not ensure P, B, superscript 10, especially since his system contains an axiom of continuity. Their systems, accordingly, are inconsistent as they stand, although they can sometimes be mended. Other authors have seen the point. But as a consequence, their systems are, at least as compared with my system, very weak. It can occur in their systems that P, A, B, equals R is a meaningful formula, while at the same time, and for the same elements, P, B, A, equals R is not meaningful, i.e. not properly deaned, and not even deanable, because P, A, equals 0. But a system of this kind is not only weak, it is also for many interesting purposes inadequate. It cannot, for example, be properly applied to statements whose absolute probability is 0, although this application is very important. Universal laws, for example, have, we may here assume, cf. Appendices 7 and 8, 0 probability. If we take two universal theories, S and T, say, such that S is deducible from T, then we should like to assert that P, S, T, equals. But if P, T, equals 0, we are prevented from doing so, in the customary systems of probability. For similar reasons, the expression P, E, T, where E is evidence in favor of the theory T, may be undeaned, but this expression is very important. It is Fisher's likelihood of T on the given evidence E, see also Appendix 9. Thus there is a need for a probability calculus in which we may operate with second arguments of 0 absolute probability. It is, for example, indispensable for any serious discussion of the theory of corroboration or confirmation. This is why I have tried for some years to construct a calculus of relative probability in which, whenever P, A, B, equals R, is a well-formed formula, i.e. true or false. P, B, A, equals R is also a well-formed formula, even if P, A, equals 0. A system of this kind may be labeled symmetrical. I published the RST system of this kind only in. This symmetrical system turned out to be much simpler than I expected. But at that time, I was still preoccupied with the peculiarities which every system of this kind must exhibit. I am alluding to such facts as these: in every satisfactory symmetrical system, rules such as the following are valid. P, A, B, B, equals. If P, B, B, superscript 10, then P, A, B, equals. If P, A, B, superscript 10, then P, A, B, equals. These formulae are either invalid in the customary systems, or else, the second and third, vacuously satisfied, since they involve second arguments with 0 absolute probabilities. I therefore believed, at that time, that some of them would have to appear in my axioms. But I found later that my axiom system could be simplified, and in simplifying it, I found that all these unusual formulae could be derived from formulae having a completely normal look. I published the resulting simplified system RST in my paper Philosophy of Science, a personal report. It is the same system of 6 axioms which is more fully presented in the present appendix. The system is surprisingly simple and intuitive, and its power, which far surpasses that of any of the customary systems, is merely due to the fact that I omit from all the formulae except one, axiom C, any condition like if P, B, superscript 10, then. In the customary systems, these conditions either are present, or they ought to be present, in order to avoid inconsistencies. I intend to explain, in the present appendix, RST the axiom system, with proofs of consistency and independence, and afterwards a few definitions based upon the system, among them that of a Borel-Eld of probabilities. First, the axiom system itself. Four undefined concepts appear in our postulates: I, S, the universe of discourse, or the system of admissible elements. The elements of S are denoted by lowercase italics, A, B, C, etc. 2, a binary numerical function of these elements, denoted by P, A, B, etc., that is to say, the probability a given B. 3, a binary operation on the elements, denoted by a B, and called the product, or meet or conjunction, of A and B. 4, the complement of the element A, denoted by A. To these four undefined concepts we may add a FTH1 that can be treated, according to choice, as an undefined or as a defined concept. It is the absolute probability of A, denoted by P, A. Each of the undefined concepts is introduced by a postulate. For an intuitive understanding of these postulates, it is advisable to keep in mind that P, A, equals P, B, B, for all elements A and B of S, as can of course be formally proved with the help of the postulates. Postulate. The number of elements in S is at most enumerably infinite. Postulate. If A and B are in S, then P, A, B, is a real number, and the following axioms hold. A. There are elements C and D in S such that P, A, B, superscript 1 P, C, D. Existence, A. If P, A, C, equals P, B, C, for every C in S, then P, D, A, equals P, D, B, for every D in S. Substitutivity. AP, A, equals P, B, B, reexivity. Postulate. If A and B are in S, then AB is in S, and if, moreover, C is in S, and therefore also BC, then the following axioms hold. BP, AB, C, P, A, C, monotony. BP, AB, C, equals P, A, BC, P, B, C, multiplication. Postulate. If A is in S, then A is in S, and if, moreover, B is in S, then the following axiom holds. CP, A, B, plus P, A, B, equals P, B, B, unless P, B, B, equals P, C, B, for every C. In S, complementation. This concludes the elementary system, elementary as opposed to its extension to Borel-Eldes. We may, as indicated, add here the definition of absolute probability as a FTH postulate, called postulate AP. Alternatively, we may regard this as an explicit definition rather than as a postulate. Postulate AP. If A and B are in S, and if P, B, C, P, C, B, for every C in S, then P, A, equals P, A, B, definition of absolute probability. The system of postulates and axioms given here will be shown below to be consistent and independent. The following comments may be made upon this system of postulates. The six axioms A, B, B, and B are explicitly used in the actual operations of deriving the theorems. The remaining, existential, parts of the postulates can be taken for granted, as in the paper in which IRST published this system of axioms. Cf. note, above. At the price of introducing a fourth variable, D, in postulates and, these six axioms may be replaced by a system of only four axioms, consisting of A, and the following two. B and if P, A, B, C, P, B, C, superscript 1 P, D, C, provided that P, A, C, P, D, C, then P, AB, C, superscript 1 P, D, C. C plus if P, A, B, plus P, A, B, superscript 1 P, C, C, then P, C, C, equals P, D, B. In this system, B and is equivalent to the conjunction of B and B, and C plus, similarly, to that of A and C. The resulting system of 4 axioms is very brief, and shares many of the advantages of the longer system. Product and complement occur separately, so that all the axioms except those lettered B are free of the product, and the complement occurs once only. But personally I prefer the longer system of 6 axioms. The following comments may be made upon the various postulates and axioms of the system. Postulate, which only belongs to the elementary theory, may be dispensed with. This is shown by the fact that, in order to prove its independence, we may construct a system S which is non-denumerable. All other postulates are satisfied if we interpret S as the set of all night sums of half-open subintervals x, y, of the unit interval 0, where x and y are real numbers rather than rational numbers. We may then interpret p, a, as the length of these intervals, and p, a, b, as equal to p, a, slash p, b, provided p, b, superscript 1 0, and as equal to provided b equals 0, or else as lim p, a, slash p, b, provided this limit exists. The function of postulate is merely to characterize the elementary systems. A postulate of this kind is often assumed in an axiomatic treatment of Boolean algebra or the logic of statements or propositions, and we wish to be able to show that, in the elementary theory, S is a denumerable Boolean algebra. For another example, see Appendix 6, point. In postulate, A is needed to establish that not all probabilities are equal, say, equal to 0 or equal to. The function of A is to allow us to prove P, x, A, equals P, x, B, for all elements A and B whose probabilities, given any condition C, are equal. This can be done without A, but only under the assumption P, A, superscript 1 0 superscript 1 P, B. Thus A is to enable us to extend the probabilistic equivalence of A and B to the second argument even in those cases in which A and B have 0 absolute probability. A may be replaced by the following stronger formula. A plus if P, A, equals P, B, C, equals P, C, B, then P, A, B, equals P, A, C. Or by either of the formulae, the weaker of which is B. B. If P, A, C, equals P, B, A, C, then P, C, A, equals P, C, B, A. If P, A, C, equals P, A, C, then P, B, A, C, A, equals P, B, A, C. Obviously, it can therefore also be replaced by the formula, which is simpler but much stronger. B plus P, A, B C, equals P, A, C B. But since B plus is stronger than necessary in fact, P, A, B C, C B, equals P, A, C B, B C, though weaker, would sus it is a little misleading. Its adoption would veil the fact that with the help of the other axioms alone, the law of commutation can be proved for the RST argument. A and is preferable to the other formulae here mentioned in so far as it avoids, like the much weaker A, using the product of A and B. However, we can make use of the facts here stated in order to reduce the number of our axioms to 3, viz. A, C plus, and the following axiom B which combines B and with B plus. B if P, A, C, superscript 1 P, A, D, P, B, C, provided that P, A, C, P, A, D, P, B, C, and P, A, D, equals P, A, B, C, then P, A, C, B, superscript 1 P, A, D. Apart from being stronger than one might wish it to be, this system of only 3 axioms has all the advantages of the system of 4 axioms A, B plus, and C plus. A is needed to prove that P, A, equals, for every element of S, as has been indicated. But it may be omitted if we strengthen C, as may be seen from axiom C plus. A becomes redundant if we replace in C the 2 occurrences of P, B, by P, D, or only the second occurrence. Postulate demands the existence of a product, or meet, or intersection, of any elements A and B in S. It characterizes exhaustively all the properties of the product, such as idempotence, commutation, and association, by two simple axioms of which the RST is intuitively obvious. The second has been discussed in Appendix 3. Axiom B is, in my opinion, the intuitively most obvious of all our axioms. It is preferable to both A cent and B cent, cf note above, which together may replace it. For A cent may be mistaken for a convention, as opposed to B, and B cent does not, as does B, characterize an intuitive metrical aspect of probability, but rather the product or conjunction of. As shown by formula B above, axiom B can be combined with B and A+. There are other possible combinations, among them some in which the product appears only once. They are very complicated, but have the advantage that they may be given a form analogous to that of a denition. One such denitional form may be obtained from the following axiom BD, which, like B, may replace A, B, and B, by inserting the symbol, A, twice, once at the beginning and a second time before, EB, and by replacing the RST arrow, conditional, by a double arrow, for the biconditional. I am using here the abbreviations explained in the beginning of Appendix V. BDP, XY, A, equals P, Z, A, registered trademark, EB, C, D, E, F, EG, P, X, A, P, Z, A, equals P, X, B, P, Y, A, and P, A, C, P, B, C, P, Y, C, and P, A, E, P, C, E. P, Y, E, registered trademark P, C, D, P, B, D, and P, A, F, equals P, Y, F, registered trademark P, X, A, equals P, X, B, equals P, X, Y, and P, X, G, P, C, G, P, Y, G, registered trademark P, C, A, P, Z, A. Postulate demands the existence of a complement, A, for every A in S, and it characterizes this complement by a weakened conditional form of what appears to be an obvious formula, P, A, C, plus P, A, C, equals, considering that equals P, A, A. The condition which precedes this formula is needed, because in case C is, say AA, the empty element, AA equals 0, we obtain P, A, C, equals P, A, C, so that, in this limiting case, the apparently obvious formula breaks down. This postulate, or the axiom C, has the character of a denition of P, A, B, in terms of P, A, B, and P, A, A, as can be easily seen if we write C as follows. Note that, 2, follows from, I, dot. I, P, A, B, equals P, A, P, A, B, provided there is a C such that P, C, B, superscript 1. P, A, 2, P, A, B, equals P, A, provided there is no such C. A formula CD analogous to an improved version of BD will be found in an addendum on P. The system consisting of A, BD, and CD is, I think, slightly preferable to A, B, and C+, in spite of the complexity of BD. Postulate AP, ultimately, can be replaced by the simple denition. Dot. P, A, equals P, A, which, however, uses complementation and the product, and accordingly presupposes both postulates and formula, dot, will be derived below in Appendix V as formula. Our axiom system can be proved to be consistent. We may construct systems of elements S, with an inite number of diarent elements, for a nite S, the proof is trivial, and a function p, a, b, such that all the axioms are demonstrably satisfied. Our system of axioms may also be proved to be independent. Owing to the weakness of the axioms, these proofs are quite easy. A trivial RST consistency proof for a night S is obtained by assuming that S equals 0, that is to say, that S consists of the two elements, and 0, product or meet and complement are taken to be equal to arithmetical product and complement, with respect to we deem P, 0, equals 0, and in all other cases put P, A, B, equals. Then all the axioms are satisfied. Two further night interpretations of S will be given before proceeding to a denumerably innate interpretation. Both of these satisfy not only our axiom system but also, for example, the following existential assertion, E. There are elements A, B, and C in S such that P, A, B, equals and P, A, B, C, equals 0. A similar assertion would be E cent. There is an element in S such that P, A, equals P, A, equals P, A, equals 0 superscript 1 P, A, equals. This assertion, E, is not satisfied by our RST example, nor can it be satisfied in any system of probability known to me, except, of course, some of my own systems. The RST example satisfying our system and, E, consists of 4 elements. S equals 0. Here A is deemed as the smaller of the two numbers A and B, except that equals 0. We deem A equals A, and P, A, equals P, A, equals 0 whenever A equals 0 or, and P, A, equals P, A, equals whenever A equals or, P, A, 0, equals, P, A, equals 0 unless A equals or A equals, in which case P, A, equals. In the remaining cases P, A, B, equals P, AB, slash P, B. Intuitively, the element may be identified with a universal law of zero absolute probability, and with its existential negation. In order to satisfy E, we take A equals, B equals, and C equals. The example just described may be represented by way of the following two matrices. This method, I believe, was RST introduced by Huntington in 0. The second example is a generalization of the RST, showing that the idea underlying the RST example can be extended to a number of elements exceeding any chosen number, provided these elements form a Boolean algebra, which means that the number of elements has to be equal to n. Here n may be taken to be the number of the smallest exclusive areas or classes into which some universe of discourse is divided. We can freely correlate with each of these classes some positive fraction, 0r, as its absolute probability, taking care that their sum equals. With any of the Boolean sums, we correlate the arithmetical sum of their probabilities, and with any Boolean complement, the arithmetical complement with respect to. We may assign to one or several of the smallest, non-zero, exclusive areas or classes the probability 0. If B is such an area or class, we put P, A, B, equals 0 in case of equals 0, otherwise P, A, B, equals. We also put P, A, 0, equals, and in all other cases, we put P, A, B, equals P, AB, slash P, B. In order to show that our system is consistent even under the assumption that S is denumerably innate, the following interpretation may be chosen. It is of interest because of its connection with the frequency interpretation. Let S be the class of rational fractions in dyadic representation, so that, if A is an element of S, we may write A as a sequence, A equals A, where AI is either 0 or. We interpret AB as the sequence of equals AB, so that, AB, I equals AB and A as the sequence A equals, A, so that AI equals, AI. In order to deem P, A, B, we introduce an auxiliary expression, N, deemed as follows. N equals sigma ai. N. So that we have ab, N equals sigma ab. N. Moreover, we deem an auxiliary function, q. Q, n, bn, equals whenever bn equals 0. Q, n, bn, equals, ab, n slash bn, whenever bn superscript 1 0. Now we can deem p, a, b, equals lim q, n, bn. This limit exists for all elements a and b of S, and it can be easily shown to satisfy all our axioms. See also Appendix 6, points 2. So much about the consistency of our axiom systems. In order to show the independence of A, we may take P, A, B, equals 0 for every A and B in S. Then all the axioms except A are satisfied. In order to show the independence of A WE0, take S to consist of 3 elements, S equals 0. We can easily show that the product of must be non-commutative. It may be deemed as follows. Equals, and in all other cases, including, of is equal to min, A, B, i.e. to the smallest of its 2 components A and B. We also deem, A equals if and only if A equals 0, otherwise A equals 0, and we deem P, 0, equals 0, in all other cases, P, A, B, equals. It is now easy to show that for every B, P, B, equals P, B, while P, 0, equals and P, 0, equals 0. Thus A is not satisfied. But all the other axioms are. We can illustrate this interpretation by writing the non-commutative matrix as follows. P, 0, equals 0. In all other cases, P, A, B, equals. In order to show that A is independent, we take, as in our trivial RST consistency proof, S equals 0, with logical products and complements equal to the arithmetical ones. We deem P, equals, and in all other cases P, A, B, equals 0. Then P, superscript 1 P, 0, 0, so that A fails. The other axioms are satisfied. In order to show that B is independent, we take S equals 0, plus, we take up to be the arithmetical product of A and B, A equals A, and P, A, B, equals A, B. Then all axioms are satisfied except B, which fails for A equals B superscript 1 plus, and C equals 0. The matrices may be written. This example also proves the independence of A cent, cf. Note, above. A second example, proving the independence of B and also of B cent, is based upon the following non-commutative matrix. P, 0, equals 0. In all other cases, P, A, B, equals. B fails for A equals 0, B equals, and C equals. In order to show that B is independent, we take the same S as for A, and deem P, 0, equals 0, in all other cases, P, A, B, equals. B fails because equals P, dot, superscript 1 P, P, equals, but all other axioms are satisfied. Another example showing the independence of B can be obtained. If we consider that B is needed to prove P, B A, C, P, A, C, that is to say, the dual of B. This suggests that we may use the second example for B, changing only the value of point 0 from 0 to, and that of 0 from to 0. Everything else may be left unchanged. B fails for A equals, B equals 0, and C equals. Ultimately, for showing that C is independent, we take again the same S, but assume that A equals A. If we now take P, 0, equals 0 and in all other cases P, A, B, equals, then C fails, because P, 0, superscript 1 P. The other axioms are satisfied. This concludes the proofs of the independence of the operational axioms. As to the non-operational parts of the postulates, a proof of the independence of postulate has been given above, when I commented upon this postulate. Postulate requires, in its non-operational part, that whenever A and B are in S, P, A, B, is a real number. In order to show the independence of this requirement, which we may refer to as postulate, we are consider a non-numerical Boolean interpretation of S. To this end, we interpret S as an at most enumerable and non-numerical Boolean algebra, such as a set of statements, so that A, B, etc. are variable names of statements. And we stipulate that X is to denote, if X is a number, the same as X, and if X is a Boolean element, say, a statement, then X is to denote the Boolean complement, negation, of X. Similarly, we stipulate that xy, x plus y, x equals y, x superscript 1y, and xy, have their usual arithmetical meaning if x and y are numbers, and their well-known Boolean meanings whenever x and y are Boolean elements. If x and y are statements, xy should be interpreted as x entails y. In order to prove the independence of postulate, we now merely add one more stipulation. We interpret P, A, B, as synonymous with A plus B in the Boolean sense. Then postulate breaks down while A, and all the other axioms and postulates turn into well-known theorems of Boolean algebra. The proofs of the independence of the existential parts of postulates and are almost trivial. We are introduce an auxiliary system. S-cent equals 0, and in product, complement, and absolute probability by the matrix. Relative probability is deemed by P, A, B, equals 0 whenever P, A, superscript 1 equals P, B, P, A, B, equals in all other cases. This system S-cent satisfies all our axioms and postulates. In order to show the independence of the existential part of postulate, we now take S to be con to the elements n of S-cent, leaving everything else unchanged. Obviously, postulate fails, because the product of the elements n is not in S, everything else remains valid. Similarly, we can show the independence of postulate by conning S to the elements 0 and of S-cent. We may also choose and, or any combination consisting of 3 of the 4 elements of S-cent except the combination consisting of, and. The proof of the independence of postulate AP is even more trivial. We only need to interpret S and P, A, B, in the sense of our RST consistency proof and take P, A, equals constant, a constant such as 0, or slash, or. In order to obtain an interpretation in which postulate AP fails. Thus we have shown that every single assertion made in our axiom system is independent. To my knowledge, no proofs of independence for axiom systems of probability have been published before. The reason, I suppose, is that the known systems, provided they are otherwise satisfactory, are not independent. The redundancy of the usual systems is due to the fact that they all postulate, implicitly or explicitly, the validity of some or all of the rules of Boolean algebra for the elements of S, but as we shall prove at the end of Appendix V, these rules are all derivable from our system if we deem Boolean equivalence, A equals B, by the formula A equals B if, and only if, P, A, C, equals P, B, C, for every C in S. The question may be asked whether any axioms of our system become redundant if we postulate that of is a Boolean product and A Boolean complement, that they both obey all the laws of Boolean algebra, and that is valid. The answer is, none of the axioms, except B-cent, becomes redundant. Only if we were to postulate, in addition, that any two elements for which Boolean equivalence can be proved may be substituted for each other in the second argument of the P function, then one of our axioms would become redundant, i.e. our axiom of substitutive ity, A, which serves precisely the same purpose as this additional postulate. That our axioms remain non-redundant can be seen from the fact that their independence, except that of A, of course, and B-cent, can be proved with the help of examples that satisfy Boolean algebra. I have given such examples for all except B and C, for which simpler examples have been given. An example of a Boolean algebra that shows the independence of B, and A cent, and of C is this. 0 and are the Boolean 0 and universal elements, and A equals A. The example is, essentially, the same as the last one, but with the probabilities, and attached to the elements other than 0 or B, and A cent. P, A, equals A, P, A, 0, equals, in all other cases. P, A, B, equals P, ab, slash P, B, equals ab slash B. C, P, A, B, equals 0 if ab equals 0 superscript 1b. In all other cases, P, A, B, equals. B is violated because equals P, dot, P, equals. C is violated because P, plus P, equals, though P, 0, superscript 1p, the fact that our system remains independent even if we postulate Boolean algebra and, may be expressed by saying that our system is autonomously independent. If we replace our axiom B by A cent and B cent, see note above, then our system ceases, of course, to be autonomously independent. Autonomous independence seems to me an interesting, and desirable, property of axiom systems for the calculus of probability. In conclusion, I wish to give a definition, in the autonomous i.e. probabilistic terms of our theory, of an admissible system S, and of a Borel-Eld of probabilities S. The latter term is Kolmogorov's, but I am using it in a sense slightly wider than his. I will discuss the difference between Kolmogorov's treatment of the subject and mine in some detail because it seems to me illuminating. IRST in probabilistic terms, what I mean by saying that A is a superelement of B, and wider than, or equal to, B, or that B is a sub-element of A, and logically stronger than, or equal to, A. The definition is as follows. See also the end of Appendix V. A is a superelement of B, or B is a sub-element of A in symbols. A B if, and only if, P, A, X, P, B, X, for every X in S. Next I define what I mean by the product element of an inite sequence, A equals A, all of whose members in are elements of S. Let some O or perhaps all elements of S be ordered in an inite sequence A equals A, such that any element of S is permitted to recur in the sequence. For example, let S consist only of the two elements, 0 and, then A equals 0, 0 and B equals 0, 0, 0, will both be inite sequences of elements of S, in the sense here intended. But the more important case is of course that of an inite sequences such that all, or almost all, of its members are diarent elements of S which, accordingly, will contain initely many elements. A case of special interest is a decreasing, or rather non-increasing, inite sequence, that is to say, a sequence A equals A, such that an n plus for every consecutive pair of members of A. We can now define the Boolean, as opposed to set theoretical product element of the inite sequence A equals A, as the widest. Among those elements of S which are sub-elements of every element and belonging to the sequence A, or in symbols. A equals an if, and only if, A satisfies the following two conditions. I, P, n, X, P, A, X, for all elements n of A, and for every element X of S. 2, P, A, X, P, B, X, for all elements X of S and for every element B of S that satisfies the condition P, n, Y, P, B, Y, for all elements n and for every element Y of S. In order to show the difference between our Boolean product element of A and the set theoretical inner product or meat of A, we will now convey our discussion to examples S, satisfying our postulates to, whose elements X, Y, Z, are sets, such that XY is their set theoretic product. Our main example S to which I shall refer as the example of the missing half interval is the following. S is a system of certain half-open subintervals of the universal interval U equals 0. S contains, precisely, A, the decreasing sequence A, such that A equals 0, plus, n, and in addition, B, the set theoretic prod n ux of any two of its elements and the set theoretic complements of any one of its elements. Thus S does not contain the half-interval H equals 0, nor any non-empty subinterval of H. Since the missing half-interval H equals 0 is the set theoretic product of the sequence A, it is clear that S does not contain the set theoretic product of A. But S does contain the Boolean product element of A, as here deemed. For the empty interval trivially satisfies condition I, and since it is the widest interval satisfying I, it also satisfies 2. It is clear, moreover, that if we add to S, say any of the intervals b equals 0, or b equals 0, etc., then the largest of these will be the product element of A in the Boolean sense of our definition, although none of them will be the set theoretic product of A. One might think, for a moment, that owing to the presence of an empty element in every S will contain, like S, a product element, in the sense of our definition, of any A in S, for if it does not contain any wider element satisfying I, the empty element will always LL the bill. That this is not so is shown by an example S containing, in addition to the elements of S, the elements, plus the set theoretic products of any two elements and the set theoretic complement of any one element, of the sequence B equals B, where Bn equals 0, n/n plus. It will be easily seen that, although each Bn satisfies condition I, for the product element of A, none of them satisfies condition 2, so that in fact, there is no widest element in S that satisfies the condition I, for the product element of A. Thus S contains neither the set theoretic product of A, nor a product element in our Boolean sense. But S, and all the systems obtained by adding to S a finite number of new intervals, plus products and complements, will contain a product element of A in our sense but not in the set theoretic sense, unless, indeed, we add to S the missing half-interval H equals 0. Remembering that the emptiness of an element A may be characterized in our system by P, A, superscript 10, we can now define an admissible system S and a Borel-Eld of probabilities S, as follows. I, a system S that satisfies our postulates to is called an admissible system if, and only if, S satisfies our set of postulates and in addition the following Denning condition. Let B A equals a be any decreasing sequence of elements of S, we say in this case that A equals A is decreasing relative to B. Then if the product element above the sequence is in S, then lim P, n, B, equals P, A, B. 2. An admissible system S is called a Borel-Eld of probabilities if, and only if, there is in S a product element of any, absolutely or relatively, decreasing sequence of elements of S. Of these two definitions, I, corresponds precisely to Kolmogorov's so-called axiom of continuity, while, 2, plays a part in our system analogous to Kolmogorov's definition of Borel-Elds of probability. It can now be shown that whenever S is a Borel-Eld of probabilities in Kolmogorov's sense, it is also one in the sense here deemed, with probability as a countably additive measure function of the sets which are the elements of S. The definitions of admissible systems and Borel-Elds of probabilities are framed in such a way that all systems S satisfying our postulates and containing only a finite number of diarent elements are admissible systems and Borel-Elds. Accordingly, our definitions are interesting only in connection with systems S containing an finite number of diarent elements. Such finite systems may, or may not, satisfy the one or the other or both of our Denning conditions. In other words, for finite systems our Denning conditions are non-redundant or independent. This non-redundancy can be proved for I, most easily in that form of it which is mentioned in footnote with the help of the example of the missing half interval, S, given above. All we have to do is to deem probability P, x, as equal to L, x, that is to say, the length of the interval x. Our RST definition, I, is then violated since lim P, A, equals N. While for the product element, in S, of A, P, A, equals 0. Definition, too, is violated by our example S, which vacuously satisfies the RST definition. While the RST of these examples establishes the independence or more precisely the non-redundancy of our RST definition by violating it, it does not, as it stands, establish the independence of Kolmogorov's axiom of continuity, which is clearly satisfied by our example. For the missing half interval, h equals 0, whether in S or not, is the only set theoretic product of A, so that A equals H is true for the set theorist, whether or not A is in S. And with A equals H, we have lim P, N, equals P, A. Thus Kolmogorov's axiom is satisfied, even if we omit the condition P, A, superscript 10, cf footnote. It should be mentioned, in this connection, that Kolmogorov fails, in his book, to offer an independence proof for his axiom of continuity, although he claims independence for it. But it is possible to reframe our proof of independence so that it becomes applicable to Kolmogorov's axiom and his set theoretic approach. This may be done by choosing, instead of our S, a system of intervals S, exactly like S but based upon a sequence C equals C, defined by Cn equals 0, n rather than upon the sequence A equals A, with an equals 0, plus, n. We can now show the independence of Kolmogorov's axiom by denning the probabilities of the elements of the sequence A as follows. P, C, equals L, C, plus equals P, A. N. Here L, Cn, is the length of the interval Cn. This definition is highly counterintuitive, since, for example, it assigns to both the intervals, 0, and 0, the probability 1, and therefore to the interval, the probability 0, and the fact that it violates Kolmogorov's axiom, thereby establishing its independence, is closely connected with its counterintuitive character. For it violates the axiom because lim P, C, equals, even though P, C, equals 0. Because of its counterintuitive char. N. Actor, the consistency of this example is far from self-evident, and so the need arises to prove its consistency in order to establish the validity of this independence proof of Kolmogorov's axiom. But this consistency proof is easy in view of our previous independence proof, the proof of the independence of our own RST definition with the help of the example S. For the probabilities P, N, and P, Cn, of the two examples S and S coincide. And since by correlating the two sequences, A and C, we may establish a 1-1 correspondence between the elements of S and S, the consistency of S proves that of S. It is clear that any example proving the independence of Kolmogorov's axiom must be equally counterintuitive, so that its consistency will be in need of proof by some method similar to ours. In other words, the proof of the independence of Kolmogorov's axiom will have to utilize an example which is, essentially, based upon a Boolean definition of products such as ours, rather than upon the set theoretic definition. Although every Borel-Eld of probabilities in Kolmogorov's sense is also one in our sense, the opposite is not the case. For we can construct a system S, which is exactly like S, with H equals, A still missing and containing in its stead the open interval G equals, A, with P, G, equals. We deem, somewhat arbitrarily, G equals U, G equals, and U, G plus G, equals UU. Rather than the point. It is easily seen that S is a Borel-Eld in our sense, with G as the product element of A. But S is not a Borel-Eld in Kolmogorov's sense, since it does not contain the set theoretic product of A, our definition allows an interpretation by a system of sets which is not a Borel system of sets, and in which product and complement are not exactly the set theoretic product and complement. Thus our definition is wider than Kolmogorov's. Our independence proofs of I and 2 seem to me to shed some light upon the functions performed by I and 2. The function of I is to exclude systems such as S, in order to ensure measure theoretical adequacy of the product, or limit, of a decreasing sequence. The limit of the measures must be equal to the measure of the limit. The function of 2 is to exclude systems such as S, with increasing sequences without limits. It is to ensure that every decreasing sequence has a product in S and every increasing sequence a sum. Appendix V. Derivations in the formal theory of probability. In this appendix I propose to give the most important derivations from the system of postulates which has been explained in Appendix 4. I am going to show how the laws of the upper and lower bounds of idempotence, commutation, association, and distribution are obtained, as well as a simpler definition of absolute probability. I will also indicate how Boolean algebra is derivable in the system. A fuller treatment will be given elsewhere. As an abbreviation for if then, I am going to use an arrow registered trademark, a double arrow. For if and only. If, and for and, ea, for there is an a in S such that, and, a, for all a in S. IRST restate postulate and the 6 operational axioms which will all be cited in the proofs. The other postulates will be used implicitly, even postulate will be cited only once, in the proof of. In reading the axioms A and C, it should be kept in mind that I shall soon prove C formula that P, A, equals. Postulate. If A and B are in S, then P, A, B, is a real number. A, EC, ed, P, A, B, superscript 1 P, C, D. A, C, P, A, C, equals P, B, C, registered trademark P, D, A, equals P, D, B. AP, A, equals P, B, B. BP, AB, C, P, A, C. BP, AB, C, equals P, A, B, C, P, B, C. CP, A, superscript 1 P, B, A, registered trademark P, A, equals P, C, A, plus P, C, A. I now proceed to the derivations. P, A, equals P, B, B, equals K. Abbreviation based upon A. P, A, P, A, P, A, equals K. B. P, A, equals P, A, P, A, equals K. B. KK. 0K. And postulate. K superscript 1 P, A, B, registered trademark K equals K plus P, B, B. C. K superscript 1 P, A, B, registered trademark P, B, B, equals 0. P, AB, B, equals P, A, B, B, P, B, B. B. K superscript 1 P, A, B, registered trademark 0 equals P, AB, B, P, A, B. B. 0. K superscript 1 P, A, B, registered trademark 0 P, A, B. 0 P, A, B, registered trademark K equals P, A, B. 0. K equals P, A, B, registered trademark 0 P, A, B. 0 P, A, B, registered trademark 0 P, A, B. 0 P, A, B. Or 0. 0 P, A, B. K superscript 1 P, A, B, registered trademark KP, A, B, C, P, A, B, K. 0 P, A, B, K. K equals P, A, P, A, K. B. 0. K equals P, A, P, A, K. B. K equals P, A, equals P, A, P, A, equals K. B, 0. K equals K. EA, EB, P, A, B, superscript 10 registered trademark K equals EA, EB, P, A, B, superscript 10, A, P, A, equals K equals EB, EA, P, B, A, superscript 1 KA, EA, P, A, equals 0. We have now established all the laws of the upper and lower bounds. And, summed up in, show that probabilities are bounded by 0 and, show that these bounds are actually reached. We now turn to the derivation of the various laws usually taken either from Boolean algebra or from the propositional calculus. First we derive the law of idempotence. Equals P, P, A, equals, B. P, A, B, equals P, A, P, A, B, B. 0, P, A, B, equals P, A, B. This is the law of idempotence, sometimes also called the law of tautology. We now turn to the derivation of the law of commutation. P, A, B, C. P, C, P, B, C, B. This is the second law of monotony, analogous to B. P, A, B, C, A, B, C, equals P, B, C, A, B, C, equals P, B, A, B, C, equals B. P, B, A, B, C, equals P, A, B, C, B. P, B, A, B, C, equals P, C, B. P, B, A, C, P, C, B. P, C, P, B, A, C, substitute. 0, P, C, equals P, B, A, C. This is the law of commutation for the RST argument. In order to extend it to the second argument, we should have to use A. It has been derived from, merely by using the two laws of monotony, B and B. We now turn to the derivation of the law of association. P, D, C, equals, substitute. P, A, D, C, equals P, B, D, C, B. P, A, B, C, C, equals, substitute. P, A, B, C, C, equals P, B, C, C, B. P, B, C, C, equals P, B, C, C, P, C, C, B, P, B, C, C, equals, substitute. P, C, C, equals P, A, B, C, C, equals 2. This is a preliminary form of the law of association. Follows from it by A plus, and B, but I avoid where possible using A or A plus. P, A, B, C, D, D, equals P, C, D, B, add, P, B, add, P, A, D, 0, B. 0, P, A, B, C, D, equals P, C, B, add, P, B, add, P, A, D, 0, B. P, A, B, C, D, P, A, B, C, D, D, 0, B. This is a kind of weak generalization of the RST monotony law, B, P, A, B, C, D, AB, C, D, equals, substitute, P, A, B, C, D, AB, C, D, equals P, AB, C, D, B, P, A, B, C, D, C, D, P, AB, C, D, B, P, A, B, C, D, C, D, P, AB, C, D, B, P, A, B, C, D, D, P, AB, C, D, B, P, A, B, C, D, P, AB, C, D. This is one half of the law of association. P, B, C, A, D, P, AB, C, D, 0. P, AB, C, D, P, B, C, A, D, substitute, 0. 0, P, B, C, A, D, P, B, C, A, D, P, AB, C, D, P, A, B, C, D, 0, substitute, this the second half of the law of association. P, AB, C, D, equals P, A, B, C, D. This is the complete form of the law of association. For the RST argument, see also formula, G, at the beginning of Appendix 4. The law for the second argument can be obtained by applying A. Applying B twice to each side of, only leads to a conditional form with P, B, C, D, superscript 10 registered trademark as antecedent. I now turn to a generalization of the axiom of complementation, C. I shall be a little more concise in my derivations from now on. P, B, B, superscript 10, C, P, C, B, equals P, A, B, plus P, A, B, equals plus P, B, B, C. This is an unconditional form of the principle of complementation, C, which I am now going to generalize. In view of the fact that is unconditional, and that A does not occur on the right-hand side, we can substitute C for A and assert P, A, B, plus P, A, B, equals P, C, B, plus P, C, B. P, A, B, D, plus P, A, B, D, equals P, C, B, D, plus P, C, B, D. By multiplying with P, B, D, we get P, AB, D, plus P, AB, D, equals P, CB, D, plus P, CB, D, B. This is a generalization of. By substitution, we get P, AB, C, plus P, AB, C, equals P, CB, C, plus P, CB, C. In view of P, CB, C, equals P, C, C, B. We may also write, more brie, and in analogy to 0, P, AB, C, plus P, AB, C, equals P, B, C, plus P, C, C. In the derivation of 0, we also need the following formula. P, CB, C, equals P, B, C. Which may be called, cent. Its derivation, in the presence of 0, and, is analogous to the steps, and. This is the generalization of the unconditional form of C and of formula. P, A, B, plus P, A, B, equals P, A, B, plus P, B, B. 0. P, A, B, equals P, A, B, equals P, B, B. 0, 0. P, A, B, plus P, A, B, equals P, A, B, plus P, A, B, equals plus P, B, B. P, A, B, equals P, A, B. This establishes the fact that the elements AA satisfy the condition of postulate AP. We obtain, accordingly, P A equals P A equals P A equals P A B equals P A B AP, that is, a definition of absolute probability in a more workable form. We next derive the general law of addition. P ab C equals P A C P ab C plus P C C 0 0 P A B C equals P A C P A B C plus P C C P A B C equals P A C P B C plus P ab C plus P C C 0 P A B C equals P A C plus P B C P ab C. This is a form of the general law of addition, as will be easily seen if it is remembered that AB means the same in our system as A and B in the Boolean sense. It is worth mentioning that, has the usual cent, P ab equals P B ab cent, P B A B equals P B ab P A B equals P A B B. Sent to this we may add the law of idempotence for the second argument. 0 cents, P ab B equals P A B B equals P A B B cent 0. Moreover, from, we obtain by substitution cent P A equals, and likewise from cent P A equals cent. This yields, by C cent P A B B equals cent C. We therefore have cent EB A P A B equals cent EA P A equals cent C. Also, formulae cent cent do not belong to the theorems of the usual systems. Form, it is unconditional and free of the unusual plus P C C. Can be further generalized. 0 P B C add equals P B add plus P C add P B C add P A B C D equals P ab D plus P A C D P A B C D 0 B 0. This is a generalization of. We now proceed to the derivation of the law of distribution. It may be obtained from, and a simple lemma, which I propose to call the distribution lemma, and which is a generalization of 0 P A B C D equals P A B C D P B C D equals P A B C D B 0 P A B C D equals P A ab C D P C D equals P ab A C D B 0 P A B C D equals P ab A C D. This is the distribution lemma. P ab A C D equals P ab D plus P A C D P ab A C D. Substitute to this formula and, we can now apply the distribution lemma, and we obtain P A B C D equals P ab A C D. This is a form of the RST law of distribution. It can be applied to the left side of the following formula. P B B A C equals P B B A C P A C equals P A C B. We then obtain P ab A B C equals P A C 0. It may be noted that P A B C equals P ab, c, substitute. 0, p, a, c, equals p, b, c, registered trademark p, a, c, equals p, b, c. Consequently, we have p, a, b, c, d, equals p, a, b, c, d. 0, p, a, b, c, d, equals p, a, b, c, d. 0. This is the law of association for the Boolean sum. By substituting in 40, the complements of a and b, we nd p, a, b, c, equals p, b, a, c, 0, 0. This is the law of commutation for the Boolean sum. In the same way we get p, a, b, equals p, a, b, 0, 0. This is the law of idempotence for the Boolean sum. From, we obtain p, a, b, equals p, a, b, c, c, 0, a. p, a, b, p, b, equals p, a, b. This may also be written p, b, superscript 10 registered trademark p, a, b, equals p, a, slash p, b. This formula shows that our generalized concept of relative probability coincides, for p, b, superscript 10, with the usual concept, and that our calculus is a generalization of the usual calculus. That the generalization is a genuine one can be seen from the examples, given in the preceding Appendix 4, showing the consistency of our system with the following formula, E, Ea, Eb, Ec, P, A, B, equals and P, A, B, C, equals 0. A formula which is invalid in many night interpretations of our S but valid in its normal inite interpretations. In order to prove now that, in any consistent interpretation, S must be a Boolean algebra, we note that x, p, a, x, equals p, b, x, registered trademark p, I, z, equals p, by, z, b. X, p, a, x, equals p, b, x, registered trademark p, y, a, z, equals p, y, b, z, a. It is interesting that, needs a, it does not follow from, 0, and b, since it is possible that p, a, z, equals p, b, z, equals 0. This will be the case, for example, if a equals z superscript 1 xx 0 0 x p a x equals p b x and p c x equals p d x registered trademark p a c y equals p b d y b. With the help of 0 of 0 0 and of a, it can now easily be shown at once that whenever the condition p, a, x, equals p, b, x, for every x in S, is satisfied, any name of the element A may be substituted for some O are all occurrences of names of the element B in any well-formed formula of the calculus without changing its truth value, or in other words, the condition, guarantees the substitutional equivalence of A and B. In view of this result, we now deem the Boolean equivalence of two elements, A and B, as follows. D, A equals B, x, P, A, x, equals P, B, x. From this definition we obtain at once the formulae. A equals A. B, A equals B registered trademark B equals A. C, A equals B and B equals C, registered trademark A equals C. D, A equals B registered trademark A may replace B in some O or all places of any formula without equaling its truth value. A, 0, 0, 0. We may also introduce a second definition, D, A equals B plus C A equals BC. Then we obtain I, if A and B are in S, then A and B is in S. Postulate, D, 0, 0, 0. 2. If A is in S then A is in S, postulate. 3. A plus B equals B plus A, D. 4. A plus B, plus C equals A plus, B plus C, D. V. A plus A equals A, D. 6. A plus AB equals A, D. 7. EA, EB, a superscript 1B, 0, D. But the system, A, 2, D, and I, 2, 6, is a well-known axiom system for Boolean algebra, due to Huntington, and it is known that all valid formulae of Boolean algebra are derivable from it. Thus S is a Boolean algebra. And since a Boolean algebra may be interpreted as a logic of derivation, we may assert that in its logical interpretation, the probability calculus is a genuine generalization of the logic of derivation. More particularly, we may interpret AB, which is denoted by AB equals B, to mean, in logical interpretation, A follows from B, or B entails A. It can be easily proved that plus AB registered trademark P, A, B, equals. This is an important formula which is asserted by many authors, but which is nevertheless invalid in the usual systems provided they are consistent. For in order to make it valid, we must make allowance for P, A, AA, plus P, A, AA, equals. Even though we have P, A plus A, AA, equals. That is to say, such formulae as P, A plus A, B, equals P, A, B, plus P, A, B, must not be unconditionally asserted in the system. CFR axiom C, see also footnote, above. The converse of plus, that is to say, P, A, B, equals registered trademark AB, must not be demonstrable, of course, as our second and third examples proving consistency show. Cf also the formula, E, in the present and in the preceding appendices. But there are other valid equivalences in our system such as ABP, A, AB, superscript 10. ABP, A, AB, equals. None of these can hold in the usual systems in which P, A, B, is undefined unless P, B, superscript 10. It seems to be quite clear, therefore, that the usual systems of probability theory are wrongly described as generalizations of logic. They are formally inadequate for this purpose, since they do not even entail Boolean algebra. The formal character of our system makes it possible to interpret it, for example, as a many-valued propositional logic, with as many values as we choose, either discrete, or dense, or continuous, or as a system of modal logic. There are in fact many ways of doing this. For example, we may deem A necessarily implies B by P, B, AB, superscript 10, as just indicated, or A is logically necessary by P, A, equals. Even the problem whether a necessary statement is necessarily necessary and ds a natural place in probability theory, it is closely connected with the relation between primary and secondary probability statements, which plays an important part in probability theory, as shown in Appendix 9, point of the third note. Roughly, writing Cx for x is necessary, or demonstrable, and h for p, a, equals, we may show that CACH. And therefore we nd that CA registered trademark CP, H, equals. Which may be taken to mean that CA entails that A is necessarily necessary, and since this means something like CA registered trademark CP, P, A, equals, P, A, equals, we obtain, secondary, probability statements about, primary, probability statements. But there are of course other possible ways of interpreting the relation between a primary and a secondary probability statement. Some interpretations would prevent us from treating them as belonging to the same linguistic level, or even to the same language. Addendum. I have found since that the following system of 3 axioms, A, B, D, and C, D, is equivalent to the 6 axioms on PP. And A, EA, EB, P, A, superscript 1 P, A, B, BD, D, P, AB, D, equals P, C, D, E, F, P, A, B, divided by P, C, B, and P, A, E, divided by P, C, E, divided by P, B, C, and P, B, E, divided by P, F, E, and P, B, F, divided by P, F, F, divided by P, E, F, registered trademark P, A, F, P, B, E, equals P, C, E, CDP, A, B, equals P, B, B, P, A, B, EC, P, B, B, superscript 1 P, C, B. I also have found since an example not satisfying A but satisfying all the other axioms and postulate AP, see note 0 on P. The example on P can be moded, putting P equals P, A, B, equals whenever P, B, equals 0, P, A, B, equals P, AB, slash P, B, whenever P, B, superscript 1 0, so as to obtain a Boolean algebra proving the independence of C. See also my conjectures and refutations, pages. The third and later German editions of my Logik der Verstchung, and Synthese, pages 0, and 0, p0. Appendix 6. On objective disorder or randomness. It is essential for an objective theory of probability and its application to such concepts as entropy, or molecular disorder, to give an objective characterization of disorder or randomness, as a type of order. In this appendix, I intend to indicate some of the general problems this characterization may help to solve, and the way in which they may be approached. 1. The distribution of velocities of the molecules of a gas in equilibrium is supposed to be, very nearly, random. Similarly, the distribution of nebulae in the universe appears to be random, with a constant overall density of occurrence. The occurrence of rain on Sundays is random. In the long run, each day of the week gets equal amounts of rain, and the fact that there was rain on Wednesday, or any other day, may not help us to predict whether or not there will be rain on Sunday. 2. We have certain statistical tests of randomness. 3. We can describe randomness as absence of regularity, but this is not, as we shall see, a helpful description. For there are no tests for presence or absence of regularity in general, only tests for presence or absence of some given or proposed specific regularity. Thus our tests of randomness are never tests which exclude the presence of all regularity. We may test whether or not there is a significant correlation between rain and Sundays, or whether a certain given formula for predicting rain on Sundays works, such as at least once in 3 weeks, but though we may reject this formula in view of our tests, we cannot determine, by our tests, whether or not there exists some better formula. 4. Under these circumstances, it seems tempting to say that randomness or disorder is not a type of order which can be described objectively and that it must be interpreted as our lack of knowledge as to the order prevailing, if any order prevails. I think that this temptation should be resisted, and that we can develop a theory which allows us actually to construct ideal types of disorder, and of course also ideal types of order, and of all degrees in between these extremes. 5. The simplest problem in this ELD, and the one which, I believe, I have solved, is the construction of a one-dimensional ideal type of disorder, an ideally disordered sequence. The problem of constructing a sequence of this kind arises immediately from any frequency theory of probability which operates with innate sequences. This may be shown as follows. 6. According to von Mises, a sequence of 0s and s with equidistribution is random if it admits of no gambling system, that is to say, of no system which would allow us to select in advance a subsequence in which the distribution is unequal. But of course, von Mises admits that any gambling system may, accidentally, work for some time. It is only postulated that it will break down in the long run, or more precisely, in an infinite number of trials. Accordingly, a Mises collective may be extremely regular in its commencing segment, provided they become irregular in the end. Von Mises's rule is incapable of excluding collectives which start very regularly, say with 0,000,000, and so on, for the RSTVE 100 million places. 7. It is clear that we cannot empirically test this kind of deferred randomness, and it is clear that whenever we do test randomness in a sequence, we have a diarrhent type of randomness in mind, a sequence which from the very beginning behaves in a reasonably random-like fashion. But this phrase, from the very beginning, creates its own problem. Is the sequence 000 random-like? Clearly, it is too short for us to say yes or no. But if we say that we need a long sequence for deciding a question of this kind, then, it seems, we unsay what we have said before. It seems that we retract the phrase from the very beginning. 8. The solution of this difficulty is the construction of an ideally random sequence, one which for each beginning segment, whether short or long, is as random as the length of the segment permits, or in other words, a sequence whose degree n of randomness, that is, its n freedom from after x, grows with the length of the sequence as quickly as is mathematically possible. How to construct a sequence of this kind has been shown in Appendix 4 of the book. See especially Note to Appendix 4, with a reference to an as yet unpublished paper by Dr. L.R.B. Elton and myself. 9. The infinite set of all sequences answering this description may be called the ideal type of random alternatives with equal distribution. 10. Although no more is postulated of these sequences than that they are strongly random in the sense that the night commencing segments would pass all tests of randomness, they can easily be shown to possess frequency limits, in the sense usually demanded by frequency theories. This solves in a simple manner one of the central problems of my chapter on probability elimination of the limit axiom, by way of a reduction of the limit-like behavior of the sequences to their random-like behavior in night segments. 11. The construction may quite easily be extended into both directions of the one-dimensional case, by correlating the RST, second, of the odd-numbered elements with the RST, second, place of the positive direction, and the RST, second, of the even-numbered elements with the RST, second, place of the negative direction, and by similar well-known methods, we can extend our construction to the cells of an n-dimensional space. 12. While other frequency theorists, especially von Mises, Copeland, Wald, and Church, were mainly interested in denning random sequences in the most severe way by excluding all gambling systems. In the widest possible sense of the word all, that is, in the widest sense compatible with a proof that random sequences so deemed exist, my aim has been quite diarrhent. I wished from the beginning to answer the objection that randomness is compatible with any night commencing segment, and I wished to describe sequences that arise from random-like night sequences, by a transition to infinity. I hoped by this method to achieve two things: to keep close to that type of sequence which would pass statistical tests of randomness, and to prove the limit theorem. Both have been done now, as here indicated under point, with the help of the construction given in my old Appendix 4. But I have meanwhile found that the measure-theoretical approach to probability is preferable to the frequency interpretation. See my postscript, Chapter 3, both for mathematical and philosophical reasons. The decisive point is connected with the propensity interpretation of probability, fully discussed in my postscript. I therefore do not think any longer that the elimination of the limit axiom from the frequency theory is very important. Still, it can be done. We can build up the frequency theory with the help of the ideal type of the random sequences constructed in Appendix 4, and we can say that an empirical sequence is random to the extent to which tests show its statistical similarity to an ideal sequence. The sequences admitted by von Mises, Copeland, Wald, and Church are not necessarily of this kind, as mentioned above. but it is a fact that any sequence ever rejected on the basis of statistical tests for being not random may later turn into an admissible random sequence in the sense of these authors. Addendum 13. Today, some years after reaching a solution of this old problem which would have satisfied me I no longer believe in the importance of the fact that a frequency theory can be constructed which is free from all the old difficulties. Yet I still think it important that it is possible to characterize randomness as a type of order, and that we can construct models of random sequences. 14. It is significant that ideally random sequences, as described here under, 2, 0, satisfy the formal system of appendices 4 and v. And also of the older appendix 2. For let S be any set of random sequences of 0s and s, such that A equals A, B equals B, and that, for a superscript 1b, A and B are independent, and thus abrandom. Let S contain the two sequences consisting of 0s and of s only. We put P, A, B, equals lim, \n, /bn, P, ab, C, equals lim, \n, /cn. P, A, B, equals lim, n, bn, /bn, P, A, equals lim, n, Then all postulates and axioms of appendices 4 and v are satisfied, except postulate, cfp. Appendix 7. 0 Probability and the fine structure of probability and of content. In the book, a sharp distinction is made between the idea of the probability of a hypothesis, and its degree of corroboration. It is asserted that if we say of a hypothesis that it is well corroborated, we do not say more than that it has been severely tested, it must be thus a hypothesis with a high degree of testability, and that it has stood up well to the severest tests we were able to design so far. And it is further asserted that degree of corroboration cannot be a probability, because it cannot satisfy the laws of the probability calculus. For the laws of the probability calculus demand that, of two hypotheses, the one that is logically stronger, or more informative, or better testable, and thus the one which can be better corroborated, is always less probable on any given evidence than the other. See especially sections and. Thus a higher degree of corroboration will, in general, be combined with a lower degree of probability, which shows not only that we must distinguish sharply between probability, in the sense of the probability calculus, and degree of corroboration or confirmation, but also that the probabilistic theory of induction, or the idea of an inductive probability, is untenable. The impossibility of an inductive probability is illustrated in the book, sections 0, and, by a discussion of certain ideas of Reichenbach's, Keynes's, and Caille's. One result of this discussion is that in an innate universe, it may be innate with respect to the number of distinguishable things, or of spatio-temporal regions, the probability of any, non-tautological, universal law will be 0. Another result was that we must not uncritically assume that scientists ever aim at a high degree of probability for their theories. They have to choose between high probability and high informative content, since for logical reasons they cannot have both, and faced with this choice, they have so far always chosen high informative content in preference to high probability provided that the theory has stood up well to its tests. By probability, I mean here either the absolute logical probability of the universal law, or its probability relative to some evidence, that is to say, relative to a singular statement, or to a night conjunction of singular statements. Thus if A is our law, and B any empirical evidence, I assert that. And also that P, A, equals 0. P, A, B, equals 0. These formulae will be discussed in the present appendix. The two formulae, and, are equivalent. For as Juries and Keynes observed, if the prior probability, the absolute logical probability, of a statement A is 0, then so must be its probability relative to any night evidence B, since we may assume that for any night evidence B, we have P, B, superscript 1 0. For P, A, equals 0 entails P, a, b, equals 0, and since P, a, b, equals P, a, b, slash P, b, we obtain, from. On the other hand, we may obtain, from, for if, holds for any evidential B, however weak or almost tautological, we may assume that it also holds for the zero evidence, that is to say, for the tautology T equals BB, and P, A, may be deemed as equal to P, A, T. There are many arguments in support of, and. First, we may consider the classical definition of probability as the number of the favorable possibilities divided by that of all, equal, possibilities. We can then derive, for example, if we identify the favorable possibilities with the favorable evidence. It is clear that, in this case, P, A, B, equals 0, for the favorable evidence can only be nite, while the possibilities in an inite universe must be clearly inite. Nothing depends here on inity, for any sufficiently large universe will yield, with any desired degree of approximation, the same result, and we know that our universe is extremely large, compared with the amount of evidence available to us. This simple consideration is perhaps a little vague, but it can be considerably strengthened if we try to derive, rather than, from the classical definition. We may to this end interpret the universal statement as entailing an inite product of singular statements, each endowed with a probability which of course must be less than unity. In the simplest case, A itself may be interpreted as such as inite product, that is to say, we may put A equals everything has the property A, or in symbols, x, x, which may be read for whatever value of x we may choose, x has the property A. In this case, A may be interpreted as the inite product A equals AAA where AI equals Aki, and where key is the name of the th individual of our inite universe of discourse. We may now introduce the name n for the product of the RSTN. Singular statements, A n, so that A may be written. A equals lemon. N registered trademark yen. And, see page. P, A, equals lim P, N registered trademark yen. It is clear that we may interpret n as the assertion that, within the nite sequence of elements k, kn, all elements possess the property A. This makes it easy to apply the classical definition to the evaluation of P, n. There is only one possibility that is favorable to the assertion and it is the possibility that all the n individuals, key without exception, possess the property A rather than the property non-A. But there are in all n possibilities, since we must assume that it is possible for any individual key, either to possess the property A or the property non-A accordingly, the classical theory gives C. P, n, equals /n. But from, and, C, we obtain immediately. The classical argument leading to, C, is not entirely adequate, although it is, I believe, essentially correct. The inadequacy lies merely in the assumption that A and non-A are equally probable. For it may be argued correctly, I believe that since A is supposed to describe a law of nature, the various AI are instantiation statements, and thus more probable than their negations which are potential falsiers. Cf. Note to section. This objection, however, relates to an inessential part of the argument. For whatever probability short of unity we attribute to A, the inite product A will have zero probability, assuming independence, which will be discussed later on. Indeed, we have struck here a particularly trivial case of the 1 or 0 law of probability, which we may also call, with an allusion to neurophysiology, the all or nothing principle. In this case it may be formulated thus: if A is the inite product of A, where P, AI, equals P, Aj, and where every AI is independent of all others, then the following holds. P, A, equals lim P, n, equals 0, unless P, A, equals P, n, equals n registered trademark yen. But it is clear that P, A, equals is unacceptable, not only from my point of view but also from that of my inductivist opponents, who clearly cannot accept the consequence that the probability of a universal law can never be increased by experience. For all swans are black would have the probability as well as all swans are white, and similarly for all colors, so that there exists a black swan and there exists a white swan, etc., would all have zero probability, in spite of their intuitive logical weakness. In other words, P, A, equals would amount to asserting on purely logical grounds with probability the emptiness of the universe. Thus, establishes. Although I believe that this argument, including the assumption of independence to be discussed below, is incontestable, there are a number of much weaker arguments which do not assume independence and which still lead to. For example, we might argue as follows. It was assumed in our derivation that for every key, it is logically possible that it has the property A, and alternatively, that it has the property non-A. This leads essentially to. But one might also assume, perhaps, that what we have to consider as our fundamental possibilities are not the possible properties of every individual in the universe of n individuals, but rather the possible proportions with which the properties A and non-A may occur within a sample of individuals. In a sample of n individuals, the possible proportions with which A may occur are 0/n, n/n. If we consider the occurrences of any of these proportions as our fundamental possibilities, and thus treat them as equiprobable, Laplace's distribution, then, would have to be replaced by P, n, equals /n plus, so that lim P, n, equals 0. It is the assumption underlying Laplace's derivation of his famous rule of succession. This is why I call it Laplace's distribution. It is an adequate assumption if our problem is one of mere sampling. It seems inadequate if we are concerned, as was Laplace, with a succession of individual events. See also Appendix 9, points of my third note, and Note 0 to Appendix 8. Although from the point of view of a derivation of formula is much weaker than C, it still allows us to derive, and it allows us to do so without identifying the observed cases as the favorable ones or assuming that the number of observed cases is night. A very similar argument leading to, would be the following. We may consider the fact that every universal law entails, and is therefore at most equally as probable as, a statistical hypothesis H of the form P, x, y, equals, and that the absolute probability of H may be calculated with the help of Laplace's distribution, with the result P, H, equals 0. Cf Appendix 9, the third note, especially. But since A entails H, this leads to P, A, equals 0, that is to say, 2. To me, this proof appears the simplest and most convincing. It makes it possible to uphold, and, by assuming that, applies to A and 5, to H. So far our considerations were based on the classical definition of probability. But we arrive at the same result if instead we adopt as our basis the logical interpretation of the formal calculus of probability. In this case, the problem becomes one of dependence or independence of statements. If we again regard it as the logical product of the singular statements A, then the only reasonable assumption seems to be that, in the absence of any, other than tautological, information, we must consider all these singular statements as mutually independent of one another, so that AI may be followed by AJ or by its negation, AJ, with the probabilities P, AJ, AI, equals P, AJ. P, AJ, AI, equals P, AJ, equals P, AJ. Every other assumption would amount to postulating ad hoc a kind of aftereffect, or in other words, to postulating that there is something like a causal connection between AI and AJ. But this would obviously be a non-logical, a synthetic assumption, to be formulated as a hypothesis. It thus cannot form part of purely logical theory of probability. The same point may be put a little differently thus, in the presence of some hypothesis, H say, we may of course have 6, P, AJ, I, P, AJ, H. For H may inform us of the existence of a kind of aftereffect. Consequently, we should then have 7, P, AJ, H, P, AI, H, P, AJ, H. Since, is equivalent to. But in the absence of H, or if H is tautologos or, in other words, if we are concerned with absolute logical probabilities, must be replaced by 8, P, AJ, equals P, AI, P, AJ. Which means that AI and AJ are independent, and which is equivalent to 9, P, AJ, AI, equals P, AJ. But the assumption of mutual independence leads, together with P, AI, as before to P, A, equals 0, that is to say, 2. Thus, that is, the assumption of the mutual independence of the singular statements AI leads to, and mainly for this reason, some authors have, directly or indirectly, rejected. The argument has been, invariably, that, must be false because if it were true, we could not learn from experience, empirical knowledge would be impossible. But this is incorrect, we may learn from experience even though P, A, equals P, A, B, equals 0, for example, C, A, B, that is to say, the degree of corroboration of A by the tests B may nonetheless increase with new tests. Cf. Appendix 9. Thus this transcendental argument fails to hit its target, at any rate, it does not hit my theory. But let us now consider the view that, is false, or in other words, that P, AJ, P, AI, P, AJ is valid, and consequently P, AJ, AI, P, AJ. And also the following, plus P, N, AN, P, N. This view asserts that once we have found some key to possess the property A, the probability increases that another kj possesses the same property, and even more so if we have found the property in a number of cases. Or in Hume's terminology, plus, asserts that those instances, for example, Kn, of which we have had no experience, are likely to resemble those, of which we have had experience. The quotation, except for the words are likely to, is taken from Hume's criticism of induction. And Hume's criticism fully applies to, plus, or its italicized verbal formulation. For, Hume argues, even after the observation of the frequent constant conjunction of objects, we have no reason to draw any inference concerning any object beyond those of which we have had experience. If anybody should suggest that our experience entitles us to draw inferences from observed to unobserved objects, then, Hume says, I would renew my question, why from this experience we form any conclusion beyond those past instances, of which we have had experience. In other words, Hume points out that we get involved in an innate regress if we appeal to experience in order to justify any conclusion concerning unobserved instances, even mere probable conclusions, as he adds in his abstract. For there we read, it is evident that Adam, with all his science, would never have been able to demonstrate that the course of nature must continue uniformly the same. Nay, I will go farther, and assert that he could not so much as prove by any probable arguments that the future must be conformable to the past. All probable arguments are built on the supposition that there is conformity betwixt the future and the past, and therefore can never prove it. Thus, plus, is not justable by experience, yet in order to be logically valid, it would have to be of the character of a tautology, valid in every logically possible universe. But this is clearly not the case. Thus, plus, if true, would have the logical character of a synthetic a priori principle of induction, rather than of an analytic or logical assertion. But it does not quite so even as a principle of induction. For, plus, may be true, and P, A, equals 0 may be valid nonetheless. An example of a theory which accepts, plus, as a priori valid though, as we have seen, plus, must be synthetic and which at the same time accepts P, A, equals 0, is Carnap's. An ective probabilistic principle of induction would have to be even stronger than plus. It would have to allow us, at least, to conclude that for something singular evidence B, we may obtain P, A, B, slash, or in words, that A may be made, by accumulating evidence in its favor, more probable than its negation. But this is only possible if, is false, that is to say, if we have P, A, 0. A more direct disproof of, plus, and a proof of, can be obtained from an argument which Juries gives in his theory of probability. Juries discusses a formula which he numbers, and which in our symbolism amounts to the assertion that, provided P, by, A, equals for every in, so that P, A B n, equals P, A, the following formula must hold. 0, P, A, B n, equals P, A, slash P, B n, equals P, A, slash P, B, P, B, B, P, B n, B n. Discussing this formula, Juries says, I am still using my symbols in place of his thus, with a sufficient number of variations, one of three things must happen, the probability of it on the information available exceeds. It is always 0. P, Bn, Bn, will tend to. To this he adds that case, is impossible, trivially so, so that only, and, remain. Now I say that the assumption that case, holds universally, for some obscure logical reasons, and it would have to hold universally, and indeed a priori, if it were to be used in induction, can be easily refuted. For the only condition needed for deriving 0, apart from 0p, by, is that 3 exists some statement as such that p, bn, a, equals. But this condition can always be satisfied, for any sequence of statements by. For assume that the by are reports on penny tosses, then it is always possible to construct a universal law which entails the reports of all the n, observed penny tosses, and which allows us to predict all further penny tosses, though probably incorrectly. Thus, the required A always exists, and there always is also another law, ascent, yielding the same RSTN, results but predicting, for the nth toss, the opposite result. It would be paradoxical, therefore, to accept Juries' case, since for a sufficiently large n we would always obtain P, Bn, Bn, close to, and also, from another law, ascent, P, Bn, Bn, close to. Accordingly, Juries' argument, which is mathematically inescapable, can be used to prove his case, which happens to coincide with my own formula, as stated at the beginning of this appendix. Point 0. We may sum up our criticism of plus as follows. Some people believe that, for purely logical reasons, the probability that the next thing we meet will be red increases in general with the number of red things seen in the past. But this is a belief in magic, in the magic of human language. For red is merely a predicate, and there will always be predicates A and B which both apply to all the things so far observed, but lead to incompatible probabilistic predictions with respect to the next thing. These predicates may not occur in ordinary languages, but they can always be constructed. Strangely enough, the magical belief here criticized is to be found among those who construct artificial model languages, rather than among the analysts of ordinary language. By thus criticizing, plus, I am defending, of course, the principle of the absolute logical independence of the various and from any combination age, that is to say, my criticism amounts to a defense of, and. There are further proofs of. One of them, which is fundamentally due to an idea of Juries and Rinch, will be discussed more fully in Appendix 8. Its main idea may be put, with slight adjustments, as follows. Let E be an explicandum, or more precisely, a set of singular facts or data which we wish to explain with the help of a universal law. There will be, in general, an infinite number of possible explanations, even an infinite number of explanations, mutually exclusive, given the data E, such that the sum of their probabilities, given E, cannot exceed unity. But this means that the probability of almost all of them must be zero unless, indeed, we can order the possible laws in an infinite sequence, so that we can attribute to each a positive probability in such a way that their sum converges and does not exceed unity. And it means, further, that to laws which appear earlier in the sequence, a greater probability must be attributed, in general, than to laws which appear later in the sequence. We should therefore have to make sure that the following important consistency condition is satisfied. Our method of ordering the laws must never place a law before another one if it is possible to prove that the probability of the latter is greater than that of the former. Juries and Rinch had some intuitive reasons to believe that a method of ordering the laws satisfying this consistency condition may be found. They proposed to order the explanatory theories according to their decreasing simplicity postulate, or according to their increasing complexity, measuring complexity by the number of the adjustable parameters of the law. But it can be shown, and it will be shown in Appendix 8, that this method of ordering, or any other possible method, violates the consistency condition. Thus we obtain P, A, E, equals 0 for all explanatory hypotheses, whatever the data E may be, that is to say, we obtain, and thereby indirectly. An interesting aspect of this last proof is that it is valid even in a finite universe, provided our explanatory hypotheses are formulated in a mathematical language which allows for an infinity of mutually exclusive hypotheses. For example, we may construct the following universe. On a much extended chessboard, little disks or draft pieces are placed by somebody according to the following rule: there is a mathematically defined function, or curve, known to him but not to us, and the disks may be placed only in squares which lie on the curve. Within the limits determined by this rule, they may be placed at random. Our task is to observe the placing of the disks, and to end an explanatory theory, that is to say, the unknown mathematical curve, if possible, or one very close to it. Clearly, there will be an infinity of possible solutions, any two of which are incompatible, although some of them will be indistinguishable with respect to the disks placed on the board. Any of these theories may, of course, be refuted by disks placed on the board after the theory was announced. Although the universe that of possible positions may here be chosen to be a finite one, there will be nevertheless an infinity of mathematically incompatible explanatory theories. I am aware, of course, that instrumentalists or operationalists might say that the differences between any two theories determining the same squares would be meaningless. But apart from the fact that this example does not form part of my argument, so that I need really not reply to this objection, the following should be noted. It will be possible, in many cases, to give meaning to these meaningless differences by making our mesh sosiently any, i.e. subdividing our squares. The detailed discussion of the fact that my consistency condition cannot be satisfied will be found in Appendix 8. I will now leave the problem of the validity of formulae, and, in order to proceed to the discussion of a formal problem arising from the fact that these formulae are valid, so that all universal theories, whatever their content, have zero probability. There can be no doubt that the content or the logical strength of two universal theories can differ greatly. Take the two laws A equals all planets move in circles and A equals all planets move in ellipses. Owing to the fact that all circles are ellipses, with eccentricity 0, A entails A, but not vice versa. The content of A is greater by far than the content of A. There are, of course, other theories, and logically stronger ones, than A. For example, all planets move in concentric circles round the Sun. The fact that the content of A exceeds that of A is of the greatest significance for all our problems. For example, there are tests of A, that is to say, attempts to refute A by discovering some deviation from circularity, which are not tests of A, but there could be no genuine test of A which would not, at the same time, be an attempt to refute A. Thus A can be more severely tested than A, it has the greater degree of testability, and if it stands up to its more severe tests, it will attain a higher degree of corroboration than A can attain. Similar relationships may hold between two theories, A and A, even if it does not logically entail A, but entails instead a theory to which A is a very good approximation. Thus A may be Newton's dynamics and A may be Kepler's laws, which do not follow from Newton's theory, but merely follow with good approximation. See also section of my postscript. Here too, Newton's theory is better testable, because its content is greater. Now our proof of shows that these differences in content and in testability cannot be expressed immediately in terms of the absolute logical probability of the theories A and A, since P, A, equals P, A, equals 0. And if we deem a measure of content, C, A, by C, A, equals, P, A, as suggested in the book, then we obtain, again, C, A, equals C, A, so that the differences in content which interest us here remain unexpressed by these messieurs. Similarly, the difference between a self-contradictory statement AA and a universal theory remains unexpressed, since P, AA, equals P, A, equals 0, and C, AA, equals C, A, equals. All this does not mean that we cannot express the difference in content between A and A in terms of probability, at least in some cases. For example, the fact that A entails A but not vice versa would give rise to P, A, equals 0, P, A, equals. Even though we should have, at the same time, P, A, equals P, A, equals 0. Thus we should have P, A, P, A, which would be an indication of the greater content of A. The fact that there are these differences in content and in absolute logical probability which cannot be expressed immediately by the corresponding measures may be expressed by saying that there is any structure of content, and of logical probability, which may allow us to differentiate between greater and smaller contents and absolute probabilities even in cases where the measures C, A, and P, A, are too coarse, and insensitive to the differences, that is, in cases where they yield equality. In order to express this any structure, we may use the symbols, is higher, and, is lower, in place of the ordinary symbols and. We may also use, or is higher or equally high, and dot. The use of these symbols can be explained by the following rules. 1. C, A, C, B, and thus its equivalent P, B, P, A, may be used to state that the content of A is greater than that of B, at least in the sense of the any structure of content. We shall thus assume that C, A, C, B, entails C, A, C, B, and that this in turn entails C, A, C, B, that is to say, the falsity of C, A, C, B. None of the opposite entailments hold. 2. C, A, C, B, and C, A, C, B, together entail C, A, equals C, B, but C, A, equals C, B, is compatible with C, A, C, B, or with C, A, C, B, and, of course, also with C, A, C, B, and with C, A, C, B. 3. C, A, C, B, always entails C, A, C, B. 4. Corresponding rules will hold for P, A, P, B, etc. The problem now arises of determining the cases in which we may say that C, A, C, B, holds even though we have C, A, equals C, B. A number of cases are fairly clear, for example, unilateral entailment of B by A. More generally, I suggest the following rule. If for all sufficiently large night universes, that is, for all universes with more than n members, for some sufficiently large n, we have C, A, C, B, and thus, in accordance with rule, C, A, C, B, we retain C, A, C, B, for an inite universe even if, for an inite universe, we obtain C, A, equals C, B. This rule seems to cover most cases of interest, although perhaps not all. The problem of A equals all planets move in circles and A equals all planets move in ellipses is clearly covered by our rule, and so is even the case of comparing an A equals all planets move in ellipses with an eccentricity other than 0, for P, A will hold in all sufficiently large night universes, of possible observations, say, in the simple sense that there are more possibilities compatible with A than with A. The NE structure of content and of probability here discussed not only ekes the limits, 0 and, of the probability interval, but it ekes in principle all probabilities between 0 and. For let A and A be universal laws with P, A, equals 0 and P, A, as before, let B be not entailed by either A or their negations, and let 0 P, B, equals R. Then we have P, AVB, equals P, AVB, equals R. And at the same time, P, AVB, P, AVB. Similarly we have P, AB, equals P, AB, equals R. And at the same time, P, AB, equals P, AB. Since P, A, although of course P, A, equals P, A, equals. Thus we may have for every B such that P, B, equals R, AC such that P, C, equals P, B, and P, C, P, B, and also AC such that P, C, equals P, B, and P, C, P, B. The situation here discussed is important for the treatment of the simplicity or the dimension of a theory. This problem will be further discussed in the next appendix. Addendum. In the last paragraph of the preceding appendix, I hinted that the idea of a NE structure of probability may be of significance for the comparison of the simplicity and dimension of theories. But the opposite also holds. The simplicity and especially the dimension of a theory are significant for the theory of its NE structure, as emerges from the RST pages of the following appendix. The dimension of a theory is relative to a field of application and thus to a set of problems for which the theory is some solution. The same relativization will be relevant to the NE structure of theories, and thus to their goodness. Appendix 8. Content, simplicity, and dimension. As indicated earlier, I do not believe in hampering scientific language by preventing the scientist from using freely, whenever it is convenient, new ideas, predicates, occult concepts, or anything else. For this reason, I cannot support the various recent attempts to introduce into the philosophy of science the method of artificial calculi or language systems supposed to be models of a simplified language of science. I believe that these attempts have not only been useless so far, but that they have even contributed to the obscurity and confusion prevalent in the philosophy of science. It has been explained in section and in appendix I that, had we, absolutely, atomic statements at our disposal or what amounts to the same, absolutely, atomic predicates, then we might introduce, as a measure of the content of a theory, the reciprocal of the minimum number of atomic statements needed for refuting that theory. For since the degree of content of a theory is the same as its degree of testability or refutability, the theory which is refutable by fewer atomic statements would also be the one which is the more easily refutable or testable, and thus the one with the greater content. In brief, the smaller the number of atomic statements needed to compose a potential falsier, the greater the content of the theory. But I do not want to operate either with the science of atomic statements, or with an artificial language system in which atomic statements are available to us. For it seems to me quite clear that there are no natural atomic predicates available in science. To some older logicians, the predicates man and mortal seem to have presented themselves as examples of something like atomic predicates. Carnap uses blue or warm as examples, presumably because man and mortal are highly complex ideas which, some may think, can be deemed in terms of simpler ideas such as blue or warm. Yet it is characteristic of scientific discussions that neither these nor any other predicates are treated as, absolutely, atomic. Depending upon the problem under consideration, Not only man and mortal but also blue or warm may be treated as highly complex, blue, say, as the color of the sky, explicable in terms of atomic theory. Even the phenomenal term blue may be treated, in certain contexts, as definable as a character of visual images correlated with certain physiological stimuli. It is characteristic of scientific discussion that it proceeds freely, and the attempt to take away its freedom, by tying it down upon the Procrustean bed of a pre-established language system would, if successful, be the end of science. For these reasons I rejected in advance the idea of using atomic statements for the purpose of measuring the degree of content or simplicity of a theory, and I suggested that we might use, instead, the idea of relative atomic statements, and further, the idea of of statements which are relative atomic with respect to a theory or a set of theories to the testing of which they are relevant, f which could be interpreted as of application of the theory, or of the set of theories. If we take as our example again, as in the preceding appendix, the two theories A equals all planets move in circles and A equals all planets move in ellipses, then we can take as our all the statements of the form at the time x the planet y was in the position z, which will be our relative atomic statements. And if we assume that we already know that the track of the planet is a plane curve, then we can take a graph paper that represents the and enter on it the various positions, marking in each case the time, and the name of the planet in question, so that each entry represents one of the relative atomic statements. We can, of course, make the representation three-dimensional, by marking the position with a pin whose length represents the time, measured from some assumed zero instant, and variations in the color of the pinhead may be used to indicate the names of the various planets. It has been explained, mainly in sections 02, and in my old appendix I, how the minimum number of the relative atomic statements needed to refute a certain theory could be used as a measure of the complexity of the theory. And it was shown that the formal simplicity of a theory might be measured by the paucity of its parameters, insofar as this paucity was not the result of a formal rather than a material reduction in the number of the parameters. Cf especially sections 0, f, and appendix I. Now all these comparisons of the simplicity of theories, or of their contents, will, clearly, amount to comparisons of the NE structure of their contents, in the sense explained in the preceding appendix, because their absolute probabilities will all be equal, that is, equal to 0. And I wish RST to show that the number of the parameters of a theory, with respect to a of application, can indeed be interpreted as measuring the NE structure of its content. What I have to show, to this end, is that for a sufficiently large night universe, the theory with the greater number of parameters will always be more probable, in the classical sense, than the theory with the smaller number of parameters. This can be shown as follows. In the case of a continuous geometrical of applications, our universe of possible events, each described by a possible relative atomic statement, is of course inite. As shown in sections F, we can in this case compare two theories with respect to the dimension, rather than the number, of the possibilities which they leave open, that is, the possibilities which are favorable to them. The dimension of these possibilities turns out to be equal to the number of parameters. We now replace the inite universe of relative atomic statements by a nite, although very large, universe of relative atomic statements, corresponding to the chessboard example in the preceding appendix. That is to say, we assume that every relative atomic statement refers to a little square with the side epsilon as the position of a planet rather than to a point of the plane, and that the possible positions do not overlap. Somewhat differently from the example of the preceding appendix, we now replace the various curves which are the usual geometrical representations of our theories by quasi-curves, of a width approximately equal to epsilon, that is to say, by sets, or chains, of squares. As a result of all this, the number of the possible theories becomes nite. We now consider the representation of a theory with d parameters which in the continuous case was represented by a d-dimensional continuum whose points, d tuples, each represented a curve. We nd that we can still use a similar representation, except that our d-dimensional continuum will be replaced by a d-dimensional arrangement of d-dimensional cubes, with the side epsilon. Each chain of these cubes will now represent one quasi-curve, and thus one of the possibilities favorable to the theory, and the d-dimensional arrangement will represent the set of all quasi-curves compatible with, or favorable to, the theory. But we can now say that the theory with fewer parameters, that is to say, the set of quasi-curves which is represented by an arrangement of fewer dimensions, will not only have fewer dimensions, but will also contain a smaller number of cubes, that is, of favorable possibilities. Thus we are just in applying the results of the preceding section. If A has fewer parameters than A, we can assert that, in a sufficiently large but night universe, we shall have P, A, P, A. And therefore, P, A, P, A. But formula remains valid when we assume that epsilon tends to 0, which in the limit amounts to replacing the night universe by an innate one. We arrive, therefore, at the following theorem. If the number of parameters of A is smaller than the number of parameters of A, then the assumption P, A, P, A contradicts the laws of the calculus of probability. Writing df, A, or more simply d, A, for the dimension of the theory A, with respect to the ELD of application F, we can formulate our theorem as follows. If d, A, d, A, then P, A, P, A. Consequently, P, A, P, A, is incompatible with d, A, d, A. This theorem, which is implied in what has been said in the body of the book, is in keeping with the following considerations. A theory requires a minimum of d, A, plus relative atomic statements for its refutation. Its weakest falsiers, as we may call them, consist of a conjunction of d, A, plus relative atomic statements. This means that if n d, A, then no conjunction of n relative atomic statements is logically strong enough for deriving from them A, that is, the negation of A. The strength or content of A, accordingly, can be measured by d, A, plus, since A will be stronger than any conjunction of d, A, relative atomic statements, but certainly not stronger than some conjunctions of d, A, plus such statements. But from the probability rule, P, A, equals, P, A. We know that the probability of a theory decreases with increasing probability of its negation A, and vice versa, and that the same relations hold between the contents of A and of A. From this we see, again, that d, A, d, A, means that the content of A is greater than that of A, so that d, A, d, A, entails P, A, P, A, and is thus incompatible with P, A, P, A. But this result is nothing but the theorem, derived above. Our theorem has been derived by considering night universes, and it is indeed quite independent of the transition to innate universes. It is therefore independent of the formulae, and, of the preceding appendix, that is to say, of the fact that in an innate universe, we have for any universal law and any night evidence E. P, A, equals P, A, E, equals 0. We may therefore legitimately use, for another derivation of, and this can indeed be done, if we utilize an idea due to Dorothy Rinch and Harold Juries. As Bree indicated in the preceding appendix, Rinch and Juries observed that if we have an entity of mutually incompatible or exclusive explanatory theories, the sum of the probabilities of these theories cannot exceed unity, so that almost all of these probabilities must be 0, unless we can order the theories in a sequence, and assign to each, as its probability, a value from a convergent sequence of fractions whose sum does not exceed. For example, we may make the following assignments. We may assign the value / to the RST theory, / to the second, and, generally, / n to the nth. But we may also assign to each of the RST theories the value /0, that is to say, / to each of the next 0, say, the value /00, that is to say, /.00, and so on. However we may construct the order of the theories and however we may assign our probabilities to them, there will always be some greatest probability value, p say, such as / in our RST example, or /0, and this value p will be assigned to at most n theories, where n is a night number, and n.p. Each of these n theories to which the maximum probability p has been assigned, has a dimension. Let d be the largest dimension present among these n theories, and let a be one of them, with d, a, equals d. Then, clearly, none of the theories with dimensions greater than d will be among our n theories with maximum probability. Let a be a theory with a dimension greater than d, so that d, a, d equals d, a. Then the assignment leads to d, a, d, a, and p, a, p, a. This result shows that our theorem is violated. But an assignment of the kind described which leads to this result is unavoidable if we wish to avoid assigning the same probability, that is, 0, to all theories. Consequently, our theorem entails the assignment of 0 probabilities to all theories. Rinch and Juries themselves arrived at a very different result. They believed that the possibility of empirical knowledge required the possibility of raising the probability of a law by accumulating evidence in its favor. From this they concluded that must be false, and further, that a legitimate method must exist of assigning non-zero probabilities to an innate sequence of explanatory theories. Thus Rinch and Juries drew very strong positive conclusions from the transcendental argument, as I called it in the preceding appendix. Believing, as they did, that an increase in probability means an increase in knowledge, so that obtaining a high probability becomes an aim of science, they did not consider the possibility that we may learn from experience more and more about universal laws without ever increasing their probability, that we may test and corroborate some of them better and better, thereby increasing their degree of corroboration without altering their probability whose value remains 0. Juries and Rinch never described the sequence of theories, and the assignment of probability values, in a sufficiently clear way. Their main idea, called the simplicity postulate, was that the theories should be so ordered that their complexity, or number of parameters, increases, while the probabilities which they assign to them decrease. This, incidentally, would mean that any two theories of the sequence would violate our theorem. But this way of ordering cannot be carried through, as Juries himself noticed. For there may be theories with the same number of parameters. Juries himself gives as examples y equals x and y equals x, and he says of them, laws involving the same number of parameters can be taken as having the same prior probability. But the number of laws having the same prior probability is innate, for Juries' own examples can be continued to infinity, y equals x, y equals x, y equals x, and so on, with n registered trademark yen. Thus for each number of parament ERS, the same problem would recur as for the whole sequence. Moreover, Juries himself recognizes, in the same point 0, that a law, A, say, may be obtained from a law A with one additional parameter, by assuming that parameter to be equal to 0, and that in this case, P, A, since A is a special case of A, so that fewer possibilities belong to A. Thus in this special case, he recognizes that a theory with fewer parameters will be less probable than one with more parameters in agreement with our theorem. But he recognizes this fact only in this special case, and he does not comment at all on the fact that a contradiction may well arise between his simplicity postulate and this case. Altogether, he nowhere tries to show that the simplicity postulate is consistent with his axiom system, but in view of the special case mentioned, which of course follows from his axiom system, it should have been clear that a proof of consistency was urgently needed. Our own considerations show that a consistency proof cannot be given, and that the simplicity postulate must contradict every adequate axiom system for probability, for it must violate our theorem. In concluding this appendix, I wish to attempt something like an explanation why Rinch and Juries may have regarded their simplicity postulate as harmless as unable to create trouble. It should be kept in mind that they were the RST to identify simplicity and paucity of parameters. I do not simply identify these two, I distinguish between a formal and a material reduction in the number of the parameters cf sections 0, and intuitive simplicity. Thus becomes something like formal simplicity, but otherwise my theory of simplicity agrees with that of Rinch and Juries in this point. They also saw clearly that simplicity is one of the things aimed at by scientists, that these prefer a simpler theory to a more complicated one, and that they therefore try the simplest theories RST. On all these points, Rinch and Juries were right. They were also right in believing that there are comparatively few simple theories, and many complex ones whose numbers increase with the number of their parameters. This last fact may have led them to believe that the complex theories were the less probable ones, since the available probability was somehow to be divided among the various theories. And since they also assumed that a high degree of probability was indicative of a high degree of knowledge and therefore was one of the scientists' aims, they may have thought that it was intuitively evident that the simpler, and therefore more desirable, theory was to be identified with the more probable, and therefore more desirable, theory, for otherwise the aims of the scientist would become inconsistent. Thus the simplicity postulate appeared to be necessary on intuitive grounds and therefore a fortiori consistent. But once we realize that the scientist does not and cannot aim at a high degree of probability, and that the opposite impression is due to mistaking the intuitive idea of probability for another intuitive idea, here labeled degree of corroboration, 0, it will also become clear to us that simplicity, or paucity of parameters, is linked with, and tends to increase with, improbability rather than probability. And so it will also become clear to us that a high degree of simplicity is nevertheless linked with a high degree of corroboration. For a high degree of testability or corroborability is the same as a high prior improbability or simplicity. The problem of corroboration will be discussed in the next appendix. Addendum. If we remember what has been said in the old appendix I, p, about the dimension of a theory, a, relative to a eld f, that is, df, a, and what has been said in the present appendix about the weakest falsiers of a theory, we can introduce a measure of the simplicity or the content of a relative to f, CTF, a, as follows. CTF, a, equals / df, a, plus. This is a measure of the NE structure of the content of a theory, relative to f, for it may be applicable where the probabilities become indistinguishable, because p, a, equals 0. Incidentally, simplicity should always be regarded as relative to a given problem of explanation. See note to chapter 0, p, of my conjectures and refutations, in the revised, 2nd edition, and later, dot. Addendum. We sometimes discover a new connection between scientific problems. Thus if the simplicity of a theory is relative to the problems which the theory tries to solve, then it is, to some degree, also relative to the historical problem situation. With this it becomes clear that the problems of the content and simplicity of a theory may change in the course of the historical development of a science. Appendix 9. Corroboration, the weight of evidence, and statistical tests. The 3 notes reprinted below in the present appendix were originally published in the British Journal for the Philosophy of Science. Even before my book was published, I felt that the problem of degree of corroboration was one of those problems which should be further investigated. By the problem of degree of corroboration I mean the problem, of showing that there exists a measure, to be called degree of corroboration, of the severity of tests to which a theory has been subjected, and of the manner in which it has passed these tests, or failed them, and, 2, of showing that this measure cannot be a probability, or more precisely, that it does not satisfy the formal laws of the probability calculus. An outline of the solution of both of these tasks, especially the second, was contained in my book. But I felt that a little more was needed. It was not quite enough to show the failure of the existing theories of probability of Keynes and of Juries, for example, or of Caille, or of Reichenbach, none of whom could establish even their central doctrine, that a universal law, or a theory, could ever reach a probability / They even failed to establish that a universal law, or a theory, could ever have a probability other than zero. What was needed was a perfectly general treatment. I therefore aimed at constructing a formal probability calculus which could be interpreted in various senses. I had in mind, the logical sense, outlined in my book as, absolute, logical probability of statements, 2, the sense of relative logical probability of statements or propositions, as envisaged by Kuhn, 3, the sense of a calculus of relative frequencies in sequences. 4, the sense of a calculus of a measure of ranges, or of predicates, classes, or sets. The ultimate aim was, of course, to show that degree of corroboration was not a probability, that is to say that it was not one of the possible interpretations of the probability calculus. Yet I realized that the task of constructing a formal calculus was not only needed for this purpose, but was interesting in itself. This led to my paper in Mind, reprinted here as Appendix 2, and to other work extending over many years and aimed both at simplifying my axiom systems and at producing a probability calculus in which P, A, B, the probability of a given B could have d-night values, rather than 0/0, even if P, B, was equal to 0. The problem arises, of course, because the definition P, A, B, equals P, A, B/P, B, breaks down if P, B, equals 0. A solution of this last problem was needed because I soon found that, in order to define C, X, Y, the degree of corroboration of the theory X by the evidence Y, I had to operate with some converse P, Y, X, called by Fisher the likelihood of X, in the light of the evidence Y, or given Y. Note that both, my corroboration and Fisher's likelihood, are intended to measure the acceptability of the hypothesis X. It is thus X which is important, while Y represents merely the changing empirical evidence, or, as I prefer to say, the reports of the results of tests. Now I was convinced that, if X is a theory, P, X, equals 0. I saw therefore that I had to construct a new probability calculus in which the likelihood, P, Y, X, could be a d-night number, other than 0/0, even if X was a universal theory with P, X, equals 0. I will now explain how the problem of P, Y, X, of the likelihood of X arises. If we are asked to give a criterion of the fact that the evidence Y supports or corroborates or confirms a statement X, the most obvious reply is, that Y increases the probability of X. We can put this in symbols if we write CO, X, Y, for X is supported or corroborated or confirmed by Y. We then can formulate our criterion as follows. CO, X, Y, if, and only if, P, X, Y, P, X. This formulation, however, has a defect. For if X is a universal theory and Y some empirical evidence, then, as we have seen in the two preceding appendices, P, X, equals 0 equals P, X, Y. But from this it would follow that, for a theory X and evidence Y, CO, X, Y, is always false, or in other words, that a universal law can never be supported or corroborated or confirmed by empirical evidence. This holds not only for an infinite universe but also for any extremely large universe, such as ours, for in this case, P, X, Y and P, X, will be both immeasurably small, and thus practically equal. This difficulty however can be got over, as follows. Whenever P, X, superscript 1, 0 superscript 1 P, Y, we have 3, P, X, Y, P, X, if, and only if, P, Y, X, P, Y. So that we can transform, into 4, CO, X, Y, if, and only if, P, X, Y, P, X, or P, Y, X, P, Y. Now let X be again a universal law, and let Y be empirical evidence which, say, follows from X. In this case, that is whenever y follows from x, we shall say, intuitively, that p, y, x, equals. And since y is empirical, so that p, y, will certainly be less than, we nd that, can be applied. And that the assertion co, x, y, will be true. That is to say, x may be corroborated by y if y follows from x, provided only that p, y. Thus, 4 is intuitively perfectly satisfactory, but in order to operate freely with, we have to have a calculus of probability in which p, y, x, is a finite number in our case, rather than 0/0, even if p, x, equals 0. In order to achieve this, a generalization of the usual calculus has to be provided, as explained above. Although I had realized this by the time my note in mind appeared, cf. Appendix 2, the pressure of other work which I considered more urgent prevented me from completing my researches in this eld. It was only in that I published my results concerning degree of corroboration, in the RST of the notes here reprinted, and another 6 months elapsed before I published an axiom system of relative probability, equivalent to, though less simple than, the one which will be found in Appendix 4, which satisfies the demand that p, x, y, should be a finite number even if p, y, was equal to 0. This paper provided the technical prerequisites for a satisfactory definition of likelihood and of degree of corroboration or confirmation. My RST note degree of confirmation, published in the BJPS, contains a mathematical refutation of all those theories of induction which identify the degree to which a statement is supported or confirmed or corroborated by empirical tests with its degree of probability in the sense of the calculus of probability. The refutation consists in showing that if we identify degree of corroboration or confirmation with probability, we should be forced to adopt a number of highly paradoxical views, among them the following clearly self-contradictory assertion. There are cases in which x is strongly supported by z and y is strongly undermined by z while, at the same time, x is confirmed by z to a lesser degree than is y. A simple example, showing that this devastating consequence would follow if we were to identify corroboration or confirmation with probability, will be found under point of my RST note. In view of the brevity of that passage, I may perhaps explain this point here again. Consider the next throw with a homogeneous die. Let x be the statement 6 will turn up, let y be its negation, that is to say, let y equals x, and let z be the information an even number will turn up. We have the following absolute probabilities. P, x, equals slash, P, y, equals slash, P, z, equals slash. Moreover, we have the following relative probabilities. P, x, z, equals slash, P, y, z, equals slash. We see that x is supported by the information z, for z raises the probability of x from slash to slash equals slash. We also see that y is undermined by z, for z lowers the probability of y by the same amount from slash to slash equals slash. Nevertheless, we have p, x, z, p, y, z. This example proves the following theorem. 5. There exist statements x, y, and z, which satisfy the formula p, x, z, p, x, and p, y, z, p, y, and p, x, z, p, y, z. Obviously, we may replace here p, y, z, p, y, by the weaker p, y, z, p, y. This theorem is, of course, far from being paradoxical. And the same holds for its corollary, which we obtain by substituting for p, x, z, p, x, and p, y, z, p, y, the expressions co, x, z, and co, y, z, that is to say non-co, y, z, respectively, in accordance with formula, above. 6. There exist statements x, y, and z which satisfy the formula co, x, z, and co, y, z, and p, x, z, p, y, z. Like, theorem, expresses a fact we have established by our example, that x may be supported by z, and y undermined by z, and that nevertheless x, given z, may be less probable than y, given z. There at once arises, however, a clear self-contradiction if we now identify in degree of confirmation c, a, b, and probability p, a, b. In other words, the formula CO, x, z, and CO, y, z, and c, x, z, c, y, z. That is, z conreams x but not y, yet z also conreams x to a lesser degree than y, is clearly self-contradictory. Thus we have proved that the identification of degree of corroboration or confirmation with probability, and even with likelihood, is absurd on both formal and intuitive grounds. It leads to self-contradiction. Here degree of corroboration or confirmation may be taken in a sense wider than the one I usually have in mind. While I usually take it to be a synonym for degree of severity of the tests which a theory has passed, it is here used merely as degree to which a statement X is supported by a statement Y. If we look at this proof, then we see that it depends upon two assumptions only. A. Formula. B. The assumption that any assertion of the following form is self-contradictory. X has the property P, for example, the property warm, and Y has not the property P, and Y has the property P in a higher degree than X, for example, Y is warmer than X. Every careful reader of my RST note, and especially of the example given under point, will nd that all this is clearly implied there, except perhaps the general formulation of the contradictions, and admittedly it is put here in a more explicit form, but the purpose of my note was not so much to criticize as to give a definition of degree of corroboration. The criticism contained in my note was directed against all those who identify, explicitly or implicitly, degree of corroboration, or of confirmation, or of acceptability, with probability. The philosophers I had in mind were especially Keynes, Juries, Reichenbach, Keil, Josiassen and, more recently, Carnap. As to Carnap, I wrote a critical footnote which, I believe, speaks for itself. It was motivated by the fact that Carnap, in stating adequacy criteria for degree of confirmation, speaks of the consensus of practically all modern theories of degree of confirmation, but does not mention my dissent, in spite of the fact that he introduced the English term degree of confirmation as a translation of my term grad der Bewahrung. Cf the footnote before section, above. Moreover, I wish to point out that his division of probability into probability, equals his degree of confirmation, and probability, equals statistical frequency, was insouciant, that there were at the very least two interpretations of the calculus of probability, the logical and the statistical, and that, in addition, there was my degree of corroboration which was not a probability, as has now been shown here, and as was shown in my note. It seems that this 10-line footnote of mine has drawn more attention to itself than the rest of my note. It led to a discussion in the BJPS in which Bar Hillel asserted that my criticism of what he termed the current theory of confirmation, i.e. Carnap's theory, was purely verbal and that all I had to say was anticipated by Carnap, and it led to a review of my paper in the Journal of Symbolic Logic in which Kemeny summed up my note by the words, "The principal thesis of this paper is that Carnap's proposed measurers of degree of confirmation, or any other assignment of logical probability, are not suited to measure degrees of confirmation." This was certainly not my principal thesis. My note was a continuation of some work of mine published 15 years before Carnap's book was written, and as far as criticism is concerned, the point at issue, the identification of corroboration or confirmation or acceptability with probability, though it is of course the main thesis of Carnap's book, is far from being an original thesis of Carnap's, for he is here merely following the tradition of Keynes, Juries, Reichenbach, Keil, Josiassen, and others. Moreover, both Bar Hillel and Kemeny suggest that this criticism, as far as it applies to Carnap's theory, is purely verbal, and that there is no reason why Carnap's theory should be given up, and I therefore feel compelled to say now quite clearly that Carnap's theory is self-contradictory, and that its contradictoriness is not a minor matter which can be easily repaired, but is due to mistakes in its logical foundations. First, both the assumptions, A, and, B, which, as we have seen, sus for the proof that degree of confirmation must not be identified with probability, are explicitly asserted in Carnap's theory. A, that is to say our formula, can be found in Carnap's book as formula, on P. B, that is to say, or the assumption that R, is self-contradictory, can be found on P. Of Carnap's book where he writes, if the property warm and the relation warmer were designated by, say, P and R, then Pa PB.RBA would be self-contradictory. But this is R. Of course, in a way it is quite irrelevant to my argument that shows the absurdity of the identification of C and P whether or not, A, and, B, are explicitly admitted in a book, but it so happens that in Carnap's book, they are. Moreover, the contradiction here explained is crucial for Carnap, by accepting, or more precisely, by denning on pp. Fx is con Rmed by y with the help of p, x, y, p, x. In our symbolism, Carnap shows that the intended meaning of degree of confirmation, his explicandum, is, roughly, the same as the one intended by myself. It is the intuitive idea of degree of support by empirical evidence. Kemeny Loccit is mistaken when he suggests the opposite. In fact, a careful reading of my paper and, I should add, of Carnap's book will not show that Popper and Carnap have two different explicanda in mind, but it will show that Carnap had inadvertently two different and incompatible explicanda in mind with his probability, one of them my C, the other my P, and it will show that I have repeatedly pointed out the dangers of this confusion, for example in the paper reviewed by Kemeny. Therefore, any change of assumption, A, would be ad hoc. It is not my criticism that is purely verbal, but the attempts to rescue the current theory of confirmation. For further details, I must refer to the discussion in the pages of the BJPS. I may say that I was a little disappointed both by this discussion and by Kemeny's review in the Journal of Symbolic Logic. From a rational point of view, the situation appears to me quite serious. In this post-rationalist age of ours, more and more books are written in symbolic languages, and it becomes more and more difficult to see why, what it is all about, and why it should be necessary, or advantageous, to allow oneself to be bored by volumes of symbolic trivialities. It almost seems as if the symbolism were becoming a value in itself, to be revered for its sublime exactness, a new expression of the old quest for certainty, a new symbolic ritual, a new substitute for religion. Yet the only possible value of this kind of thing, the only possible excuse for its dubious claim to exactness seems to be this. Once a mistake, or a contradiction, is pinpointed, there can be no verbal evasion, it can be proved, and that is that. Frege did not try evasive maneuvers when he received Russell's criticism. So if one has to put up with a lot of tiresome technicalities, and with a formalism of unnecessary complex ity, one might at least hope to be compensated by the ready acceptance of a straightforward proof of contradictoriness, a proof consisting of the simplest of counterexamples. It was disappointing to be met, instead, by merely verbal evasions, combined with the assertion that the criticism aired was merely verbal. Still, one must not be impatient. Since Aristotle, the riddle of induction has turned many philosophers to irrationalism, to skepticism, or to mysticism. And although the philosophy of the identity of C and P seems to have weathered many a storm since Laplace, I still think that it will be abandoned one day. I really cannot bring myself to believe that the defenders of the faith will be satisfied forever with mysticism and Hegelianism, upholding C equals P as a self-evident axiom, or as the dazzling object of an inductive intuition. I say dazzling because it seems to be an object whose beholders are smitten with blindness when running into its logical contradictions. I may perhaps say here that I regard the doctrine that degree of Corroboration or acceptability cannot be a probability as one of the more interesting endings of the philosophy of knowledge. It can be put very simply like this. A report of the result of testing a theory can be summed up by an appraisal. This can take the form of assigning some degree of corroboration to the theory. But it can never take the form of assigning to it a degree of probability, for the probability of a statement, given some test statements, simply does not express an appraisal of the severity of the tests a theory has passed, or of the manner in which it has passed these tests. The main reason for this is that the content of a theory which is the same as its improbability determines its testability and its corroborability. I believe that these two ideas, content and degree of corroboration, are the most important logical tools developed in my book. So much by way of introduction. In the 3 notes which follow here I have left the word confirmation even where I should now only write corroboration. I have also left p, x, where I now usually write p, x. But I have corrected some misprints, and I have added a few footnotes, preceded by stars, and also 2 new points, and, to the end of the 3rd note. Degree of confirmation. 1. The purpose of this note is to propose and to discuss a definition, in terms of probabilities, of the degree to which a statement X is confirmed by a statement Y. Obviously this may be taken to be identical with the degree to which a statement Y confirms a statement X. I shall denote this degree by the symbol C, X, Y, to be pronounced the degree of confirmation of X by Y. In particular cases, X may be a hypothesis, H, and Y may be some empirical evidence, E, in favor of H, or against H, or neutral with respect to H. But C, X, Y, will be applicable to less typical cases also. The definition is to be in terms of probabilities. I shall make use of both, P, X, Y, i.e. the relative probability of X given Y, and P, X, i.e. the absolute probability of X. But either of these two would be sufficient. 2. It is often assumed that the degree of confirmation of X by Y must be the same as the relative probability of X given Y, i.e. that C, X, Y, equals P, X, Y. My RST task is to show the inadequacy of this view. 3. Consider 2 contingent statements, X and Y. From the point of view of the confirmation of X by Y, there will be 2 extreme cases: the complete support of X by Y or the establishment of X by Y, when X follows from Y, and the complete undermining or refutation or disestablishment of X by Y, when X follows from Y. A third case of special importance is that of mutual independence or irrelevance, characterized by P, X, Y, equals P, X, P, Y. Its value of C, X, Y, will lie below establishment and above disestablishment. Between these 3 special cases, establishment, independence, and disestablishment, there will be intermediate cases, partial support, when Y entails part of the content of X. For example, if our contingent Y follows from X but not vice versa, then it is itself part of the content of X, and thus entails part of the content of X, supporting X, and partial undermining of X by Y, when Y partially supports X. For example, if Y follows from X, we shall say, then, that Y supports X, or that it undermines X, whenever P, XY, or P, XY, respectively, exceed their values for independence. The 3 cases support, undermining, independence are easily seen to be exhaustive and exclusive in view of this definition. 4. Consider now the conjecture that there are 3 statements, X, X, and Y, such that, I, X and X are each independent of Y, or undermined by Y, while, 2, Y supports their conjunction X, X. Obviously, we should have to say in such a case that Y confirms X, X to a higher degree than it confirms either X or X, in symbols. C, X, Y, C, X, X, Y, C, X, Y. But this would be incompatible with the view that C, X, Y, is a probability, i.e. with C, X, Y, equals p, x, y. Since for probabilities we have the generally valid formula dot p, x, y, p, x, x, y, p, x, y, which, in the presence of dot, contradicts dot. Thus we should have to drop dot. But in view of 0 p, x, y, dot, is an immediate consequence of the general multiplication principle for probabilities. Thus we should have to discard such a principle for the degree of confirmation. Moreover, it appears that we should have to drop the special addition principle also. For a consequence of this principle is, since p, x, y, 0. Dot. P, xx or xx, y, p, xx, y. But for c, x, y, this could not remain valid, considering that the alternative xx or xx is equivalent to x, so that we obtain by substitution on the left-hand side of dot dot c, xx or xx, y, c, xx, y. In the presence of dot dot contradicts dot. 5. These results depend upon the conjecture that statements x, x, and y exist such that I, x and x are each independent of y, or undermined by y, while 2. Y supports xx. I shall prove this conjecture by an example. Take colored counters, called A, B, with 4 exclusive and equally probable properties, blue, green, red, and yellow. Let x be the statement A is blue or green, x equals A is blue or red, y equals A is blue or yellow. Then all our conditions are satisfied. That y supports xx is obvious, y follows from xx, and its presence raises the probability of xx to twice the value it has in the absence of y. 6. But we may even construct a more striking example to show the inadequacy of identifying c, x, y, and p, x, y. We choose x so that it is strongly supported by y, and x so that it is strongly undermined by y. Thus we shall have to demand that c, x, y, c, x, y. But x and x can be so chosen that p, x, y, p, x, y. The example is this: take x equals A is blue, x equals A is not red, and y equals A is not yellow. Then p, x, equals slash, p, x, equals slash, and slash equals p, x, y, p, x, y, equals slash. That y supports x and undermines x is clear from these gers, and also from the fact that y follows from x and also from x. 7. Why have c, x, y, and p, x, y, been confounded so persistently? Why has it not been seen that it is absurd to say that some evidence y of which x is completely independent can yet strongly confirm x? And that y can strongly confirm x, even if y undermines x? And this even if y is the total available evidence? I do not know the answer to these questions, but I can make a few suggestions. First, there is the powerful tendency to think that whatever may be called the likelihood or probability of a hypothesis must be a probability in the sense of the calculus of probabilities. In order to disentangle the various issues here involved, I distinguished 20 years ago what I then called the degree of confirmation from both the logical and the statistical probability. But unfortunately, the term degree of confirmation was soon used by others as a new name for logical probability, perhaps under the influence of the mistaken view that science, unable to attain certainty, must aim at a kind of ersatz at the highest attainable probability. Another suggestion is this. It seems that the phrase the degree of confirmation of x by y was turned round into the degree to which y confirms x, or the power of y to support x. Yet in this form it would have been quite obvious that, in a case in which y supports x and undermines x, c, x, y, c, x, y, is absurd, although p, x, y, p, x, y, may be quite in order, indicating, in such a case, that we had p, x, p, x, to start with. Furthermore, there seems to be a tendency to confuse measures of increase or decrease with the measures that increase and decrease, as shown by the history of the concepts of velocity, acceleration, and force. But the power of y to support x, it will be seen, is essentially a measure of the increase or decrease due to y, in the probability of x, see also, 7, below. 8. It will perhaps be said, in reply to all this, that it is in any case legitimate to call p, x, y, by any name, and also by the name degree of confirmation. But the question before us is not a verbal one. The degree of confirmation of a hypothesis x by empirical evidence y is supposed to be used for estimating the degree to which x is backed by experience. But p, x, y, cannot serve this purpose, since p, x, y, may be higher than p, x, y, even though x is undermined by y and x supported by y, and since this is due to the fact that p, x, y, depends very strongly upon p, x, i.e. the absolute probability of x, which has nothing whatever to do with the empirical evidence. Furthermore, the degree of confirmation is supposed to have an influence upon the question whether we should accept, or choose, a certain hypothesis x, if only tentatively. A high degree of confirmation is supposed to characterize a hypothesis as good, or acceptable, while a disconfirmed hypothesis is supposed to be bad. But p, x, y, cannot help here. Science does not aim, primarily, at high probabilities. It aims at a high informative content, well backed by experience. But a hypothesis may be very probable simply because it tells us nothing, or very little. A high degree of probability is therefore not an indication of goodness, it may be merely a symptom of low informative content. On the other hand, c, x, y, must, and can, be so deemed that only hypotheses with a high informative content can reach high degrees of confirmation. The confirmability of x, i.e. the maximum degree of confirmation which a statement x can reach, should increase with c, x, i.e. the measure of the content of x, which is equal to p, x, and therefore to the degree of testability of x. Thus, while p, x, x, y, equals, c, x, x, y, should be 0. 9. A definition of c, x, y, that satisfies all these and other desiderata indicated in my logic der first Chung, and stronger ones besides, may be based upon a, x, y, i.e. a non-additive measure of the explanatory power of x with respect to y, designed so as to have, and end as its lower and upper bounds. It is deemed as follows. Let x be consistent, and p, y, superscript 1 0, then we deem p, y, x, p, y, e, x, y, equals p, y, x, plus p, y, e, x, y, may also be interpreted as a non-additive measure of the dependence of y upon x, or the support given to y by x, and vice versa. It satisfies the most important of our desiderata, but not all. For example, it violates 8, c, below, and satisfies 3, and 4, only approximately in special cases. To remedy these defects, I propose to deem c, x, y, as follows. Let x be consistent and p, y, superscript 1 0, then we deem c, x, y, equals e, x, y, plus p, x, p, x, y. This is less simple than, for example, e, x, y, plus p, x, y, which satisfies most of our desiderata but violates 4, while for c, x, y, the theorem holds that it satisfies all of the following desiderata. I, c, x, y, per 1000 0 respectively if and only if y supports x, or is independent of x, or undermines x. 2, equals c, y, y, c, x, y, c, x, x. 3, 0 c, x, x, equals c, x, equals p, x. Note that c, x, and therefore c, x, x, is an additive measure of the content of x, definable by p, x, i.e. the absolute probability of x to be false, or the a priori likelihood of x to be refuted. Thus confirmability equals refutability or testability. 4. If y entails x, then c, x, y, equals c, x, x, equals c, x. v. If y entails x, then c, x, y, equals c, y, y, equals. 6. Let x have a high content so that c, x, y, approaches e, x, y, and let y support x. We may, for example, take y to be the total available empirical evidence. Then for any given y, c, x, y, increases with the power of x to explain y, i.e. to explain more and more of the content of y, and therefore with the scientific interest of x. 7. If c, x, equals c, y, superscript 1, then c, x, u, per thousand c, y, w, whenever p, x, u, per thousand. P, y, w. 8. If x entails y, then, a, c, x, y, 0, b, for any given x, c, x, y, and c, y, increase together, and, c, for any given y, c, x, y, and p, x, increase together. 9. If x is consistent and entails y, then, a, c, x, y, 0, b, for any given x, c, x, y, and p, y, increase together, and, c, for any given y, c, x, y, and p, x, increase together. 10. All our considerations, without exception, may be relativized with respect to some initial information z, adding at the appropriate places phrases like in the presence of z, assuming p, z, zz, superscript 10. The relativized definition of the degree of confirmation becomes 0. Where 0, c, x, y, z, equals e, x, y, z, plus p, x, z, p, x, y, z, p, y, x, z, p, y, z, e, x, y, z, equals p, y, x, z, plus p, y, z, e, x, y, z, is the explanatory power of x with respect to y, in the presence of z. 11. There are, I believe, some intuitive desiderata which cannot be satisfied by any formal definition. For example, a theory is the better confirmed the more ingenious or unsuccessful attempts at its refutation have been. My definition incorporates something of this idea if not as much as can be formalized. But one cannot completely formalize the idea of a sincere and ingenious attempt. The particular way in which c, x, y, is here deemed I consider unimportant. What may be important are the desiderata, and the fact that they can be satisfied together. A second note on degree of confirmation. The suggestion has been made by Professor J. G. Kemeny, with a reference to my definition of content, and independently by Dr. C. L. Hamblin that the content of x, denoted by c, x, should be measured by log p, x, instead of p, x, as I originally suggested. I am here using my own symbols. If this suggestion is adopted, then my desiderata for degree of confirmation of x by y, denoted by c, x, y, have to be slightly amended. In 2, and in v, we must replace plus or minus by plus or minus yen, and 3 becomes 3, 0 c, x, x, y, equals c, x, x, equals c, x, equals, log p, x, plus yen. The other desiderata remain as they were. Dr. Hamblin suggests that we deem degree of confirmation by C, x, y, equals log, p, x, y, slash p, x, p, y. Which for night systems, but not necessarily for innite systems, is the same as C, x, y, equals log, p, y, x, slash p, y. A formula which has the advantage of remaining determinate even if p, x, equals 0, as may be the case if x is a universal theory. The corresponding relativized formula would be C, x, y, z, equals log, p, y, x z, slash p, y, z. The definition does not, however, satisfy my desideratum 8, c, as Dr. Hamblin observes, and the same holds for, and. Desideratum 9, b, and, c, are also not satisfied. Now my desideratum 8, c, marks, in my opinion, the difference between a measure of explanatory power and one of confirmation. The former may be symmetrical in x and y, the latter not. For let y follow from x, and support x, and let x be unconfirmed by y. In this case it does not seem satisfactory to say that x is always as well confirmed by y as is x, but there does not seem to be any reason why x and x should not have the same explanatory power with respect to y, since y is completely explained by both. This is why I feel that 8, c, should not be dropped. Thus I prefer to look upon, and, as highly adequate definitions of explanatory power of E, x, y and E, x, y, z, rather than of degree of confirmation. The latter may be deemed, on the basis of explanatory power, in many different ways so as to satisfy 8, c. One way is as follows. I think that better ways may be found. C, x, y, equals E, x, y, slash, plus np, x, p, x, y. C, x, y, z, equals E, x, y, z, slash, plus np, x, z, p, x, y, z. Here we may choose n. And if we wish 8, c, to have a marked ect, we can make n a large number. In case x is a universal theory with p, x, equals 0 and y is empirical evi. Denke, the difference between E and C disappears, as in my original definitions, and as demanded by desideratum 6. It also disappears if x follows from y. Thus at least some of the advantages of operating with a logarithmic measure remain, as explained by Hamblin. The concept deemed by becomes closely related to the fundamental idea of information theory. Good also comments on this point, see footnote. The transition from the old to the new definitions is order-preserving. This holds also for explanatory power, as Hamblin's observations imply. Thus the difference is metrical only. 2. The definitions of explanatory power, and even more of degree of confirmation, or corroboration or acceptability or attestation, or whatever name may be chosen for it, give of course full weight to the weight of evidence, or the weight of an argument as Keynes called it in his chapter 6. This becomes obvious with the new definitions, based upon Hamblin's suggestions, which seem to have considerable advantages if we are at all interested in metrical questions. 3. However, we must realize that the metric of RC will depend entirely upon the metric of P. But there cannot be a satisfactory metric of P, that is to say, there cannot be a metric of logical probability which is based upon purely logical considerations. To show this we consider the logical probability of any measurable physical property, non-discrete random variable, such as length, to take the simplest example. We make the assumption, favorable to our opponents, that we are given some logically necessary night lower and upper limits, I and u, to its values. Assume that we are given a distribution function for the logical probability of this property, for example, a generalized equidistribution function between L and U. we may discover that an empirically desirable change of our theories leads to a nonlinear correction of the measure of our physical property, based, say, on the Paris meter. Then logical probability has to be corrected also, which shows that its metric depends upon our empirical knowledge, and that it cannot be deemed a priori, in purely logical terms. In other words, the metric of the logical probability of a measurable property would depend upon the metric of the measurable property itself, and since this latter is liable to correction on the basis of empirical theories, there can be no purely logical measure of probability. These difficulties can be largely, but not entirely, overcome by making use of our background knowledge Z. But they establish, I think, the significance of the topological approach to the problem of both degree of confirmation and logical probability. But, even if we were to discard all metric considerations, we should still adhere, I believe, to the concept of probability, as deemed, implicitly, by the usual axiom systems for probability. These retain their full significance, exactly as pure metrical geometry retains its significance, even though we may not be able to deem a yardstick in terms of pure, metrical, geometry. This is especially important in view of the need to identify logical independence with probabilistic independence, special multiplication theorem. If we assume a language such as Cheminese, which, however, breaks down for continuous properties, or a language with relative atomic statements, as indicated in Appendix N of my Logic of Scientific Discovery, then we shall have to postulate independence for the atomic, or relative atomic, sentences, of course, as far as they are not logically dependent, in Cheminese sense. On the basis of a probabilistic theory of induction, it then turns out that we cannot learn if we identify logical and probabilistic independence in the way here described, but we can learn very well in the sense of my C functions, that is to say, we can corroborate our theories. Two further points may be mentioned in this connection. For the RST point is this. On the basis of my axiom systems for relative probability, P, X, Y, can be considered as deemed for any value of X and Y, including such values for which P, Y, equals 0. More especially, in the logical interpretation of the system, whenever X follows from Y, P, X, Y, equals, even if P, Y, equals 0. There is thus no reason to doubt that our definition works for languages containing both singular statements and universal laws, even if all the latter have zero probability, as is the case, for example, if we employ Cheminese measure function m, by postulating P, X, equals m, X. In the case of our definitions of E and C, there is no need whatever to depart from the assignment of equal weight to the models, cf. Cheminese, OPCITP0. On the contrary, any such departure must be considered as a deviation from a logical interpretation, since it would violate the equality of logical and probabilistic independence demanded in, above. 5. The second point is this. Among the derived desiderata, the following is not satisfied by all definitions of X is confirmed by Y which have been proposed by other authors. It might therefore be mentioned separately as a 10th desideratum. X, if X is confirmed or corroborated or supported by Y so that C, X, Y, 0, then, A, X is always undermined by Y, i.e. C, X, Y, 0, and B, X is always undermined by Y, i.e. C, X, Y, 0. It seems to me clear that this desideratum is an indispensable adequacy condition, and that any proposed definition which does not satisfy it is intuitively paradoxical. A third note on degree of corroboration or confirmation. In this note I wish to make a number of comments on the problem of the weight of evidence, and on statistical tests. 1. The theory of corroboration or confirmation proposed in my two previous notes on degree of confirmation is able to solve with ease the so-called problem of the weight of evidence. This problem was raised by Peirce, and discussed in some detail by Keynes, who usually spoke of the weight of an argument or of the amount of evidence. The term the weight of evidence is taken from J. M. Keynes and from I. J. Good. Considerations of the weight of evidence lead, within the subjective theory of probability, to paradoxes which, in my opinion, are insoluble within the framework of this theory. 2. By the subjective theory of probability, or the subjective interpretation of the calculus of probability, I mean a theory that interprets probability as a measure of our ignorance, or of our partial knowledge, or, say, of the degree of the rationality of our beliefs, in the light of the evidence available to us. I may mention, in parentheses, that the more customary term, degree of rational belief, may be a symptom of a slight confusion, since what is intended is degree of rationality of a belief. The confusion arises as follows. Probability is RST explained as a measure of the strength or intensity of a belief or conviction measurable, say, by our readiness to accept odds in betting. Next, it is realized that the intensity of our belief often depends, in fact, upon our wishes or fears rather than upon rational arguments. Thus, by a slight change, probability is then interpreted as the intensity, or the degree, of a belief in so far as it is rationally justable. But at this stage, the reference to the intensity of a belief, or to its degree, clearly becomes redundant, and degree of belief should therefore be replaced by degree of the rationality of a belief. These remarks should not be taken to mean that I am prepared to accept any form of the subjective interpretation, see point below, and chapter 2 of my postscript, after 20 years. 3. In order to save space, I shall explain the problem of the weight of evidence merely by giving one instance of the paradoxes to which I referred above. It may be called the paradox of ideal evidence. Let Z be a certain penny, and let A be the statement the nth, as yet unobserved, toss of Z will yield heads. Within the subjective theory, it may be assumed that the absolute, or prior, probability of the statement A is equal to slash, that is to say, P, A, equals slash. Now let E be some statistical evidence, that is to say, a statistical report, based upon the observation of thousands or perhaps millions of tosses of Z, and let this evidence E be ideally favorable to the hypothesis that Z is strictly symmetrical, that it is a good penny, with equidistribution. Note that here E is not the full, detailed report about the results of each of these tosses. This report we might assume to have been lost, but only a statistical abstract from the full report. For example, E may be the statement, among a million of observed tosses of Z, heads occurred in 0,000 plus or minus 0 cases. It will be seen, from point below, that an evidence E sent with 0,000 plus or minus 0 cases would still be ideal, if my functions C and E are adopted. Indeed, from the point of view of these functions, E is ideal precisely because it entails E sent. We then have no other option concerning P, A, E, than to assume that P, A, E, equals slash. This means that the probability of tossing heads remains unchanged, in the light of the evidence E, for we now have P, A, equals P, A, E. But according to the subjective theory, means that E is, on the whole, absolutely, irrelevant information with respect to A. Now this is a little startling, for it means, more explicitly, that our so-called degree of rational belief in the hypothesis, A, ought to be completely unaffected by the accumulated evidential knowledge, E, that the absence of any statistical evidence concerning Z justifies precisely the same degree of rational belief as the weighty evidence of millions of observations which, prima facie, support or confirm or strengthen our belief. For I do not think that this paradox can be solved within the framework of the subjective theory, for the following reason. The fundamental postulate of the subjective theory is the postulate that degrees of the rationality of beliefs in the light of evidence exhibit a linear order, that they can be measured, like degrees of temperature, on a one-dimensional scale. But from Pierce to Good, all attempts to solve the problem of the weight of evidence within the framework of the subjective theory proceed by introducing, in addition to probability, another measure of the rationality of belief in the light of evidence. Whether this new measure is called another dimension of probability, or degree of reliability in the light of the evidence, or weight of evidence is quite irrelevant. What is relevant is the implicit admission that it is not possible to attribute linear order to degrees of the rationality of beliefs in the light of the evidence, that there may be more than one way in which evidence may eke the rationality of a belief. This admission is sufficient to overthrow the fundamental postulate on which the subjective theory is based. Thus the naive belief that there really are intrinsically different kinds of entities, some to be called, perhaps, degree of the rationality of belief and others degree of reliability or of evidential support, is no more able to rescue the subjective theory than the equally naive belief that these various measures explicate different explicanda, for the claim that there exists an explicandum here such as degree of rational belief capable of explication in terms of probability, stands or falls with what I have called the fundamental postulate. 5. All these difficulties disappear as soon as we interpret our probabilities objectively. It does not matter, in the context of the present paper, whether the objective interpretation is a purely statistical interpretation or a propensity interpretation. According to the objective interpretation, we have to introduce B, the statement of the conditions of the experiment, the conditions denying the sequence of the experiments from which we take our example. For instance, B may be the information, the toss in question will be a toss of Z, randomized by spinning. Moreover, we have to introduce the objective probabilistic hypothesis H, that is to say, the hypothesis, P, A, B, equals /. From the point of view of the objective theory, what we are mainly interested in is the hypothesis H, that is to say, the statement P, A, B, equals /. 6. If we now consider the ideally favorable statistical evidence E which led to the paradox of ideal evidence, it is quite obvious that from the point of view of the objective theory, E is to be considered as evidence bearing upon H rather than evidence bearing upon A. It is ideally favorable to H, and quite neutral to A. Upon the assumption that the various tosses are independent, or random, the objective theory yields for any statistical evidence E quite naturally P, A, B, equals P, A, B, thus E is indeed irrelevant to A, in the presence of B. Since E is evidence in favor of H, our problem turns, as a matter of course, into the question of how the evidence E corroborates H, or confirms H. The answer is that if E is ideally favorable evidence, then both E, H, E, and C, H, E, i.e. the degree of corroboration of H, given E, will approach, if the size of the sample upon which E is based goes to infinity. Thus ideal evidence produces a correspondingly ideal behavior of E and C. Consequently, no paradox arises, and we may quite naturally measure the weight of the evidence E with respect to the hypothesis H by either E, H, E, or C, H, E, or else keeping more closely to Keynes' idea by the absolute values of either of these functions. 7. If, as in our case, H is a statistical hypothesis, and E the report of the results of statistical tests of H, then C, H, E, is a measure of the degree to which these tests corroborate H, exactly as in the case of a non-statistical hypothesis. It should be mentioned, however, that as opposed to the case of a non-statistical hypothesis, it might sometimes be quite easy to estimate the numerical values of E, H, E, and even of C, H, E, if H is a statistical hypothesis. In I will indicate how such numerical calculations might proceed in simple cases, including, of course, the case of H equals P, A, B, equals dot. The expression P, E, H, P, E is crucial for the functions E, H, E, and C, H, E. Indeed, these functions are nothing but two different ways of normalizing the expression, they thus increase and decrease with. This means that in order to nd a good test statement E1 which, if true, is highly favorable to H, we must construct a statistical report E such that E makes P, E, H, which is Fisher's likelihood of H given E large, i.e. nearly equal to, and such that, 2, E makes P, E, small, i.e. nearly equal to O. Having constructed a test statement E of this kind, we must submit E itself to empirical tests. That is to say, we must try to nd evidence refuting E. Now let H be the statement. P, A, B, equals R. And let E be the statement in a sample which has the size n and which satisfies the condition B, or which is taken at random from the population B, A is satisfied in n, R plus or minus delta, of the instances. Then we may put, especially for small values of delta, P, E, delta. We may even put P, E, equals delta, for this would mean that we assign equal probabilities and therefore, the probability slash, n plus, to each of the n plus proportions, 0 slash n, slash n, n slash n, with which a property A may occur in a sample of the size n. It follows that we should have to assign the probability, P, E, equals, d plus, slash, n plus, to a statistical report E telling us that m plus or minus d members of a population of the size n have the property A, so that putting delta equals, d plus, slash, n plus, we obtain P, E, equals delta. The equidistribution here described is the one which Laplace assumes in the derivation of his rule of succession. It is adequate for assessing the absolute probability, P, E, if E is a statistical report about a sample. But it is inadequate for assessing the relative probability P, E, H, of the same report, given a hypothesis H according to which the sample is the product of an n times repeated experiment whose possible results occur each with a certain probability. For in this case, it is adequate to assume a combinatoric, i.e. a Bernoullian rather than a Laplacian, distribution. We see from that, if we wish to make P, E, small, we have to make delta small. On the other hand, P, E, H, the likelihood of H will be close to either if delta is comparatively large, roughly, if delta slash, or in case delta is small if n, the sample size, is a large number. We therefore nd that P, E, H, P, E, and thus our functions E and C, can only be large if delta is small and n large, or in other words, if E is a statistical report asserting a good T in a large sample. Thus the test statement E will be the better the greater its precision, which will be inverse to delta, and consequently its refutability or content, and the larger the sample size n, that is to say, the statistical material required for testing E. And the test statement E so constructed may then be confronted with the results of actual observations. We see that accumulating statistical evidence will, if favorable, increase E and C accordingly. E or C may be taken as measures of the weight of the evidence in favor of H, or else, their absolute values may be taken as measuring the weight of the evidence with respect to H. 8. Since the numerical value of P, E, H, can be determined with the help of the binomial theorem, or of Laplace's integral, and since especially for a small delta we can, by, put P, E, equal to delta, it is possible to calculate P, E, H, P, E, numerically, and also E. Moreover, we can calculate for any given n a value delta equals P, E, slash for which P, E, H, P, E, would become a maximum. For n equals 0, 0, 0, 0, 0, 0, we obtain delta equals 0.00. Similarly, we can calculate another value, of delta equals P, E, slash, for which E would become a maximum. For the same n, we obtain delta equals 0.00, and E, H, E, equals 0. For a universal law H such that H equals P, A, B, equals which has passed n severe tests, all of them with the result A, we obtain, RST, C, H, E, equals E, H, E, in view of P, H, equals 0, and further, evaluating P, E, with the help of the Laplacian distribution and D equals O, we obtain C, H, E, equals n slash, n plus, equals, slash, n plus. It should be remembered, however, that non-statistical scientific theories have as a rule a form totally different from that of the H here described. Moreover, if they are forced into this form, then any instance A, and therefore the evidence E, would become essentially non-observational. 9. One may see from all this that the testing of a statistical hypothesis is deductive as is that of all other hypotheses. A test statement is constructed in such a way that it follows, or almost follows, from the hypothesis, although its content or testability is high, and afterwards it is confronted with experience. It is interesting to note that if he were chosen so as to be a full report of our observations, say, a full report about a long sequence of tosses, head, tail, etc., a sequence of 1000 elements, then E would be useless as evidence for a statistical hypothesis, for any actual sequence of the length n has the same probability as any other sequence, given h. Thus we should arrive at the same value for p, e, h, and thus for E and C, viz. E equals C equals 0 whether E contains, say, only heads, or whether it contains exactly half heads and half tails. This shows that we cannot use, as evidence for or against H, our total observational knowledge, but that we must extract, from our observational knowledge, such statistical statements as can be compared with statements which either follow from H, or which have at least a high probability, given H. Thus if E consists of the complete results of a long sequence of tosses, then E is, in this form, completely useless as a test statement of a statistical hypothesis. But a logically weaker statement of the average frequency of heads, extracted from the same E, could be used. For a probabilistic hypothesis can explain only statistically interpreted endings, and it can therefore be tested and corroborated only by statistical abstracts and not, for example, by the total available evidence, if this consists of a full observation report, not even if it's various. Statistical interpretations may be used as excellent and weighty test statements. Thus our analysis shows that statistical methods are essentially hypothetical deductive, and that they proceed by the elimination of inadequate hypotheses as do all other methods of science. 10. If delta is very small, and therefore also p, e, which is possible only for large samples, then we have, in view of p, e, h, p, e, h, p, e. In this case, and only in this case, it will therefore be possible to accept Fisher's likelihood function as an adequate measure of degree of corroboration. We can interpret, vice versa, our measure of degree of corroboration as a generalization of Fisher's likelihood function, a generalization which covers cases, such as a comparatively large delta, in which Fisher's likelihood function would become clearly inadequate. For the likelihood of H in the light of the statistical evidence E should certainly not reach a value close to its maximum merely because, or partly because, the available statistical evidence E was lacking in precision. It is unsatisfactory, not to say paradoxical, that statistical evidence E, based upon 1,000,000 tosses and delta equals 0.00, may result in numerically the same likelihood, i.e. p, e, h, equals 0.0 as would statistical evidence E sent, based on only 100 tosses and delta equals 0. But it is quite satisfactory to ND that E, H, E, equals 0 while E, H, E sent, equals 0.0. 11. It should be noticed that the absolute logical probability of a universal law H, that is, P, H, will be in general 0, in an inite universe. For this reason, P, E, H, that is, the likelihood of H will become infinite, in most systems of probability, since in most systems P, E, H, is deemed as P, E, slash P, H, equals 0/0. We therefore need a formal calculus of probability which yields finite values for P, E, H, even if P, H, equals 0, and which will always and unambiguously yield P, E, H, equals whenever E follows, or almost follows, from H. A system answering these demands was published by me some time ago. 12. Re, H, E, may be adequately interpreted as a measure of the explanatory power of H with respect to E, even if E is not a report of genuine and sincere attempts to refute H. But RC, H, E, can be adequately interpreted as degree of corroboration of H or of the rationality of our belief in H, in the light of tests only if E consists of reports of the outcome of sincere attempts to refute H, rather than of attempts to verify H. As hinted in the preceding sentence, I suggest that, while it is a mistake to think that probability may be interpreted as a measure of the rationality of our beliefs, this interpretation is excluded by the paradox of perfect evidence. Degree of corroboration may be so interpreted. As to the calculus of probability, it has a very large number of different interpretations. Although degree of rational belief is not among them, there is a logical interpretation which takes probability as a generalization of deducibility. But this probability logic has little to do with our hypothetical estimates of chances or of odds, for the probability statements in which we express these estimates are always hypothetical appraisals of the objective possibilities inherent in the particular situation in the objective conditions of the situation, for example in the experimental setup. These hypothetical estimates, which are not derivable from anything else, but freely conjectured, although they may be suggested by symmetry considerations, or by statistical material, can in many important cases be submitted to statistical tests. They are never estimates of our own nescience. The opposite view, as Poincaré saw so clearly, is the consequence of a, possibly unconscious, determinist view of the world. 0. From this point of view, a rational gambler always tries to estimate the objective odds. The odds which he is ready to accept do not represent a measure of his degree of belief, as is usually assumed, but they are, rather, the object of his belief. He believes that there are, objectively, such odds. He believes in a probabilistic hypothesis H. If we wish to measure, behavioristically, the degree of his belief, in these odds or in anything else, then we might have to nd out, perhaps, what proportion of his fortune he is ready to risk on a 1-to-1 bet that his belief, his estimate of the odds was correct, provided that this can be ascertained. As to degree of corroboration, it is nothing but a measure of the degree to which a hypothesis H has been tested, and of the degree to which it has stood up to tests. It must not be interpreted, therefore, as a degree of the rationality of our belief in the truth of H. Indeed, we know that C, H, E, equals 0 whenever H is logically true. Rather, it is a measure of the rationality of accepting, tentatively, a problematic guess, knowing that it is a guess but one that has undergone searching examinations. The foregoing 12 points constitute the third note, as published in the BJPS. 2 further remarks may be added, in order to make more explicit some of the more formal considerations which are implicit in this note. The RST problem I have in mind is, again, that of the metric of logical probability, cf. the second note, point, and its relation to the distinction between what I am going to call primary and secondary probability statements. My thesis is that on the secondary level, Laplace's and Bernoulli's distribution provide us with a metric. We may operate with a system S equals A, B, C, A, B, C, of elements. In the sense of our system of postulates in Appendix 4. These elements will give rise to probability statements of the form P, A, B, equals R. We may call them primary probability statements. These primary probability statements may now be considered as the elements of a secondary system of elements, S equals E, F, G, H, so that E, F, etc., are now names of statements of the form P, A, B, equals R. Now Bernoulli's theorem tells us, roughly, the following: let H be P, A, B, equals R, then if H is true, it is extremely probable that in a long sequence of repetitions of the conditions B, the frequency of the occurrence of A will be equal to R, or very nearly so. Let delta R, A, n denote the statement that A will occur in a long sequence of n repetitions with a frequency R plus or minus delta. Then Bernoulli's theorem says that the probability of delta R, A, n will approach, with growing n, given H, i.e. given that P, A, B, equals R, it also says that this probability will approach 0, given that P, A, B, equals S, wherever S falls outside R plus or minus delta, which is important for the refutation of probabilistic hypotheses. Now this means that we may write Bernoulli's theorem in the form of a secondary statement of relative probability about elements G and H of S, that is to say, we can write it in the form lim P, G, H, equals N registered trademark yen, where G equals delta R, A, N, and where H is the information that P, A, B, equals R, that is to say, H is a primary probability statement and G is a primary statement of relative frequency. These considerations show that we have to admit, in S, frequency statements such as G, that is to say, delta R, A, N, and probabilistic assumptions, or hypothetical probabilistic estimates, such as H. It seems for this raison proper, in the interest of a homogeneous S, to identify all the probability statements which form the elements of S, with frequency statements, or in other words, to assume, for the primary probability statements E, F, G, H, which form the elements of S, some kind of frequency interpretation of probability. At the same time, we may assume the logical interpretation of probability for the probability statements of the form P, G, H, equals R. That is to say, for the secondary probability statements which make assertions about the degree of probability of the primary probability statements G and H. Although we may not have a logical, or absolute, metric of the primary probability statements, that is to say, although we may have no idea of the value of P, A, or of P, B, we may have a logical or absolute metric of the secondary probability statements. This is provided by the Laplacian distribution, according to which P, G, the absolute probability of G, that is to say of delta R, A, N, equals delta, whether G is empirically observed, or a hypothesis, so that the typical probabilistic hypothesis, H, gets P, H, equals 0, because H has the form P, A, B, equals R, with delta equals 0. Since Bernoulli's methods allow us to calculate the value of the relative probability P, G, H, by pure mathematical analysis, we may consider the relative probabilities P, G, H, as likewise determined on purely logical grounds. It therefore seems entirely adequate to adopt, on the secondary level, the logical interpretation of the formal calculus of probability. To sum up, we may consider the methods of Bernoulli and Laplace as directed towards the establishment of a purely logical metric of probabilities on the secondary level, independently of whether or not there exists a logical metric of probabilities on the primary level. Bernoulli's methods determine thereby the logical metric of relative probabilities, secondary likelihood of primary hypotheses, in the main, and Laplace's the logical metric of absolute probabilities, of statistical reports upon samples, in the main. Their efforts were, no doubt, directed to a large extent towards establishing a probabilistic theory of induction. They certainly tended to identify C with P. I need not say that I believe they were mistaken in this. Statistical theories are, like all other theories, hypothetico-deductive. And statistical hypotheses are tested, like all other hypotheses, by attempts to falsify them, by attempts to reduce their secondary likelihood to 0, or to almost 0. Their degree of corroboration, C, is of interest only if it is the result of such tests, for nothing is easier than to select statistical evidence so that it is favorable to a statistical hypothesis if we wish to do so. It might well be asked at the end of all this whether I have not, inadvertently, changed my creed. For it may seem that there is nothing to prevent us from calling C, H, E, the inductive probability of H, given E, or if this is felt to be misleading, in view of the fact that C does not obey the laws of the probability calculus, the degree of the rationality of our belief in H, given E. A benevolent inductivist critic might even congratulate me on having solved, with my C function, The age-old problem of induction in a positive sense on having nally established, with my C function, the validity of inductive reasoning. My reply would be as follows. I do not object to calling C, H, E, by any name whatsoever, suitable or unsuitable. I am quite indifferent to terminology, so long as it does not mislead us. Nor do I object so long as it does not mislead us to an extension, inadvertent or otherwise, of the meaning of induction. But I must insist that C, H, E, can be interpreted as degree of corroboration only if E is a report on the severest tests we have been able to design. It is this point that marks the difference between the attitude of the inductivist or verificationist and my own attitude. The inductivist or verificationist wants armation for his hypothesis. He hopes to make it firmer by his evidence E, and he looks out for reamness for confirmation. At best, he may realize that we must not be based in our selection of E, that we must not ignore unfavorable cases, and that E must comprise reports on our total observational knowledge whether favorable or unfavorable. Note that the inductivist's requirement that E must comprise our total observational knowledge cannot be represented in any formalism. It is a non-formal requirement, a condition of adequacy which must be satisfied if we wish to interpret P, H, E, as degree of our imperfect knowledge of H. In opposition to this inductivist attitude, I assert that C, H, E, must not be interpreted as the degree of corroboration of H by E, unless E reports the results of our sincere efforts to overthrow H. The requirement of sincerity cannot be formalized no more than the inductivist requirement that E must represent our total observational knowledge. Yet if E is not a report about the results of our sincere attempts to overthrow H, then we shall simply deceive ourselves if we think we can interpret C, H, E, as degree of corroboration, or anything like it. My benevolent critic might reply that he can still see no reason why my C function should not be regarded as a positive solution to the classical problem of induction. For my reply, he might say, should be perfectly acceptable to the classical inductivist, seeing that it merely consists in an exposition of the so-called method of eliminative induction, an inductive method which was well known to Bacon, Whewell, and Mill, and which is not yet forgotten even by some of the probability theorists of induction, though my critic may well admit that the latter were unable to incorporate it actively into their theories. My reaction to this reply would be regret at my continued failure to explain my main point with succinct clarity. For the sole purpose of the elimination advocated by all these inductivists was to establish as RMLY as possible the surviving theory which, they thought, must be the true one, or perhaps only a highly probable one, in so far as we may not have fully succeeded in eliminating every theory except the true one. As against this, I do not think that we can ever seriously reduce, by elimination, the number of the competing theories, since this number remains always infinite. What we do or should do is to hold on, for the time being, to the most improbable of the surviving theories, or, more precisely, to the one that can be most severely tested. We tentatively accept this theory, but only in the sense that we select it as worthy to be subjected to further criticism, and to the severest tests we can design. On the positive side, we may be entitled to add that the surviving theory is the best theory and the best tested theory of which we know. Addendum 1. A comment may be added on the last 3 lines of the text. By the best theory I mean the one of the competing and surviving theories which has the greatest explanatory power, content, and simplicity, and is least ad hoc. It will also be the best testable theory, but the best theory in this sense need not always be the best tested theory. 2. A most important contribution to the problem of the falsifiability of probabilistic or statistical theories and of falsifying statistical tests has just been published as this new edition goes to the press. It is Donald A. Gillies, A Falsifying Rule for Probability Statements, BJPS, pages. Appendix X. Universals, Dispositions, and Natural or Physical Necessity. 1. The fundamental doctrine which underlies all theories of induction is the doctrine of the primacy of repetitions. Keeping Hume's attitude in mind, we may distinguish 2 variants of this doctrine. The RST, which Hume criticized, may be called the doctrine of the logical primacy of repetitions. According to this doctrine, repeated instances furnish a kind of justification for the acceptance of a universal law. The idea of repetition is linked, as a rule, with that of probability. The second, which Hume upheld, may be called the doctrine of the temporal, and psychological, primacy of repetitions. According to this second doctrine, repetitions, even though they should fail to furnish an kind of justification for a universal law and for the expectations and beliefs which it entails, nevertheless induce and arouse these expectations and beliefs in us, as a matter of fact, however little justified or rational this fact, or these beliefs, may be. Both variants of this doctrine of the primacy of repetitions, the stronger doctrine of their logical primacy and the weaker doctrine of their temporal, or causal or psychological, primacy, are untenable. This may be shown with the help of two entirely different arguments. My RST argument against the primacy of repetitions is the following. All the repetitions which we experience are approximate repetitions, and by saying that a repetition is approximate I mean that the repetition B of an event A is not identical with A, or indistinguishable from A, but only more or less similar to A. But if repetition is thus based upon mere similarity, it must share one of the main characteristics of similarity, that is, its relativity. Two things which are similar are always similar in certain respects. The point may be illustrated by a simple diagram. If we look at this diagram, we see that some of the gears are similar with respect to shading, hatching, or to its absence, others are similar with respect to shape, and others are similar with respect to size. The table might be extended. One can easily see that there is no end to the possible kinds of similarity. These diagrams show that things may be similar in different respects, and that any two things which are from one point of view similar may be dissimilar from another point of view. Generally, similarity, and with it repetition, always presuppose the adoption of a point of view. Some similarities or repetitions will strike us if we are interested in one problem, and others if we are interested in another problem. But if similarity and repetition presuppose the adoption of a point of view, or an interest, or an expectation, it is logically necessary that points of view, or interests, or expectations, are logically prior, as well as temporally, or causally or psychologically, prior, to repetition. But this result destroys both the doctrines of the logical and of the temporal primacy of repetitions. The remark may be added that for any given night group or set of things, however variously they may be chosen, we can, with a little ingenuity, always points of view such that all the things belonging to that set are similar, or partially equal, if considered from one of these points of view, which means that anything can be said to be a repetition of anything, if only we adopt the appropriate point of view. This shows how naive it is to look upon repetition as something ultimate, or given. The point here made is closely related to the fact, mentioned in Appendix 7, footnote, cf. The property B, that we can for any given night sequence of noughts and ones, a mathematical rule or law for constructing an innite sequence such that it commences with the given night sequence. I now come to my second argument against the primacy of repetitions. It is this. There are laws and theories of a character altogether different from all swans are white, even though they may be formulated in a similar way. Take ancient atomic theory. Admittedly, it may be expressed, in one of its simplest forms, as all material bodies are composed of corpuscles. Yet clearly, the all form is comparatively unimportant in the case of this law. What I mean is this. The problem of showing that one single physical body, say, a piece of iron, is composed of atoms or corpuscles is at least as difficult as that of showing that all swans are white. Our assertions transcend, in both cases, all observational experience. It is the same with almost all scientific theories. We cannot show, directly, even of one physical body that, in the absence of forces, it moves along a straight line, or that it attracts, and is attracted by, one other physical body in accordance with the inverse square law. All these theories describe what we may call structural properties of the world, and they all transcend all possible experience. The difficulty with these structural theories is not so much to establish the universality of the law from repeated instances as to establish that it holds even for one single instance. This difficulty has been seen by many inductivists. Most of those who saw it tried, like Berkeley, to make a sharp distinction between pure observational generalizations and more abstract or occult theories, such as the corpuscular theory, or Newton's theory, and they tried, as a rule, to resolve the problem by saying, as did Berkeley, that abstract theories are not genuine assertions about the world, but that they are nothing but instruments for the prediction of observable phenomena. I have called this view instrumentalism, and I have criticized it in some detail elsewhere. Here I will only say that I reject instrumentalism, and I will give only one reason for rejecting it, that it does not solve the problem of the abstract or occult or structural properties. For such properties do not only occur in the abstract theories which Berkeley and his successors had in mind. They are mentioned all the time, by everybody, and in ordinary speech. Almost every statement we make transcends experience. There is no sharp dividing line between an empirical language and a theoretical language. We are theorizing all the time, even when we make the most trivial singular statement. With this remark, we have arrived at the main problem which I intend to examine in this appendix. 2. Admittedly, if we say all swans are white, then the whiteness we predicate is an observable property, and to this extent, a singular. Statements such as this swan here is white may be said to be based on observation. Yet it transcends experience not because of the word white, but because of the word swan. For by calling something a swan, we attribute to it properties which go far beyond mere observation, almost as far as when we assert that it is composed of corpuscles. Thus not only the more abstract explanatory theories transcend experience, but even the most ordinary singular statements. For even ordinary singular statements are always interpretations of the facts in the light of theories. And the same holds even for the facts of the case. They contain universals, and universals always entail a law-like behavior. I explained at the end of section how it is that the use of universals such as glass or water, in a statement like here is a glass of water, necessarily transcends experience. It is due to the fact that words like glass or water are used to characterize the law-like behavior of certain things, which may be expressed by calling them dispositional words. Now since every law transcends experience, which is merely another way of saying that it is not variable, every predicate expressing law-like behavior transcends experience also. This is why the statement "this container contains water" is a testable but non-variable hypothesis, transcending experience. It is for this reason impossible to constitute any true universal term, as Carnap tried to do, that is to say, to dean it in purely experimental or observational terms or to reduce it to purely experiential or observational terms. Since all universals are dispositional, they cannot be reduced to experience. We must introduce them as undeaned terms, except those which we may dean in terms of other non-experiential universals, such as water if we choose to dean it as a compound of 2 atoms of hydrogen and 1 of oxygen. 3. That all universals are dispositional is often overlooked, owing to the fact that universals can be dispositional in varying degrees. Thus soluble or breakable are clearly dispositional in a higher degree than dissolved or broken. But it is sometimes not realized that even dissolved and broken are dispositional. A chemist would not say that sugar or salt has dissolved in water if he did not expect that he could get the sugar or the salt back, by evaporating the water. Thus dissolved denotes a dispositional state. And as to broken, we need only consider how we proceed if we are in doubt whether or not a thing is broken, something we have dropped, perhaps, or say, a bone in our body. We test the behavior of the thing in question, trying to find out whether it does not show a certain undue mobility. Thus broken, like dissolved, describes dispositions to behave in a certain regular or law-like manner. Similarly, we say of a surface that it is red, or white, if it has the disposition to reek red or white light, and consequently the disposition to look in daylight red or white. In general, the dispositional character of any universal property will become clear if we consider what tests we should undertake if we are in doubt whether or not the property is present in some particular case. Thus the attempt to distinguish between dispositional and non-dispositional predicates is mistaken, just as is the attempt to distinguish between theoretical terms, or languages, and non-theoretical or empirical or observational or factual or ordinary terms, or languages. It is, perhaps, somewhat like this. What people have learned before reaching a certain critical age, they are inclined to regard as factual, or ordinary, and what they hear later, as theoretical or perhaps as merely instrumental. The critical age seems to depend on the psychological type. 4. Universal laws transcend experience, if only because they are universal and thus transcend any finite number of their observable instances, and singular statements transcend experience because the universal terms which normally occur in them entail dispositions to behave in a law-like manner, so that they entail universal laws, of some lower order of universality, as a rule. Accordingly, universal laws transcend experience in at least two ways, because of their universality, and because of the occurrence of universal or dispositional terms in them. And they transcend experience in a higher degree if the dispositional terms which occur in them are dispositional in a higher degree or more abstract. There are layers of higher and higher degrees of universality, and thus of transcendence. In section of the postscript, an attempt is made to explain the sense in which these are also layers of what may be called depth. It is of course because of this transcendence that scientific laws or theories are non-variable, and that testability or refutability is the only thing that distinguishes them, in general, from metaphysical theories. If it is asked why we use these transcendent universal laws instead of keeping more closely to experience, two kinds of answer may be given. A. Because we need them, because there is no such thing as pure experience, but only experience interpreted in the light of expectations or theories which are transcendent. B. Because a theorist is a man who wishes to explain experiences, and because explanation involves the use of explanatory hypotheses which, in order to be independently testable, see section of the postscript, must transcend what we hope to explain. The reason given under A is a pragmatic or instrumentalist one, and although I believe that it is true, I do not think that it is comparable in importance with the reason given under B, for even if a program of eliminating explanatory theories for practical purposes, say, for prediction, were to succeed, the aim of the theorist would be unaided. 5. That theories transcend experience in the sense here indicated was asserted in many places in the book. At the same time, theories were described as strictly universal statements. A most penetrating criticism of the view that theories, or laws of nature, can be adequately expressed by a universal statement, such as all planets move in ellipses, has been advanced by William Neil. I have found Neil's criticism difficult to understand. Even now I am not entirely sure whether I understand him properly, but I hope I do. I believe that Neil's point can be put as follows. Although universal statements are entailed by statements of natural law, the latter are logically stronger than the former. They do not only assert all planets move in ellipses, but rather something like all planets move necessarily in ellipses. Neil calls a statement of this kind a principle of necessitation. I do not think that he succeeds in making quite clear what the difference is between a universal statement and a principle of necessitation. He speaks of the need for a more precise formulation of the notions of contingency and necessity. But a little later, one reads to one's surprise, in fact, the word necessity is the least troublesome of those with which we have to deal in this part of philosophy. Admittedly, between these two passages, Neil tries to persuade us that the sense of this distinction, the distinction between contingency and necessity, can be easily understood from examples. But I found his examples perplexing. Always assuming that I have succeeded in my endeavors to understand Neil, I must say that his positive theory of natural law seems to me utterly unacceptable. Yet his criticism seems to me most valuable. 6. I am now going to explain, with the help of an example, what I believe to be essentially Neil's criticism of the view that a characterization of laws of nature as universal statements is logically succinct and also intuitively adequate. Consider some extinct animal, say the moa, a huge bird whose bones abound in some New Zealand swamps. I have there dug for them myself. We decide to use the name moa as a universal name, rather than as a proper name, cf. section, of a certain biological structure, but we ought to admit that it is of course quite possible and even quite credible that no moas have ever existed in the universe, or will ever exist, apart from those which once lived in New Zealand, and we will assume that this credible view is correct. Now let us assume that the biological structure of the moa organism is of such a kind that under very favorable conditions, a moa might easily live 60 years or longer. Let us further assume that the conditions met by the moa in New Zealand were far from ideal, owing, perhaps, to the presence of some virus, and that no moa ever reached the age of FTY. In this case, the strictly universal statement all moas die before reaching the age of FTY will be true, for according to our assumption, there never is, was, or will be a moa in the universe more than FTY years of age. At the same time, this universal statement will not be a law of nature, for according to our assumptions, it would be possible for a moa to live longer, and it is only due to accidental or contingent conditions such as the CO presence of a certain virus that in fact no moa did live longer. The example shows that there may be true, strictly universal statements which have an accidental character rather than the character of true universal laws of nature. Accordingly, the characterization of laws of nature as strictly universal statements is logically insouciant and intuitively inadequate. 7. The example may also indicate in what sense natural laws may be described as principles of necessity or principles of impossibility, as Neil suggests. For according to our assumptions which are perfectly reasonable, it would be possible, under favorable conditions, for a moa to reach a greater age than any moa has actually reached. But were there a natural law limiting the age of any moa-like organism to FTY years, then it would not be possible for any moa to live longer than this. Thus natural laws set certain limits to what is possible. I think that all this is intuitively acceptable. In fact, when I said, in several places in my book, that natural laws forbid certain events to happen, or that they have the character of prohibitions, I gave expression to the same intuitive idea. And I think that it is quite possible and perhaps even useful to speak of natural necessity or of physical necessity, in order to describe this character of natural laws, and of their logical consequences. 8. But I think it is a mistake to underrate the differences between this natural or physical necessity, and other kinds of necessity, for example, logical necessity. We may, roughly, describe as logically necessary what would hold in any conceivable world. But although Newton's inverse square law may conceivably be a true law of nature in some world, and to that extent naturally necessary in that world, a world in which it is not valid is perfectly conceivable. Neil has criticized this kind of argument by pointing out that Goldbach's conjecture, according to which any even number greater than 2 is the sum of 2 primes, may conceivably be true, or conceivably be false, even though it may well be demonstrable, or refutable, and in this sense mathematically or logically necessary, or impossible, and he argues that the conceivability of the contradictory is not to be taken as a disproof of necessity in mathematics. But if so, why, he asks, should it be supposed to furnish a disproof in natural science? 0. Now I think that this argument lays too much stress on the word conceivable. Moreover, it operates with a sense of conceivable different from the one intended. Once we have a proof of Goldbach's theorem, we may say that this proof establishes precisely that an even number, greater than 2, which is not the sum of 2 primes, is inconceivable in the sense that it leads to inconsistent results, to the assertion, among others, that 0 equals, which is inconceivable. In another sense, 0 equals may be quite conceivable. It may even be used, like any other mathematically false statement, as an assumption in an Indirect proof. Indeed, an indirect proof may well be put thus: conceive that A is true. Then we should have to admit that B is true. But we know that B is absurd. Thus it is inconceivable that A is true. It is clear that although this use of conceivable and inconceivable is a little vague and ambiguous, it would be misleading to say that this way of arguing must be invalid, since the truth of A cannot be inconceivable, considering that we did start by conceiving, precisely, the truth of A. Thus inconceivable in logic and mathematics is simply another word for leading to an obvious contradiction. Logically possible or conceivable is everything that does not lead to an obvious contradiction, and logically impossible or inconceivable is everything that does. When Neil says that the contradictory of a theorem may be conceivable, he uses the word in another sense, and in a very good sense too. 9. Thus an assumption is logically possible if it is not self-contradictory; it is physically possible if it does not contradict the laws of nature. The two meanings of possible have enough in common to explain why we use the same word, but to gloss over their difference can only lead to confusion. Compared with logical tautologies, laws of nature have a contingent, an accidental character. This is clearly recognized by Leibniz, who teaches, cf. Philoschriften, Gerhardt, p. 0, that the world is the work of God, in a sense somewhat similar to that in which a sonnet, or a rondo, or a sonata, or a fugue, is the work of an artist. The artist may freely choose a certain form, voluntarily restricting his freedom by this choice. He imposes certain principles of impossibility upon his creation, for example upon his rhythm, and, to a lesser extent, his words, which, as compared to the rhythm, may appear contingent, accidental. But this does not mean that his choice of form, or of rhythm, was not contingent also. For another form or rhythm could have been chosen. Similarly with natural laws. They restrict the, logically, possible choice of singular facts. They are thus principles of impossibility with respect to these singular facts, and the singular facts seem highly contingent as compared with the natural laws. But the natural laws, though necessary as compared with singular facts, are contingent as compared with logical tautologies. For there may be structurally different worlds with different natural laws. Thus natural necessity or impossibility is like musical necessity or impossibility. It is like the impossibility of a 4-beat rhythm in a classical minuet, or the impossibility of ending it on a diminished seventh or some other dissonance. It imposes structural principles upon the world. But it still leaves a great deal of freedom to the more contingent singular facts, the initial conditions. If we compare the situation in music with that of our example of the Moa, we can say, there is no musical law prohibiting the writing of a minuet in G at minor, but it is nevertheless quite possible that no minuet has ever been, or will ever be, written in this unusual key. Thus we can say that musically necessary laws may be distinguished from true universal statements about the historical facts of musical composition. 10. The opposite view, the view that natural laws are in no sense contingent, seems to be the one which Neil is advancing, if I understand him well. To me it seems quite as mistaken as the view which he justly criticizes, the view that laws of nature are nothing but true universal statements. Neil's view that laws of nature are necessary in the same sense in which logical tautologies are necessary may perhaps be expressed in religious terms thus: God may have faced the choice between creating a physical world and not creating a physical world, but once this choice was made, he was no longer free to choose the form, or the structure of the world, for since this structure, the regularities of nature, described by the laws of nature, is necessarily what it is, all he could freely choose were the initial conditions. It seems to me that Descartes held a view very similar to this. According to him, all the laws of nature follow with necessity from the one analytic principle, the essential definition of body, according to which to be a body means the same as to be extended, which is taken to imply that two different bodies cannot take up the same extension, or space. Indeed, this principle is similar to Neil's standard example that nothing which is red is also green. But it is by going beyond these truisms, as Neil calls them, stressing their similarity to logical tautologies, that, beginning with Newton, physical theory has reached a depth of insight utterly beyond the Cartesian approach. It seems to me that the doctrine that the laws of nature are in no sense contingent is a particularly severe form of a view which I have described and criticized elsewhere as essentialism. For it entails the doctrine of the existence of ultimate explanations, that is to say, of the existence of explanatory theories which in their turn are neither in need of any further explanation nor capable of being further explained. For should we succeed in the task of reducing all the laws of nature to the true principles of necessitation to truisms, such as that two essentially extended things cannot take up the same extension, or that nothing which is red is also green, further explanation would become both unnecessary and impossible. I see no reason to believe that the doctrine of the existence of ultimate explanations is true, and many reasons to believe that it is false. The more we learn about theories, or laws of nature, the less do they remind us of Cartesian self-explanatory truisms or of essentialist definite ions. It is not truisms which science unveils. Rather, it is part of the greatness and the beauty of science that we can learn, through our own critical investigations, that the world is utterly different from what we ever imagined until our imagination was read by the refutation of our earlier theories. There does not seem any reason to think that this process will come to an end. All this receives the strongest support from our considerations about content and, absolute, logical probability. If laws of nature are not merely strictly universal statements, they must be logically stronger than the corresponding universal statements, since the latter must be deducible from them. But the logical necessity of A, as we have seen, at the end of Appendix V, can be deemed by the Dinians. P, A, equals P, A equals. For universal statements A, on the other hand, we obtain, cf. the same appendix and appendices 7 and 8. P, A, equals P, A equals 0. And the same must hold for any logically stronger statement. Accordingly, a law of nature is, by its great content, as far removed from a logically necessary statement as a consistent statement can be, and it is much nearer, in its logical import, to a merely accidentally universal statement than to a logical truism. 11. The upshot of this discussion is that I am prepared to accept Neil's criticism insofar as I am prepared to accept the view that there exists a category of statements, the laws of nature, which are logically stronger than the corresponding universal statements. This doctrine is, in my opinion, incompatible with any theory of induction. To my own methodology it makes little or no difference, however. On the contrary, it is quite clear that a proposed or conjectured principle which declares the impossibility of certain events would have to be tested by trying to show that these events are possible, that is to say, by trying to bring them about. But this is precisely the method of testing which I advocate. Thus, from the point of view here adopted, no change whatever is needed, as far as methodology is concerned. The change is entirely on an ontological, a metaphysical level. It may be described by saying that if we conjecture that A is a natural law, we conjecture that A expresses a structural property of our world, a property which prevents the occurrence of certain logically possible singular events, or states of errors of a certain kind, very much as explained in sections 2 of the book, and also in sections, and 12, as Tarski has shown, it is possible to explain logical necessity in terms of universality. A statement may be said to be logically necessary if and only if it is deducible, for example, by particularization, from a universally valid statement function, that is to say, from a statement function which is satisfied by every model. This means, true in all possible worlds. I think that we may explain by the same method what we mean by natural necessity, for we may adopt the following definition, and agree. And agree, a statement may be said to be naturally or physically necessary if, and only if, it is deducible from a statement function which is satisfied in all worlds that differ from our world, if at all, only with respect to initial conditions. See the addendum to the present appendix. We can never know, of course, whether a supposed law is a genuine law or whether it only looks like a law but depends, in fact, upon certain special initial conditions prevailing in our region of the universe. Cf. section. We cannot, therefore, ever nd out of any given non-logical statement that it is in fact naturally necessary. The conjecture that it is remains a conjecture forever, not merely because we cannot search our whole world in order to ensure that no counter-instance exists, but for the even stronger reason that we cannot search all worlds that differ from ours with respect to initial conditions. But although our proposed definition excludes the possibility of obtaining a positive criterion of natural necessity, we can in practice apply our definition of natural necessity in a negative way. By ending initial conditions under which the supposed law turns out to be invalid, we can show that it was not necessary, that is to say, not a law of nature. Thus the proposed definition ts our methodology very well indeed. The proposed definition would, of course, make all laws of nature, together with all their logical consequences, naturally or physically necessary. It will be seen at once that the proposed definition is in perfect agreement with the results reached in our discussion of the MOA example. Cf. points and above. It was precisely because we thought that MOAs would live longer under diurent conditions under more favorable ones that we felt that a true universal statement about their actual maximal age was of an accidental character. 13. We now introduce the symbol n as a name of the class of statements which are necessarily true, in the sense of natural or physical necessity, that is to say, true whatever the initial conditions may be. N. With the help of n, we can define a registered trademark B, or in words, if a then necessarily B, by the following somewhat obvious definition. N. D. A registered trademark B is true if, and only if, a registered trademark B, epsilon n. N. In words, perhaps, if a then necessarily B holds if, and only if a then B is necessarily true. Here a registered trademark B is, of course, the name of an ordinary conditional with the antecedent and the consequent B. If it were our intention to deem logical entailment or strict implication, then we could also use D, but we should have to interpret N as logically necessary, rather than as naturally or physically necessary. Owing to the definition, D, we can say of a registered trademark B that it is the name of a statement with the following properties. N. A registered trademark B is not always true if A is false, in contradistinction to a registered trademark B. N. B. A registered trademark B is not always true if B is true, in contradistinction to a registered trademark B. A registered trademark B is always true if A is impossible or necessarily false, or if its negation, A, is necessarily true whether by logical or by physical necessity. Cf. the last 3 pages of the present appendix, and note, below. N. B. A registered trademark B is always true if B is necessarily true, whether by logical or physical necessity. Here A and B may be either statements or statement functions. N. A registered trademark B may be called a necessary conditional or a nomic conditional. It expresses, I believe, what some authors have called subjunctive conditionals, or counterfactual conditionals. It seems, however, that other authors, for example Neal, meant something else by a counterfactual conditional. They took this name to imply that A is, in fact, false. I do not think that this usage is to be recommended. A little reaction will show that the class N of naturally necessary statements comprises not only the class of all those statements which, like true universal laws of nature, can be intuitively described as being unaffected by changes of initial conditions, but also all those statements which follow from true universal laws of nature, or from the true structural theories about the world. There will be statements among these that describe a finite set of initial conditions, for example, statements of the form if in this file under ordinary room temperature and a pressure of 000 g per cm, hydrogen and oxygen are mixed, then. If conditional statements of this kind are deducible from true laws of nature, then their truth will be also invariant with respect to all changes of initial conditions. Either the initial conditions described in the antecedent will be satised, in which case the consequent will be true, and therefore the whole conditional, or the initial conditions described in the antecedent will not be satised and therefore factually untrue, counterfactual. In this case the conditional will be true as vacuously satised. Thus the much discussed vacuous satisfaction plays its proper part to ensure that the statements deducible from naturally necessary laws are also naturally necessary in the sense of our definition. Indeed, we could have deemed N simply as the class of natural laws and their logical consequences. But there is perhaps a slight advantage in defining N with the help of the idea of initial conditions, of a simultaneity class of singular statements. If we define N as, for example, the class of statements which are true in all worlds that differ from our world, if at all, only with respect to initial conditions, then we avoid the use of subjunctive, or counterfactual, wording, such as which would remain true even if different initial conditions held, in our world, than those which actually do hold. Nevertheless, the phrase in, and degree, all worlds which differ, if at all, from our world only with respect to the initial conditions undoubtedly contains implicitly the idea of laws of nature. What we mean is all worlds which have the same structure or the same natural laws as our own world. In so far as our definition contains implicitly the idea of laws of nature, and degree, may be said to be circular. But all definitions must be circular in this sense precisely as all derivations, as opposed to proofs, for example, all syllogisms, are circular. The conclusion must be contained in the premises. Our definition is not, however, circular in a more technical sense. Its definition operates with a perfectly clear intuitive idea that of varying the initial conditions of our world, for example, the distances of the planets, their masses, and the mass of the Sun. It interprets the result of such changes as the construction of a kind of model of our world, a model or copy which does not need to be faithful with respect to the initial conditions, and it then imitates the well-known device of calling those statements necessary which are true in the universe of all these models, i.e. for all logically possible initial conditions. 14. My present treatment of this problem differs, intuitively, from a version previously published. I think that it is a considerable improvement, and I gladly acknowledge that I owe this improvement, in a considerable measure, to Neil's criticism. Nevertheless, from a more technical, rather than an intuitive, point of view the changes are slight. For in that paper, I operate, a. with the idea of natural laws, b. with the idea of conditionals which follow from natural laws, but, a. and, b. together have the same extension as n, as we have seen. C. I suggest that subjunctive conditionals are those that follow from, a. i.e. are just those of the class, b. And, d. I suggest, in the last paragraph, that we may have to introduce the supposition that all logically possible initial conditions, and therefore all events and processes which are compatible with the laws, are somewhere, at some time, realized in the world, which is a somewhat clumsy way of saying more or less what I am saying now with the help of the idea of all worlds that differ, if at all, from our world only with respect to the initial conditions. 0. My position might indeed be formulated with the help of the following statement. Although our world may not comprise all logically possible worlds, since worlds of another structure with different laws may be logically possible, it comprises all physically possible worlds, in the sense that all physically possible initial conditions are realized in it somewhere, at some time. My present view is that it is only too obvious that this metaphysical assumption may possibly be true in both senses of possible, but that we are much better without it. Yet once this metaphysical assumption is adopted, my older and my present views become, except for purely terminological differences, equivalent, as far as the status of laws is concerned. Thus my older view is, if anything, more metaphysical, or less positivistic, than my present view, even though it does not make use of the word necessary in describing the status of laws. 15. to a student of method who opposes the doctrine of induction and adheres to the theory of falsification, there is not much difference between the view that universal laws are nothing but strictly universal statements and the view that they are necessary. In both cases, we can only test our conjecture by attempted refutations. To the inductivist, there is a crucial difference here. He ought to reject the idea of necessary laws, since these, being logically stronger, must be even less accessible to induction than mere universal statements. Yet inductivists do not in fact always reason in this way. On the contrary, some seem to think that a statement asserting that laws of nature are necessary may somehow be used to justify induction, perhaps somewhat on the lines of a principle of the uniformity of nature. But it is obvious that no principle of this kind could ever justify induction. None could make inductive conclusions valid or even probable. It is quite true, of course, that a statement like "there exist laws of nature" might be appealed to if we wished to justify our search for laws of nature. But in the context of this remark of mine, justify has a sense very different from the one it has in the context of the question whether we can justify induction. In the latter case, we wish to establish certain statements, the induced generalizations. In the former case, we merely wish to justify an activity, the search for laws. Moreover, even though this activity may, in some sense, be justified by the knowledge that true laws exist, that there are structural regularities in the world, it could be so justified even without that knowledge. The hope that there may be some food somewhere certainly justifies the search for it, especially if we are starving, even if this hope is far removed from knowledge. Thus we can say that, although the knowledge that true laws exist would add something to the justification of our search for laws, this search is justified, even if we lack knowledge, by our curiosity, and by the mere hope that we may succeed. Moreover, the distinction between necessary laws and strictly universal statements does not seem to be relevant to this problem. Whether necessary or not, the knowledge that laws exist would add something to the justification of our search, without being needed for this kind of justification. 16. I believe, however, that the idea that there are necessary laws of nature, in the sense of natural or physical necessity explained under point, is metaphysically or ontologically important, and of great intuitive significance in connection with our attempts to understand the world. And although it is impossible to establish this metaphysical idea either on empirical grounds, because it is not falsifiable, or on other grounds, I believe that it is true, as I indicated in section, and 2. Yet I am now trying to go beyond what I said in these sections by emphasizing the peculiar ontological status of universal laws, for example, by speaking of their necessity, or their structural character, and also by emphasizing the fact that the metaphysical character or the irrefutability of the assertion that laws of nature exist need not prevent us from discussing this assertion rationally, that is to say, critically. See my postscript, especially sections, and 0. Nevertheless, I regard, unlike Neil, necessary as a mere word as a label useful for distinguishing the universality of laws from accidental universality. Of course, any other label would do just as well, for there is not much connection here with logical necessity. I largely agree with the spirit of Wittgenstein's paraphrase of Hume: a necessity for one thing to happen because another has happened does not exist. There is n. only logical necessity. Only in one way is a registered trademark B connected with logical necessity. The necessary link between A and B is neither to be found in A nor in B, but in the fact that the corresponding ordinary conditional, or material implication, a registered trademark B without N, follows with logical necessity from a law of nature that it is necessary, relative to a law of nature. And it may be said that a law of nature is necessary in its turn because it is logically derivable from, or explicable by, a law of a still higher degree of universality, or of greater depth. See my postscript, section. One might suppose that it is this logically necessary dependence upon true statements of higher universality, conjectured to exist, which suggested in the RST instance the idea of necessary connection between cause and effect. 17. So far as I can understand the modern discussions of Junctive conditionals or contrary to fact conditionals or counterfactual conditionals, they seems to have arisen mainly out of the problem situation created by the inherent difficulties of inductivism or positivism or operationalism or phenomenalism. The phenomenalist, for instance, wishes to translate statements about physical objects into statements about observations. For example, there is a shower pot on the windowsill should be translatable into something like if anybody in an appropriate place looks in the appropriate direction, he will see what he has learned to call a shower pot. The simplest objection, but by no means the most important one, to regarding the second statement as a translation of the RST is to point out that while the second will be, vacuously, true when nobody is looking at the windowsill, it would be absurd to say that whenever nobody is looking at some windowsill, there must be a shower pot on it. The phenomenalist is tempted to reply to this that the argument depends on the truth table definition of the conditional, or of material implication, and that we have to realize the need for a diarrhent interpretation of the conditional, a modal interpretation which makes allowance for the fact that what we mean is something like if anybody looks, or if anybody were looking, then he will see, or would see, a shower pot. N. One might think that a registered trademark B could provide the desired modal conditional, and in a way it does do this. Indeed, it does it as well as one can possibly expect. Nevertheless, our original objection stands, because we know that if A is necessary, that is, if A epsilon and then a registered trademark B holds for every B. This means that, if for some reason or other the place where a shower pot is, or is not, situated is such that it is physically impossible for anybody to look at it, then if anybody looks, or if anybody were looking, at that place, then he will, or would, see a shower pot will be true, merely because nobody can look at it. But this means that the phenomenalist modal translation of at the place X is a shower pot will be true for all those places X which, for some physical reason or other, nobody can look at. Thus there is a shower pot or whatever else you like in the center of the Sunday. But this is absurd. For this reason, and for many other reasons, I do not think that there is any chance of rescuing phenomenalism by this method. As to the doctrine of operationalism, which demands that scientific terms, such as length, or solubility, should be deemed in terms of the appropriate experimental procedure, it can be shown quite easily that all so-called operational definitions will be circular. I may show this in the case of soluble. The experiments by which we test whether a substance such as sugar is soluble in water involve such tests as the recovery of dissolved sugar from the solution, say, by evaporation of the water, cf. point above. Clearly, it is necessary to identify the recovered substance, that is to say, to ND out whether it has the same properties as sugar. Among these properties, solubility in water is one. Thus, in order to deem X is soluble in water by the standard operational test, we should at least have to say something like this. X is soluble in water if and only if, A, when X is put into water then it, necessarily, disappears, and, B, when after the water evaporates, a substance is, necessarily, recovered which, again, is soluble in water. The fundamental reason for the circularity of this kind of definition is very simple: experiments are never conclusive, and they must, in their turn, be testable by further experiments. Operationalists seem to have believed that once the problem of subjunctive conditionals was solved, so that the vacuous satisfaction of the Denning conditional could be avoided, there would be no further obstacle in the way of operational definitions of dispositional terms. It seems that the great interest shown in the so-called problem of subjunctive, or counterfactual, conditionals was mainly due to this belief. But I think I have shown that even if we have solved the problem of logically analyzing subjunctive, or gnomic, conditionals, we cannot hope to deem dispositional terms, or universal terms, operationally. For universals, or dispositional terms, transcend experience, as explained here under points and in section of the book. Addendum. Since this appendix was RST published in, there has been a very interesting reply from William Neal, BJPS, p. Dot, and a criticism by G.C. Nerlich and W.A. Suchting, BJPS. P. Dot, to which I replied, BJPS, p. I do not now think that my reply is very good. In fact, it is only after reconsidering Neil's criticism that I realized what is at the bottom of our disagreement. It is, I now think, the fact that most philosophers regard definitions as important, and that they have never taken my assurance seriously that I do regard them as unimportant. I neither believe that definitions can make the meaning of our words denied, nor do I think it worth bothering about whether or not we can define a term, though it may sometimes be moderately interesting that a term can be defined with the help of terms of a certain kind, for we do need undefined primitive terms in any case. I may perhaps sum up my position by saying that, while theories and the problems connected with their truth are all important, words and the problems connected with their meaning are unimportant. Cp. Conjectures and Refutations, RD edition, point, on p. For this reason I am not really very interested in either the definition or in the deniability of natural necessity, though I am interested in the fact, for I believe that it is a fact, that the idea is not meaningless. Least of all am I interested in establishing the fact, if it is a fact, which I regard as doubtful, that a modal term can be defined with the help of non-modal terms. If I have given the impression that this is what I wanted to show, I have certainly given the wrong impression. Appendix 11. On the use and misuse of imaginary experiments, especially in quantum theory. The criticisms presented in the later parts of this appendix are logical in character. My point is not to refute certain arguments, some of which, for all I know, may have long been discarded by their originators. I try, rather, to show that certain methods of argument are inadmissible methods which have been used, without being challenged, for many years in the discussions about the interpretation of quantum theory. It is, in the main, the apologetic use of imaginary experiments which I am criticizing here, rather than any particular theory in whose defense these experiments were propounded. Least of all do I wish to create the impression that I am doubting the fruitfulness of imaginary experiments. One of the most important imaginary experiments in the history of natural philosophy, and one of the simplest and most ingenious arguments in the history of rational thought about our universe, is contained in Galileo's criticism of Aristotle's theory of motion. It disproves the Aristotelian supposition that the natural velocity of a heavier body is greater than that of a lighter body. If we take two moving bodies, Galileo's spokesman argues, such that their natural velocities are unequal, it is manifest that if we join them together, the slower and the faster one, then the latter will be partly retarded by the slower one, and the slower partly sped up by the faster one. Thus if a big stone moves, for example, with a velocity of 8 steps and a smaller one with a velocity of 4, then, after being joined together, the composite system will move with a velocity of less than 8 steps. But the two stones joined together make a stone bigger than the RST one which moved with a velocity of 8 steps. Thus the composite body, although bigger than the RST alone, will nevertheless move more slowly than the RST alone, which is contrary to your supposition. And since this Aristotelian supposition was the one from which the argument started, it is now refuted, it is shown to be absurd. I see in Galileo's imaginary experiment a perfect model for the best use of imaginary experiments. It is the critical use. I do not wish to suggest, however, that there is no other way of using them. There is, especially, a heuristic use which is very valuable. But there are less valuable uses also. An old example of what I call the heuristic use of imaginary experiments is one that forms the heuristic basis of atomism. We imagine that we take a piece of gold, or some other substance, and cut it into smaller and smaller parts until we arrive at parts so small that they cannot be any longer subdivided, a thought experiment used in order to explain indivisible atoms. Heuristic imaginary experiments have become particularly important in thermodynamics, Carnot's cycle, and they have lately become somewhat fashionable owing to their use in relativity and in quantum theory. One of the best examples of this kind is Einstein's experiment of the accelerated lift. It illustrates the local equivalence of acceleration and gravity, and it suggests that light rays in a gravitational field may proceed on curved paths. This use is important and legitimate. The main purpose of this note is to issue a warning against what may be called the apologetic use of imaginary experiments. This use goes back, I think, to the discussion of the behavior of measuring rods and clocks from the point of view of special relativity. At RST, these experiments were used in an illustrative and expository way, a perfectly legitimate usage. But later, and in the discussion of quantum theory, they were also used, at times, as arguments, both in a critical and in a defensive or apologetic mood. In this development, an important part was played by Heisenberg's imaginary microscope, through which one could observe electrons, see points and zero below. Now, the use of imaginary experiments in critical argumentation is, undoubtedly, legitimate. It amounts to an attempt to show that certain possibilities were overlooked by the author of a theory. Clearly, it must also be legitimate to counter such critical objections, for example, by showing that the proposed imaginary experiment is in principle impossible, and that here, at least, no possibility was overlooked. An imaginary experiment designed in a critical spirit, designed in order to criticize a theory by showing that certain possibilities have been overlooked, is usually permissible, but great care must be taken with the reply, in a reconstruction of the controversial experiment, undertaken in defense of the theory. It is, more particularly, important not to introduce any idealizations or other special assumptions unless they are favorable to an opponent, or unless any opponent who uses the imaginary experiment in question would have to accept them. 2. More generally, I think that the argumentative use of imaginary experiments is legitimate only if the views of the opponent in the argument are stated with clarity, and if the rule is adhered to that the idealizations made must be concessions to the opponent, or at least acceptable to the opponent. For example, in the case of Carnot's cycle, all idealizations introduced increase the efficiency of the machine, so that the opponent to the theory who asserts that a heat machine can produce mechanical work without transferring heat from a higher temperature to a lower temperature must agree that they are concessions. Idealizations, clearly, become impermissible for the purpose of critical argumentation whenever this rule is violated. 3. This rule may be applied, for example, to the discussion initiated by the imaginary experiment of Einstein, Podolsky, and Rosen. Their argument is restated by Einstein in a letter here reproduced in Appendix 12, and this discussion is further commented upon in my postscript, Section 0. Einstein, Podolsky, and Rosen attempt, in their critical argument, to make use of idealizations acceptable to Bauer, and in his reply, Bauer does not challenge the legitimacy of their idealizations. They introduce, cf. Section 0 and Appendix 12, two particles, A and B, which interact in such a way that by measuring the position, or momentum, of B, the theory allows us to calculate the position, or momentum, of A, which has meanwhile moved far away and cannot be any longer disturbed by the measurement of B. Thus A's momentum, or position, cannot become blurred or smeared, to use a term of Schrödinger's as Heisenberg would have it. Bauer, in his reply, operates with the idea that measurement of a position can be achieved only by some instrument rigidly xed to the support which deans the space frame of reference, while measurement of the momentum would be done by a movable diaphragm whose momentum is measured before as well as after the passing of the particle. Bauer operates with the argument that in choosing one of these two systems of reference we cut ourselves off from any possibility of using the other, in connection with the same physical system under investigation. He suggests, if I understand him properly, that though A is not interfered with, its coordinates may become smeared by the smearing of the frame of reference. 4. Bauer's reply seems to me unacceptable for at least three different reasons. First, prior to the proposed imaginary experiment of Einstein, Podolsky, and Rosen, the reason given for the smearing of the position or momentum of a system was that by measuring it, we had interfered with the system. It seems to me that Bauer, surreptitiously, dropped this argument, and replaced it by saying, more or less clearly, that the reason is that we interfere with our frame of reference, or with the system of coordinates, rather than with the physical system. This is too big a change to be allowed to pass unnoticed. It would have to be explicitly acknowledged that the older position was refuted by the imaginary experiment, and it would have to be shown why this does not destroy the principle on which it was built. We must not forget, in this connection, what the imaginary experiment of Einstein, Podolsky, and Rosen was intended to show. It was intended merely to refute certain interpretations of the indeterminacy formulae. It was certainly not intended to refute these formulae. In a sense, Bohr's reply, though not explicitly, acknowledged that the imaginary experiment succeeded in its purpose, for Bohr merely tried to defend the indeterminacy relations as such. He gave up the view that the measurement would interfere with the system A which it was supposed to smear. Moreover, the argument of Einstein, Podolsky, and Rosen could be carried a little further by the assumption that we measure the position A, accidentally, at the same instant of time at which we measure the momentum of B. We then obtain, for that instant of time, positions and momenta of both A and B. Admittedly, the momentum of A and the position of B will have been destroyed or smeared by these measurements. But this is sufficient to establish the point which Einstein, Podolsky, and Rosen wanted to make, that it is incorrect to interpret the indeterminacy formulae as asserting that the system cannot have both a sharp position and a sharp momentum at the same time, even though it must be admitted that we cannot predict both at the same time. For an interpretation which takes account of all this, see my postscript. Secondly, Bohr's argument that we have cut ourselves from the other frame of reference seems to be ad hoc. For it is clearly possible to measure the momentum spectroscopically, either in a direct manner, or by using the Doppler effect, and the spectroscope will be rigidly XED to the same frame as the RST instrument. The fact that the spectroscope absorbs the particle B is irrelevant to the argument which concerns the fate of A. Thus an arrangement with a movable frame of reference cannot be accepted as an essential part of the experiment. Thirdly, Bohr does not explain here how to measure the momentum of B with the help of his movable diaphragm. In a later paper of his, a method of doing this is described, but this method seems to me again impermissible. For the method described by Bohr consists in measuring, twice, the position of a diaphragm with a slit suspended by weak springs from a solid yoke, and since the measurement of the momentum with an arrangement of this kind depends on position measurements, it does not support Bohr's argument against Einstein, Podolsky, and Rosen, nor does it succeed otherwise. For in this way we cannot get the momentum accurately before as well as after the passing of B. The RST of these measurements of momentum, since it utilizes a position measurement, will interfere with the momentum of the diaphragm. It thus will be retrospective only, and will not be of any use for calculating the momentum of the diaphragm at the time immediately before the interaction with B. It does not seem, therefore, that Bohr in his reply adhered to the principle of making only such idealizations or special assumptions which favor his opponents, quite apart from the fact that it is far from clear what he wanted to contest. 5. This shows that there is a grave danger, in connection with imaginary experiments of this kind, of carrying the analysis just as far as it serves one's purpose, and no further, a danger which can be avoided only if the above principles are strictly adhered to. There are 3 similar cases which I wish to refer to, because I find them instructive. 6. In order to meet a critical imaginary experiment of Einstein's. Based upon his famous formula E equals mc, Bohr had recourse to arguments from Einstein's gravitational theory, that is to say, from general relativity. 0 But E equals mc can be derived from special relativity, and even from non-relativistic arguments. In any case, in assuming E equals mc, we certainly do not assume the validity of Einstein's theory of gravitation. If, therefore, as Bohr suggests, we must assume certain characteristic formulae of Einstein's gravitational theory in order to rescue the consistency of quantum theory, in the presence of E equals mc, then this amounts, I hold, to the strange assertion that quantum theory contradicts Newton's gravitational theory, and further to the still stranger assertion that the validity of Einstein's gravitational theory, or at least the characteristic formulae used, which are part of the theory of the gravitational field, can be derived from quantum theory. I do not think that even those who are prepared to accept this result will be happy about it. Thus we have again an imaginary experiment which makes extravagant assumptions, with an apologetic purpose. 7. David Bohm's reply to the experiment of Einstein, Podolsky, and Rosen seems to me also highly unsatisfactory. He believes that he has to show that Einstein's particle A, which has run far away from B and from the measuring apparatus, does nevertheless become smeared in its position, or momentum, when the momentum, or position, of B is measured, and he tries, to this end, to show that A, in spite of having run away, is still interfered with in an unpredictable way. In this way he tries to show that his own theory agrees with Heisenberg's interpretation of the indeterminacy relations. But he does not succeed. This becomes manifest if we consider that the ideas of Einstein, Podolsky, and Rosen allow us, by a slight extension of their experiment, to determine simultaneously positions and momenta of both A and B, although the result of this determination will have predictive significance only for the position of the one particle and the momentum of the other. For as explained under point above, we may measure the position of B, and somebody far away may measure the momentum of A accidentally at the same instant, or at any rate before any smearing ect of our measurement of B could possibly reach A. Yet this is all that is needed to show that Bohm's attempt to save Heisenberg's idea of our interference with A is misplaced. Bohm's reply to this objection is implicit in his assertion that the smearing ect proceeds with superluminal velocity, or perhaps even instantaneously. Cf. Heisenberg's superluminal velocity commented on in section, an assumption to be supported by the further assumption that this ect cannot be used to transmit signals. But what does happen if the two measurements are carried out simultaneously? Does the particle you are supposed to observe in your Heisenberg microscope begin to dance under your very eyes? And if it does, is this not a signal? This particular smearing ect of Bohm's, like the reduction of the wave packet, is not part of his formalism, but of its interpretation. 8. A similar example is a reply of Bohm's to another critical imaginary experiment proposed by Einstein, who thereby revived Pauli's criticism of de Broglie's pilot wave theory. Einstein proposes to consider a macroscopic particle, it may be quite a big thing, say a billiard ball, moving with a certain constant velocity to and fro between two parallel walls by which it is elastically rected. Einstein shows that this system can be represented in Schrödinger's theory by a standing wave, and he shows further that the pilot wave theory of de Broglie, or Bohm's so-called causal interpretation of quantum theory, leads to the paradoxical result, RST pointed out by Pauli, that the velocity of the particle, or billiard ball, vanishes, or in other words, our original assumption that the particle moves with some arbitrarily chosen velocity leads in this theory, for every chosen velocity, to the conclusion that the velocity is zero, and that it does not move. Bohm accepts this conclusion, and replies on the following lines: the example considered by Einstein, he writes, is that of a particle moving freely between perfectly reacting and smooth walls. We need not go into the peculiarities of the arrangement. Now, in the causal interpretation of the quantum theory, that is, in Bohm's interpretation, the particle is at rest, Bohm writes, and he goes on to say that, if we wish to observe the particle, we shall trigger a process which will make the particle move. But this argument about observation, whatever its merits, is no longer interesting. What is interesting is that Bohm's interpretation paralyzes the freely moving particle. His argument amounts to the assertion that it cannot move between these two walls, as long as it is unobserved. For the assumption that it so moves leads Bohm to the conclusion that it is at rest, until triggered by an observation. This paralyzing ect is noted by Bohm, but simply not discussed. Instead, he proceeds to the assertion that though the particle does not move, our observations will show it to us moving, but this was not the point at issue, and further, to the construction of an entirely new imaginary experiment describing how our observation, the radar signal or photon used to observe the velocity of the particle, could trigger the desired movement. But this again was not the problem. And secondly, Bohm fails to explain how the triggering photon could reveal to us the particle in its full, proper speed, rather than in a state of acceleration towards its proper speed. For this seems to demand that the particle, which may be as fast and as heavy as we like, acquires and reveals its full speed during the exceedingly short time of its interaction with the triggering photon. All these are ad hoc assumptions which few of his opponents will accept. But we may elaborate Einstein's imaginary experiment by operating with two particles, or billiard balls, of which the one moves to and fro between the left wall and the center of the box while the other moves between the right wall and the center. In the center, the particles collide elastically with one another. This example leads again to standing waves, and thus to the disappearance of the velocity, and the Pauli-Einstein criticism of the theory remains unchanged. But Bohm's triggering now becomes even more precarious. For let us assume we observe the left particle by shooting at it a triggering photon from the left. This will, according to Bohm, overthrow the balance of forces which keep the particle at rest, and the particle will start moving presumably from left to right. But although we triggered only the left particle, the right particle will have to start simultaneously, and in the opposite direction. It is asking much of a physicist to acquiesce in the possibility of all these processes, all assumed ad hoc, in order to avoid the consequences of the argument of Pauli and Einstein. Einstein might have answered Bohm as follows: I think. In the case considered, our physical system was a big macroscopic ball. No reason has been given why in such a case the usual classical view of measurement should be inapplicable. And this is a view that conforms, after all, as well with experience as one can desire. But leaving measurement aside, is it seriously asserted that an oscillating ball, or two oscillating balls in a symmetric arrangement here described, simply cannot exist while unobserved? Or, what amounts to the same, is it seriously asserted that the assumption that it does move, or oscillate, while unobserved, must lead to the conclusion that it does not? And what happens if, once our observation has set the ball in motion, it is then no longer asymmetrically interfered with so that the system again becomes stationary? Does the particle then stop as suddenly as it started? And is its energy transformed into Eld energy? Or is the process irreversible? Even assuming that all these questions may be answered somehow, they illustrate, I think, the significance of Pauli's and of Einstein's criticism, and of the critical use of imaginary experiments, especially the experiment of Einstein, Podolsky, and Rosen. And I think that they also illustrate the danger of an apologetic use of imaginary experiments. 9. So far I have discussed the problem of pairs of particles, introduced into the discussion by Einstein, Podolsky, and Rosen. I now turn to some of the older imaginary experiments with single particles, such as Heisenberg's famous imaginary microscope through which one could observe electrons, and measure either their positions or their momenta. Few imaginary experiments have exerted a greater influence on thought about physics than this one. With the help of his imaginary experiment, Heisenberg tried to establish various points, of which I may mention 3. A. The interpretation of the Heisenberg indeterminacy formulae as stating the existence of insuperable barriers to the precision of our measurements. B. The disturbance of the measured object by the process of measurement, whether of position or of momentum, and C. The impossibility of testing the spatiotemporal path of the particle. I believe that Heisenberg's arguments tending to establish these points are all clearly invalid, whatever the merits of the 3 points in themselves may be. The reason is that Heisenberg's discussion fails to establish that measurements of position and of momentum are symmetrical, that is, with respect to the disturbance of the measured object by the process of measurement. For Heisenberg does show with the help of his experiment that in order to measure the position of the electron we should have to use light of a high frequency, that is to say, high energy photons, which means that we transfer an unknown momentum to the electron and thus disturb it, by giving it a severe knock, as it were. But Heisenberg does not show that the situation is analogous if we wish to measure the momentum of the electron, rather than its position. For in this case, Heisenberg says, we must observe it with a low-frequency light so low that we may assume that we do not disturb the electron's momentum by our observation. The resulting observation, though revealing the momentum, will fail to reveal the electron's position, which will thus remain indeterminate. Now consider this last argument. There is no assertion here that we have disturbed, or smeared, the electron's position. For Heisenberg merely asserts that we have failed to disclose it. In fact, his argument implies that we have not disturbed the system at all, or only so slightly that we can neglect the disturbance. We have used photons of so low an energy level that there simply was not enough energy available to disturb the electron. Thus the two cases, the measurement of position and that of momentum, are far from analogous or symmetrical, according to Heisenberg's argument. This fact is veiled, however, by the customary talk, positivist or operationalist or instrumentalist talk, about the results of measurement whose uncertainty is admittedly symmetrical with respect to position and momentum. Yet in countless discussions of the experiment, beginning with Heisenberg's own, it is always assumed that his argument establishes the symmetry of the disturbances. In the formalism, the symmetry between position and momentum is complete, of course, but this does not mean that it is accounted for by Heisenberg's imaginary experiment. Thus it is assumed quite wrongly that we disturb the electron's position if we measure its momentum with Heisenberg's microscope, and that this smearing act has been established by Heisenberg's discussion of his imaginary experiment. My own imaginary experiment of section was largely based on this asymmetry in Heisenberg's experiment. Cf. Note to Appendix 6. Yet my experiment is invalid just because the asymmetry invalidates Heisenberg's whole discussion of measurement. Only measurements resulting from physical selection, as I call it, can be used to illustrate Heisenberg's formulae, and a physical selection, as I quite correctly pointed out in the book, must always satisfy the scatter relations. Physical selection does disturb the system. Were Heisenberg's measurements possible, we could even check the momentum of an electron between two position measurements without disturbing it, which would also allow us, contrary to point c. above, to check part of its spatiotemporal path, which is calculable from these two position measurements. That the inadequacy of Heisenberg's argument has remained unnoticed for so long is no doubt due to the fact that the indeterminacy formulae clearly follow from the formalism of the quantum theory, the wave equation, and that the symmetry between position, q, and momentum, p, is also implicit in this formalism. This may explain why many physicists have failed to scrutinize Heisenberg's imaginary experiment with sufficient care. They did not take it seriously, I suppose, but merely as an illustration of a derivable formula. My point is that it is a bad illustration just because it fails to account for the symmetry between position and momentum. And being a bad illustration, it is quite inadequate as a basis for interpreting these formulae, let alone the whole quantum theory. 10. The immense ignorance of Heisenberg's imaginary experiment is, I am convinced, due to the fact that he managed to convey through it a new metaphysical picture of the physical world, whilst at the same time disclaiming metaphysics. He thus ministered to a curiously ambivalent obsession of our post-rationalist age, its preoccupation with killing the father, that is, metaphysics, while keeping him inviolate, in some other form, and beyond all criticism. With some quantum physicists it sometimes looks almost as if the father was Einstein. The metaphysical picture of the world, somehow conveyed through Heisenberg's discussion of his experiment although never really implied in it, is this. The thing in itself is unknowable, we can only know its appearances, which are to be understood, as pointed out by Kant, as resulting from the thing in itself, and from our own perceiving apparatus. Thus the appearances result from a kind of interaction between the things in themselves and ourselves. This is why one thing may appear to us in diarrhent forms, according to our diarrhent ways of perceiving it, of observing it, and of interacting with it. We try to catch, as it were, the thing in itself, but we never succeed, we only end the appearances in our traps. We can set either a classical particle trap or a classical wave trap, classical because we can build them and set them like a classical mousetrap, and in the process of triggering the trap, and thus interacting with it, the thing is induced to assume the appearance of a particle or a wave. There is a symmetry between these two appearances, or between the two ways of trapping the thing. Moreover, we not only, by setting the trap, have to supply a stimulus for the thing in order to induce it to assume one of its two classical physical appearances, but we also have to bait the trap with energy, the energy needed for a classical physical realization or materialization of the unknowable thing in itself. In this way, we preserve the conservation laws. This is the metaphysical picture conveyed by Heisenberg, and perhaps also by Bohr. Now I am far from objecting to metaphysics of this kind, though I am not much attracted by this particular blend of positivism and transcendentalism. Nor do I object to its being conveyed to us through metaphors. What I do object to is the almost unconscious dissemination of this metaphysical picture, often combined with antimetaphysical disclaimers. For I think that it should not be allowed to sink in unnoticed, and thus uncriticized. It is interesting, I think, that much of David Bohm's work seems to be inspired by the same metaphysics. One might even describe his work as a valiant attempt to construct a physical theory that shall make this metaphysics clear and explicit. This is admirable. But I wonder whether this particular metaphysical idea is good enough, and really worth the trouble, considering that it cannot be supported, as we have seen, by Heisenberg's imaginary experiment, which is the intuitive source of it all. There seems to me a fairly obvious connection between Bohr's principle of complementarity and this metaphysical view of an unknowable reality, a view that suggests the renunciation, to use a favorite term of Bohr's, of our aspirations to knowledge, and the restriction of our physical studies to appearances and their interrelations. But I will not discuss this obvious connection here. Instead, I will confine myself to the discussion of certain arguments in favor of complementarity which have been based upon further imaginary experiments. 11. In connection with this principle of complementarity, discuss it more fully in my postscript, cf. also my paper 3 Views Concerning Human Knowledge, now in my Conjectures and Refutations, chapter. Bohr has analyzed a large number of subtle imaginary experiments in a similarly apologetic vein. Since Bohr's formulations of the principle of complementarity are vague and difficult to discuss, I shall have recourse to a well-known and in many respects excellent book, Oncholik Quantum Theory, by P. Jordan, and a book in which, incidentally, my logic der Chung was discussed. Jordan gives a formulation of, part of, the contents of the principle of complementarity that brings it into the closest relation to the problem of the dualism between particles and waves. He puts it as follows. Any one experiment which would bring forth, at the same time, both the wave properties and the particle properties of light would not only contradict the classical theories, we have got used to contradictions of this kind, but would, over and above this, be absurd in a logical and mathematical sense. Jordan illustrates this principle by the famous two-slit experiment. See my old Appendix V. Assume that there is a source of light from which monochromatic light falls upon a black screen with two parallel slits which are close to each other. Now assume, on the one hand, that the slits and their distance are sufficiently small, as compared with the wavelength of the light, to obtain interference fringes on a photographic plate which records the light that passes the two slits, and on the other hand, that some experimental arrangement would make it possible to ND out, of a single photon, which of the two slits it has passed through. Jordan asserts that these two assumptions contain a contradiction. I am not going to contest this, although the contradiction would not be a logical or mathematical absurdity, as he suggests in one of the previous quotations. Rather, the two assumptions would, together, merely contradict the formalism of the quantum theory. Yet I wish to contest a different point. Jordan uses this experiment to illustrate his formulation of the contents of the principle of complementarity. But the very experiment by which he illustrates this principle may be shown to refute it. For consider Jordan's description of the two-slit experiment, omitting at RST his last assumption, the one introduced by the words on the other hand. Here we obtain interference fringes on the photographic plate. Thus this is an experiment which brings forth the wave properties of the light. Now let us assume that the intensity of the light is sufficiently low to obtain on the plate distinct hits of the photons, or in other words, so low that the fringes are analyzable as due to the density distribution of the single photon hits. Then we have here one experiment that brings forth, at the same time, both the wave properties and the particle properties of light, at least some of them. That is to say, it does precisely what according to Jordan must be absurd in a logical and mathematical sense. Admittedly, were we able, in addition, to ND out through which of the slits a certain photon has passed, then we should be able to determine its path, and we might then say that this, presumably impossible, experiment would bring forth the particle properties of the photon even more strongly. I grant all this, but it is quite irrelevant. For what Jordan's principle asserted was not that some experiments which might seem at RST side possible turn out to be impossible, which is trivial, but that there are no experiments whatever which bring forth, at the same time, both the wave properties and the corpuscle properties of light. And this assertion, we have shown, is simply false. It is refuted by almost all typical quantum mechanical experiments. But what then did Jordan wish to assert? Perhaps that there was no experiment which would bring forth all the wave properties and all the particle properties of light. Clearly this cannot have been his intention, since even an experiment is impossible which would bring forth, at the same time, all the wave properties, even if we drop the demand that it should bring forth any of the particle properties. And the same holds the other way round. What is so disturbing in this argumentation of Jordan's is its arbitrariness. From what has been said, it is obvious that there must be some wave properties and some particle properties which no experiment can combine. This fact is RST generalized by Jordan, and formulated as a principle, whose formulation by Jordan, at any rate, we have refuted. And then it is illustrated by an imaginary experiment which Jordan shows to be impossible. Yet as we have seen, that part of the experiment which everybody admits to be possible actually refutes the principle, at least in Jordan's formulation. But let us look a little more closely at the other half of the imaginary experiment, the one introduced by the words on the other hand. If we make arrangements to determine the slit through which the particle has passed, then, it is said, we destroy the fringes. Good. But do we destroy the wave properties? Take the simplest arrangement, we close one of the slits. If we do so, there still remain many signs of the wave character of light. Even with one single slit we obtain a wave-like density distribution. But it is now admitted, by our opponents, that the particle properties exhibit themselves very fully, since we can now trace the path of the particle. 12. From a rational point of view, all these arguments are inadmissible. I do not doubt that there is an interesting intuitive idea behind Bohr's principle of complementarity. But neither he nor any other member of his school has been able to explain it, even to those critics who, like Einstein, tried hard for years to understand it. My impression is that it may well be the metaphysical idea described above under point 0. I may be wrong, but whatever it is, I feel that Bohr owes us a better explanation. Point 0. Appendix 12. The experiment of Einstein, Podolsky, and Rosen. A letter from Albert Einstein. The letter from Albert Einstein here printed in translation brief and decisively disposes of my imaginary experiment of section of the book. It also refers to a slightly different version contained in an unpublished paper, and it goes on to describe with admirable clarity the imaginary experiment of Einstein, Podolsky, and Rosen. Physical Review, pages 0, cf. my note on p. and section of my Appendix 11. Between these 2 points, a few remarks will be found on the relation of theory and experiment in general, and upon the influence of positivistic ideas upon the interpretation of quantum theory. The 2 last paragraphs of the letter also deal with a problem discussed in my book, and in my postscript, the problem of subjective probabilities, and of drawing statistical conclusions from Nescience. In this I still disagree with Einstein. I believe that we draw these probabilistic conclusions from conjectures about equidistribution, often very natural conjectures, and for this reason perhaps not always consciously made, and therefore from probabilistic premises. Einstein's literary executors requested that, if a translation of the letter were to be published, the original text should be published at the same time. This suggested to me the idea of reproducing Einstein's letter in his own handwriting. See pages. Old Lime. 9. Dear Mr. Popper, I have looked at your paper, and I largely agree. Only I do not believe in the possibility of producing a super-pure case which would allow us to predict position and momentum, color, of a photon with inadmissible precision. The means proposed by you, a screen with a fast shutter in conjunction with a selective set of glass filters, I hold to be inactive in principle, for the reason that I believe that a filter of this kind would act in such a way as to smear the position, just like a spectroscopic grid. My argument is as follows. Consider a short light signal, precise position. In order to see more easily the X of an absorbing filter, I assume that the signal is analyzed into a larger number of quasi-monochromatic wave trains Wn. Let the absorbing set of filters cut out all the colors Wn except one, W. Now this wave group will have a considerable spatial extension, smearing of its position, because it is quasi-monochromatic, and this means that the filter will necessarily smear the position. Altogether I really do not at all like the now fashionable modistic positivistic tendency of clinging to what is observable. I regard it as trivial that one cannot, in the range of atomic magnitudes, make predictions with any desired degree of precision, and I think, like you, by the way, that theory cannot be fabricated out of the results of observation, but that it can only be invented. I have no copies here of the paper which I wrote jointly with Mr. Rosen and Mr. Podolsky, but I can tell you what it is all about. The question may be asked whether, from the point of view of today's quantum theory, the statistical character of our experimental endings is merely the result of interfering with a system from without, which comprises measuring it, while the systems in themselves described by a psi function behave in a deterministic fashion. Heisenberg Liebogelt with this interpretation, without adopting it consistently. But one can also put the question thus, should we regard the psi function whose time-dependent changes are, according to Schrödinger's equation, deterministic, as a complete description of physical reality, and should we therefore regard the, insouciantly known, interference with the system from without as alone responsible for the fact that our predictions have a merely statistical character? The answer at which we arrive is that the psi function should not be regarded as a complete description of the physical state of a system. We consider a composite system, consisting of the partial system A and B which interact for a short time only. We assume that we know the psi function of the composite system before the interaction a collision of two free particles, for example, has taken place. Then Schrödinger's equation will give us the psi function of the composite system after the interaction. Assume that now, after the interaction, an optimal Wahl-Standage measurement is carried out upon the partial system A, which may be done in various ways, however, depending upon the variables which one wants to measure precisely, for example, the momentum or the position coordinate. Quantum mechanics will then give us the psi function for the partial system B, and it will give us various psi functions that differ, according to the kind of measurement which we have chosen to carry out upon A. Now it is unreasonable to assume that the physical state of B may depend upon some measurement carried out upon a system A which by now is separated from B so that it no longer interacts with B, and this means that two different psi functions belong to one and the same physical state of B. Since a complete description of a physical state must necessarily be an unambiguous description, apart from superficialities such as units, choice of the coordinates etc., it is therefore not possible to regard the psi function as the complete description of the state of the system. An orthodox quantum theorist will say, of course, that there is no such thing as a complete description and that there can be only a statistical description of an aggregate of systems, rather than a description of one single system. But rst of all, he ought to say so clearly, and secondly, I do not believe that we shall have to be satisfied forever with so loose and imsy a description of nature. It should be noticed that some of the precise predictions which I can obtain for the system B, according to the freely chosen way of measuring A, may well be related to each other in the same way as are measurements of momentum and of position. One can therefore hardly avoid the conclusion that the system B has indeed a d-night momentum and a d-night position co-ordinate. For if, upon freely choosing to do so, that is, without interfering with it, I am able to predict something, then this something must exist in reality. A method of description which, like the one now in use, is statistical in principle, can only be a passing phase, in my opinion. I wish to say again that I do not believe that you are right in your thesis that it is impossible to derive statistical conclusions from a deterministic theory. Only think of classical statistical mechanics, gas theory, or the theory of Brownian movement. Example: a material point moves with constant velocity in a closed circle. I can calculate the probability of ending it at a given time within a given part of the periphery. What is essential is merely this, that I do not know the initial state, or that I do not know it precisely. With kind regards. Yours, A. Einstein.